the fifth major event at NIAS in the series of events planned to commemorate Dr. Ramanna's birth centenary by thematically reminiscing different facets of this truly Renaissance man. As you are aware already, today's event is focused on nuclear physics research in India, an area in which Dr. Ramanna was deeply and actively involved. We have distinguished personalities present amongst us today who will be introduced to you in due course. Without much ado, I warmly invite Dr. Shailesh Nayak, the director of NIAS, a distinguished art scientist and Padma Shri awardee, to deliver the welcoming address. Sir, please come, the podium is yours.
Dr. Mohanty, Dr. Ramurthy, Dr. Grover, senior people from the associated with the nuclear research, my colleagues, very good morning to all of you. First of all, I am extremely grateful to you all for participating in this event, which is a part of Dr. Ramanna's birth centenary event. We have been conducting several programs starting from this January, and it will end to next January. So this is one of the such programs. Last month we had on the defense research, where Dr. Ramanna was very keenly involved. Before that, we had discussions on some of the philosophy, Buddhic and all, which also Ramanna has made very seminal contribution. I'm sure that the impact which he had on the nuclear research in India, we all aware that how we have progressed. We started in 60s and then 90s, and today, if you see, we are also discussing how nuclear energy can be used to achieve the net zero. So it has reached to a level where it is not only related to just to provide energy, but also to provide a sustainable energy, at the same time reduce our dependence on the fossil fuels. And in the research at NIAS, we realize that unless we switch over for substantial part to atomic nuclear energy, there is no way we can achieve net zero by 2070. Because all renewables and all possible, whatever advancement we make in future, in storage and everything, it won't be able to replace the existing structure. We may still have to depend on fossil fuel, but dependence would be much less, and the increase on the nuclear energy is going to increase. So we are at the stage where I think the nuclear energy again is in main focus, and I'm sure that whatever research which we have been doing or likely to be done or done in the past, which we'll be discussing, we will have some idea, some recommendations on what should be our future strategy to address this issue. I again welcome you all to this seminar, and I'm sure that this would be extremely useful to all of us. Thank you very much for coming. Thank you.
Thank Thank you, sir, for this very beautiful welcoming address. Now, I would request Dr. Ajit Kumar Mohanty, Secretary, Department of Atomic Energy and the Chairman, Atomic Energy Commission, to deliver the inaugural talk. Dr. Mohanty needs no introduction. He has been an eminent scientist in the nuclear physics community in India. Thank you very much. Please, Dr. Mohanty.
Good morning to all of you, Professor Ramanna, Dr. Gravur, Dr. Srivastava, Professor Rai, Dr. Bogi, and many colleagues, Professor Naik, Director Nias. And I'm very honored to be here to celebrate this centenary of Professor Ramanna. I just took the permission from my Guru Professor B.S. Ramurthy to talk a bit informally, because I haven't made any talk in written. And some points I have written, but now I realize I forgot my spec, even I cannot see that also. So, truly that I have not worked with Ramanna directly, because by the time I joined in 1983, he has already moved to OIC as a Secretary, Department of Atomic Energy and Chairman, Atomic Energy Commission. So, as Ramurthy rightly put it, I am his grand student, because I did PhD with Ramurthy, and my joining the fission physics section was a bit little different, because when I came in 83, I was confused. I do not know whether I had to choose science as a career or to go to the administration, civil service particularly. And I got the interviews get selected very easily, because Professor D.M. Nadkan was my chairman. I don't know what did I tell him, he selected me. Of course, recently unfortunate that we lost him. After getting selected, when I got the letter for joining BRC, I was not sure whether I should come or I should prepare for civil services. I met Ashok Tripathi, one of my senior friend, who was in MDRC to BRC, and that is the year he got selected in civil service and became #1 in Odisha and joined the IS. He was in trainees. So I met him in Bhubaneswar. So shall I go or I will prepare for IS? He says, you got selected, go there. And after training, you will get a lot of time. There is a very good library, you can prepare there. And that is how I landed in BRC. And while joining, I found out then which section I should join so that I get a lot of less work. And we went here and there. And it was a fission physics section led by Dr. Kapoor that time. And I could not meet him. In fact, I met Professor Ramurthy. He advised me. And after talking to him, I realized that this is probably the right section I should join, where work will be less. But then it never happened that way. And in fact, the fission physics section was a gurukul for me. And I came in contact with all the stalwarts, all gurus, like starting from Dr. Kapoor, Dr. Ramurthy, Dr. Nadkan, Dr. Ajitanand, Dr. Kataria, R.K. Chaudhary, Dr. Kailash, of course, he was not in that group, but from outside. So I changed my mind, and I continue taking physics as my career, and that is where today I am. And that is what my beginning is. But coming to the Ramanna's contribution, today this year we celebrated in 18th May 50 years of greatest contribution to Buddhist smiling. And in fact, this is a very important year. It is a 100th centenary year of Ramanna. Even Department of Atomic Energy has also completed 70 years this year. We are celebrating Platinum Jubilee in various ways, and this is one of such events which come in the Platinum Jubilee year. But he's a good scientist, good fission physicist, which you know, I will not be elaborating it here, but the aspect which you may not be knowing a little bit, it is his nation building. Because in 1966, Baba expired, it was an untimely death for him, And apart from many others, the person who has taken the lead is the Dr. Ramanna in science frontier, and particularly in the fission and fission-related study related to the reactors and accelerators. And making a explosive device in 1974 was not a joke. It was easier to make a reactor. Apsara came in 1956, but making a explosive device in a controlled way very difficult, because we did not know how to process plutonium at that time. It was produced in the Cyrus reactor, but processing was learned, chemical techniques were developed, and in fact plutonium, although it is a very beautiful element, from a nuclear physics point of view, Dr. Chidambaram said it is the engineer's nightmare, because anything processing with plutonium is heavily difficult. And this is where it is actually a material which changes itself very quickly with temperature. It is alpha, beta, gamma and delta phase. So little bit temperature it will make it very unstable. And we want to, in machining, we want a stable phase. And it was very difficult. But on the other hand, if you add little bit of impurity like gallium, 3%, then it becomes absolutely stable and come to the alpha phase. So these are the techniques dear scientists or these scientists learned. This was not shared by anybody. This knowledge was existing in Los Alamos for obvious reason. But then this is what Indian scientists learned. And when this explosion took place, it was needed for the country. Again, it is called peaceful nuclear explosion. But I always say it is a peaceful nuclear experiment. So it is a controlled experiment of uncontrolled phenomena. If you don't do that, you will not learn anything. How a nucleus behaves under compression, high compression and high temperature, and how the shock wave moves in the material. Still, when the nucleons are the degrees of freedom. We have seen the compressed material in stars, even creating the accelerators, what we call quark-gluon plasma. These are all created by us, but still the degrees of freedom is something different, not nucleons. But being in the nucleons, to see how the shock wave propagates, how the yield comes. So I say it is not an explosion, it is an experiment we did. But then this put us in the international scenario within the nuclear club. And we never make any weapons. We have the capability. This is the principle of Indian nuclear policy, that no first use, but we should have a minimum credible deterrent. And this is what we are moving it. But then this particular phenomena put India into the sanction list. Nobody, after that, nobody shared with technology, any knowledge, or any technological knowledge, nor any scientific knowledge. So we have been asking ourselves, it is probably a blessing in disguise, because we became more stronger after that, since 74 onwards. 98 also we did, that is Operation Shakti. And now today, if you see, a department, atomic energy, completely self-reliant, Atmanirbhar in all aspects. And this is the slogan we have taken a couple of years back, that made in India, Atmanirbhar, local for vocal, vocal for local, all those things. But you see, we are celebrating 50 years of Buddha smiling. So this is a platinum jubilee where we have been celebrating our Atmanirbharata. And we are Atmanirbhar, probably have taught to the rest of the departments or the people in the country. And this is what the Department of Atomic Energy. We are Atmanirbhar, we are going forward. And if you see Ramanna's, one of the slogan has been, when he superannuated as a Secretary, Department of Atomic Energy, 14 reactors are in operation. We have around that time 3,000, close to 3,000 megawatt of electricity. And his vision was very, very wide. He told that by 2000 AD, we should have 10,000 megawatt of electricity. It was a very ambitious program. We could not reach because of many reasons, not because that we are not capable of doing it. We had a problem, we have a financial constraints, we have a fuel constraint that time. And even people also, people of India or even globally, nuclear was not expected that well. So the program went slowly in spite of we having capacity. But today we have blown up again. We are running now 24 reactors. We have added our first stage program, second stage program, third stage program. It is all going well. This is all visualized, or it is a vision Dr. Bhava had. And we subsequently, the stalwarts like Sept, Ramanna, they all took it forward. In fact, jokingly I was telling that the three-stage program of Homi Jahangir Baba is a beautiful program. He thought in as early as 50 years back. He thought that we should use natural uranium in the first stage. Then we should use plutonium in the second stage. And then we should use uranium-233 in the third stage. That is the time it became so profound, it became the textbook level subject. In fact, I joined training school in 1982. We were taught very well. India has a first stage, second stage, third stage, but I never realized its importance. I thought it is a subject matter to be taught and to score some mark in the training school. And that is what I took it. Until recently I know what is a vision it was. In jokingly I was telling in some other day that the 3-stage program has imbibed in the Department of Atomic Energy so much. For me, any promotion I go for it, C2D, D2E, E2F, this is the thing I study and come. Because one question will be definitely there, what is the 3-stage program? And it is happening nowadays also. One question you can make out from the committee members, what is going to be. It is about the 3-stage program of the atomic energy. But the beauty is, he visualized long back. We have enough reserves, and I am very happy today to say that we have not only extracted plutonium, we have been very successful going to the second stage, that is our Bhabini, prototype fast breeder reactor. In fact, that fast breeder test reactor of Kalpakam, which is operating with a full power of 40 megawatt, it was critically it was obtained during the Ramanna's time in 1985. He was the pioneer of this fast breeder reactor programs also, and today we are in the second stage. And we have created a global news, international news today, because in a couple of months will be this reactor, 500 megawatt, fast breeder sodium cooled reactor will be operational in India. And we will be the second country, second to Russia, who will be having such a power plants. And if this happens, it is going to be a game changer. It is a breeder reactor. You cannot think any energy producing mechanism where the fuel will not be consumed. It will consume fuel like coal or any other thing. But this is the device, you will be producing more fuel than you consume it, because you will be breeding it. And and the blanket can be either uranium or it could be a thorium. And having from the blanket, we can derive uranium-233 or plutonium-238, and very well we can go to the third step. This will be real Atmanirbharta as far as the atomic energy program is concerned. And today we have a dependency on the fuel. In future, that will also go away. So this is the department today, and thanks to all stalwarts, including Homi Baba, Sethna, Sarabhai, Baba, and subsequently rest of the people, those who have carried this program. But today, where are we today? Our slogan has been that by 2030, we should be pushing our program quite a bit, nuclear program. As far as electricity is concerned, we are predicting 22 gigawatt. And that is a doable thing. We have a sanction. We have the reactors in the fleet mode. We have lands. Only we have to work it. And 700 latest, this February 2024, 2 reactors, 700 megawatt, first of its kinds, having advanced features, double containment, steel liner, all safety aspect. A reactor we have commissioned, that is Kakrapara 3 and 4. And like this, another 14-hour series we will be doing one after another. And Honorable Prime Minister dedicated to the nation in February this year, both of them. In fact, he witnessed the core loading of PFBR, fast breeder prototype fast breeder reactor in Kalpakam in March this year. And now I am told that next week, another reactor, 700 at Rajasthan. And after 6 months, Rajasthan 8 will also become critical and subsequently operational. And so, like this, every year probably we will be adding one reactor. That is our nuclear program is concerned. But then things have changed today. As rightly told, that nuclear has become a buzzword everywhere. In fact, they are not talking about big reactors. Now people are talking about small reactors, small modular reactors, even micro modular reactors. And it is being talked about everybody, probably Department of Atomic Energy talking less. It is talking about Railway Ministry. It is talked about everybody because they want a small reactor so that a small footprint they can put so that it can be replaced by carbon producing power sources with these nuclear sources. Railway wants captive power plant. Private people wants captive power plant. Everybody needs it. And this is the direction we are moving now. Fortunately, India is the country, although we started in a modest way, 220 megawatt, but this is nothing but a small reactor. and no country is having smaller reactor. If you go to the other countries, there are 1000 megawatt, 1200 megawatt. Fortunately, we had a 220 megawatt, which we have running for last 50 years very safely. Even our record of 220, if you see, we have run it in 962 days without interruptions. You cannot think of any plant runs such a long time. And in fact, most of the plants, we are running more than 1 year uninterrupted, and even 2 years. And we are closing down because of the regulatory requirements that after 2 years you have to go for the maintenance. That is the record of our track record, our safety, security, and how well we are running the nuclear power plants. Because all aspects we have taken care, and it is absolutely safe. So this 220 has come to the rescue today. We have declared it a small reactor now with these modifications, having a double containment, streamliner, and some other features to take care of the decay hydrogen, that hydrogen mitigation. So it is clear the safest reactor of smaller category and can be used as a captive power plant. That's why in this budget this year, if you see, it has been declared Bharat small reactor, and it has been declared that people should be adopting, and many private players are now, we are working together to deploy immediately for hard to abate industry like cement and steels, etc. Otherwise, they have to pay the carbon tax. And next comes, it is not the small modular reactor in that context, but modular reactor is nothing new to us. We have worked long back. I don't know how many of you have heard, maybe on 29th, one submarine was dedicated to the nation. We are not telling it, but this is on the newspaper. That's what I'm sharing in the small. That is called Orighat. The heart of the Orighat, it is a nuclear power plant of 86 megawatt electrical. And this is nothing but a small modular reactor, which can be fitted into a boat. Taken to the land, it will become a small modular reactor. And we have this technology today also. So this is what the research on small modular reactor, but we have to optimize whether we want a small reactor, 55 megawatt electrical, or we have to 100 megawatt electrical, or 200 megawatt electrical. This is the decision we have to take. But the technology is existing with us. It may be costly because we have to make one or two. Industries are not ready to make a mass production. Other technology is fully known, but probably this is the direction we will be moving. This is what we will call small modular reactor. The beauty is, it is a block. It is just a container having water inside that, and all pumps, steam generator are connected. So it is so modular, and you can transport it also. It is that safe. That is why that is the beauty. And next generation of reactor will be that SMR. Globally people are talking about, and we are also working on it. And again, people are talking about micro modular reactors. And micro modular means still smaller, 10 megawatt, 20 megawatt, 30 megawatt. Their temperature has to be very high. And when that happens, the temperature of the steam need not be used to the turbine which to produce electricity. Other than electricity, the steam temperature can be directly, heat can be directly used for many purposes. For example, hydrogen production. I don't need electricity always. I can use steam to produce hydrogen by many chemical processes, iodine, sulfur, copper, chlorine. There are carbon CO2-free processes in the loop. You can produce hydrogen, but you need heat for that. Steam can be used. In fact, electrolysis is the best source of hydrogen production. We don't have to use water. We can use steam electrolysis, more efficient. And so if you can produce steam at very, very high temperature, you cannot imagine temperature is 800 degrees centigrade, 900 degrees centigrade. If you do electrolysis, process is very efficient to produce hydrogen. But then who will give steam at that temperature? Only nuclear can give. Nuclear with high pressure if you put, and nuclear has a capability to give you the steam in a CO2-free, green, what I call green energy or green steam, where you can produce hydrogen. That is the next mission for our department. This is all about electricity production, but today the department has grown so big, thanks to Ramanna and his predecessors. It is I give an example to tell that it is like a mini India. You say that we are total, today we have grown into 30 units, 18 are core units like BRC, RRCAT, Kalpakam, VCC, so and so forth, and 12 are granting institute like Tata Institute of Fundamental Research, SINP. So put together we are 30, and I say we represent a mini India. Like granting institutes are completely free, autonomous, except funding, they don't depend on the DI, they are like states of India, and units are like union territory. We are bound by the government rules. So if you see, it is an amalgamation of union territory and states. They do the research what they want to do, and we do the research more project-based, mandate-based, and we do everything. Not only electricity production, we do basic research, we do applied research. This is you all know. And if I were to see that our motto, it is always has been atom for the service of the nation. And one service is, of course, electricity production, but then second is its application in the non-power sector. In fact, it is tremendous in the non-power applications of nuclear energy. It is giving us, like we have 10 or 11 visions. We work for energy security, we work for national security, we work for food security, we work for water security, we work for health security, basic research, education, everything. In fact, in health security, we have made a mark today. Like a couple of days back, there was a frantic phone call to me from the PM office, why BRIT is not giving LU-177. I don't know how many of you know. It is a short form lutetium-177, which is used as an injection for prostate cancer treatment. And BRIT obviously cannot give because they need the raw material from BRC, which is produced in Dhruva reactor. And Dhruva reactor is down for some reason because due to heavy rain, the water came in the sea water, there was a slit formation. So we could not cool the reactor, it has gone to shutdown mode. So once it became a shutdown, you see, as long as things are going, people are not remembering us. The moment there is a short supply, suddenly there is a reproduction, because why the radioisotopes are not produced. And in fact, today there are 75 odd radiopharmaceuticals we are producing using Dhruva and accelerator like VCC, medical cyclotron. And although it is not enough, 25% of India domestic market we are controlling by this radioisotope production. Remaining we are importing. This is the bad things. We need more. Probably we will be putting a reactor, dedicated reactor of 40-50 megawatt, similar to a research reactor, dedicated to isotope production. This is the need of the hour. And so that if that happens, even we will not be importing. And today 75% of radiopharmaceutical we are importing and 25% we are supplying. Although it is not enough, we have controlled the market price. There is no monopoly because of this 25%. But we want 100% we should be producing, and the reactor which we are proposing, it will be producing probably 800 kilocurie of radiopharmaceuticals, and our requirement up to that will be only 25%. And remaining 80% we will be able to export also. And this is probably we will be doing in a research mode, R&D mode, along with the BRIT. BRIT will be the supplier later on. And not only that, you see that we follow a closed fuel cycle. That nuclear waste, what we call, once you burn in a reactor, you start with the natural uranium, but after take out the burn fuel, you produce lot of isotopes, starting from plutonium, transuranium, fission fragments. And it was thought at a moment that you have to, what will do the spent fuel? But people in America and elsewhere, they throw it because they have enough fuels, so they dump. So the problem for them is the depository, geological depository, they have to store it. But for us from the beginning, the visions of Baba, Ramanna and others, we followed a closed fuel cycle for our one purpose. The meaning is, we need plutonium, so we started processing plutonium. In this process, we are able to process everything today. Even not only transuranium element, plutonium, actinium, and we are able to take out cesium, strontium, very easily handle. But the point is, whatever we are taking out, these are the gold mines, because you don't find them in nature. Ruthenium-106, a radioisotope, we take it out, it is a fission product. And you know it is a beta emitter, very soft beta emitter. And till this eye hospitals, Indian eye hospitals, they are importing the eye plugs from Germany, because it is used in the eye cancer treatment. They put on a silver plug, and ruthenium is a beta emitter. You put in the eye and treat the cancer. But now we have started processing it, making those plugs. We are selling BRIT through BRIT 50,000 versus 5 plugs if you import it. Similarly, cesium is a gamma emitter, yttrium, many things like that. All fission products we have taken out, which is otherwise not available naturally. So it is a wealth for us today. You are using for various purpose, gamma irradiator for food irradiation, either use a cobalt or cesium. So these are the things like that. So when I joined the department in 2003, when the visitor, 1983, when the visitor comes, very proudly we take him a division called WIP, Wealth, waste immobile plant. It is basically waste treatment plant. We tell them that see how we are following a closed fuel cycle, and then how we are treating it, how we are disposing it. But today we don't do anything, we take it out everything. So I have renamed that division Wealth Management Division. It is no longer a waste. So WIP, we call it WMD, Wealth Management Division. So this is the power of the Department of Atomic Energy. Water, isotope hydrology, we can find out where is the water source to research our water table in the ground. So everything we take, there is a application of atomic energy. And this is the department. And I'll just end telling one thing, that you remember that Jamsetji Tata, the founder of the Tata groups, he has 4 visions in his life. He thought that he will make a steel plant in India. He is a great nation builder and philanthropist. He wanted to build the country. He had 4 visions to build the steel plant. Second, he wanted to make a academic institute of world renounce. And third one, to make a hotel of world class. And fourth was to make a power plant. During his time, Hotel Taj came out. But then Tata Steel came much later. That became the first in Asia and definitely best in India. Then we have Institute of Science, Bengaluru, and Tata Institute of Fundamental Research, was because of his vision. Later on it came through Tata Trust to some extent. And but Tata Power also came. So today Tata Group, proudly they say that we build the nation. And in a small letter they write, we also produce steel. So same thing is for Department of Atomic Energy. I can say that we have the department, Indian Rare Earth. We take out the rare earth, which is not found anywhere. We do mining. We produce heavy water. We produce oxygen 18. We produce radiopharmaceutical. We produce everything. Take a name, Department of Atomic Energy does. So I say, we build the nation, and also we produce electricity. That is the Department of Energy. Thank you very much.
Dr. Mohanty, you started with a journey in the fission group, and slowly you expanded your talk into fission research and power production, and finally the diversification of the nuclear program. This is for all of us, this information is important, and particularly for our generation and the younger people, this periodical revisit is important. We are very proud of this strong and diverse nuclear program in India. So now we are entering into a special part of our program, and there could not be any better occasion for this program. We will do felicitation of Dr. Shyam Sundar Kapoor, who is one of the brightest students, or you can call it disciple, of Dr. Raja Ramanna, and it will be in a few parts. First, the introduction of Dr. Kapoor and his association with Dr. Ramanna will be read out by Dr. Srivastava, who is the fulcrum and ideator of this program. Then the reading of felicitation will be done by Dr. V.S. Ramamurthy, who is a stalwart student of Dr. Raja Ramanna. And finally, we have a special segment where I pressurized both Professor Ramamurthy and D.K. Srivastava to have a live video of the present day from Dr. Kapoor on his response, and they have very beautifully captured and brought it. We'll play it. Just to mention briefly before Dr. Srivastava is invited to the podium, Dr. Kapoor was former Director Physics Group, BRC, and they had very intimate interaction in the beginning days of building this fission group and nuclear physics group in India. Thank you very much. Dr. D.K. Srivastava, please, with your introduction for Dr. Kapoor.
Dear Professor Nayak, Professor Ramamurthy, Dr. Ajit Mohanty, distinguished guests, dear colleagues, ladies and gentlemen, and dear students. Very good morning to you all. Kabir, the famous saint poet, famously sang, Guru Gobind do khade, kaake lagun paaye, balihari Guru aapne, then Gobind ji ko bataye. Which means that when faced with any situation in which both Guru and God are in front of you, first bow down to Guru because he is the one who introduced you to God. I did not have the privilege of working directly with Dr. Ramanna, who remained a distant guiding star for me, whose brilliance I could admire, but whose life-giving warmth I could only imagine. Dr. Kapoor was much closer to us, whom I saw and admired, and from whom I was destined to learn a lot. Thus, I consider it a proud privilege to introduce our Guru, Dr. Shyamsundar Kapoor, one of the most distinguished students of Dr. Ramanna, at this Centenary event to celebrate the life and his contributions to shaping nuclear physics in this country. Dr. Kapoor was born on June 14, 1938. He earned an MSc from Agra University in physics in 1958 and started his eventful journey at the Bhabha Atomic Research Center, which was then known as the Atomic Energy Establishment. In 1959, he obtained his PhD in 1963 from Bombay University in nuclear physics under the guidance of Dr. Ramanna. Dr. Kapoor carried out postdoctoral research from 1964 to 1966 in nuclear fission at Lawrence Berkeley Laboratory, Berkeley, and was a visiting scientist from 1980 to 81 at the University of Heidelberg. He provided inspired and visionary leadership as head Nuclear Physics Division, Project Director, BRC TIAP Electron Accelerator Facility, and Director Physics Group and Electronics and Instrumentation Group at BARC from 1990 to 2000. He was DAE Homi Bhabha Chair Professor from 2000 to 2005 and a Senior Scientist with the Indian National Science Academy from 2005 to 2008. He has been an honorary scientist of the Indian National Science Academy since June 2008. Professor Kapoor is a recipient of the Sant Swarup Bhatnagar Prize in 1983, Goel Prize for Physics in 1986, and R.D. Miller Award for Physics in 2006. He has delivered several award lectures during his long and illustrious career. He is a fellow of the Indian National Science Academy, New Delhi, Indian Academy of Sciences, Bangalore, National Academy of Sciences, India, Allahabad, and Institute of Physics, UK. He was president of the Indian Society for Radiation Physics from 1995 to 1997, the Indian Physics Association from 1997 to 1999, and president of the Physics section of Indian Science Congress in 1994. Dr. Kapoor has made outstanding and pioneering contributions to the experimental study of neutrons, alpha particle and heavy ion induced particles emitted in fission to probe the characteristics of large-scale nuclear motion. His meticulous experimental studies revealed correlations between the fragment mass, charge, and total kinetic energy in binary fission. He has established a new type of nuclear splitting process which proceeds on a fast time scale. When I went to Calcutta 2 weeks ago, my colleagues there showed me the preliminary results of similar studies underway using 25 MeV per nucleon oxygen-16 beam from the superconducting cyclotron to study various contributions to the process of fission. Dr. Kapoor will forever be remembered for his alternative method of calculating cell model corrections to fission barrier in heavy nuclei and his suggestion that the route to production of super heavy nuclei must proceed through heavy ion collisions leading to a cold compound nucleus to take full advantage of these corrections, which he developed with Professor Ramamurthy and Kataria. Dr. Kapoor was instrumental in facilitating the commissioning and utilization of several nuclear facilities and unique detector systems in the country, participation of Indian researchers in experiments at Brookhaven National Laboratory, New York, and the Large Hadron Collider at Sept in Geneva, and preparing the detailed and meticulous roadmap for the accelerator-driven subcritical systems as inherently stable nuclear reactors and incinerators of nuclear waste. It is often said that other trees do not grow under large trees. He is a living example of one who formally negated this notion as he nurtured several brilliant and extremely competent researchers and rejoiced in their achievements. There is no aspect of nuclear fission and heavy ion collisions in the country which has not benefited from his deep insights and guidance. His enthusiasm and tenacity are contagious, and his eyes for detail and his acumen for accuracy have remained a guiding light for at least 2 generations of researchers in the country, one of whom, who called himself great disciple, you just heard. Most importantly, he was never swayed by the current fashion. I remember with fondness and pride the firm stand he took in clearly stating that the so-called claims which reported cold nuclear fusion were unfounded. We were very excited at the possibility of Dr. Kapoor with us today, but advancing years and associated difficulties have prevented him from being present. He has sent a recorded message which we shall play shortly. With this surely and severely inadequate introduction of Dr. Kapoor, I would like to invite his long-time collaborator, Professor V.S. Ramamurthy, to read the felicitation of Dr. Kapoor on behalf of the National Institute of Advancement. Thank you. Thank you, Dr. Srivastava. On the occasion of the Raja Ramanna birth centenary celebrations, the National Institute of Advanced Studies to felicitate Dr. Shamsundar Kapoor, one of Raja Ramanna's most well-known research students and collaborators. Born on June 14, 1938, Kapoor had his early education in Agra and graduated through the training school of the then Atomic Energy Establishment, Bombay, in 1958. As a member of Ramanna's research team, Dr. Kapoor made significant contributions to neutron and heavy ion-induced fission and fission-like reactions,
and nurtured a new generation of brilliant youngsters in nuclear research. He led the team for setting up the medium energy heavy ion accelerator facilities in Mumbai. Under his guidance, blueprints for accelerator-driven subcritical systems for inherently safe nuclear power and nuclear waste incineration were also prepared. Signed by Dr. Shailesh Nayak, Director, NIAS, today. Thank you very much.
Now, as mentioned earlier, we will be playing the...
This is Dr. S.S. Kapoor, former PhD student of Dr. Raja Ramanna. It is nice that a one-day program in nuclear physics is being organized by National Institute of Advanced Studies as a part of Dr. Raja Ramanna birth celebration, centenary celebration event. I would also like to thank the organizers to remember me on this occasion, because I was his first student who got PhD under his guidance. I was hoping and was in fact was looking forward to taking part in this one-day meeting so that I can express my interactions with Dr. Ramanna in this meeting also. But unfortunately, due to my personal constraints, I am not able to come and participate in the meeting, for which I offer my sincere apologies. Because I could not come, I had sent a reminiscences of with respect to my association with Dr. Ramanna to the organizers, and in which I have mentioned about all the scientific interactions which I had with him. In fact, from time to time, I had Dr. Ramanna was encouraging always free and frank discussions, and I was also taking part in many of these discussions throughout, whenever he was present or when he was coming to Bombay to discuss. Dr. Ramanna was quite active till the end, and in fact, whenever he was in Bombay or otherwise, he was coming to Bombay, he was still getting time or finding time to come and discuss programs in nuclear physics, heavy ion physics and all that. He was, as I mentioned, he was active till the end, and in fact, I remember 15 days before the end came, he had phoned me up and asked me to send him some transparencies because he was going to give a talk. I was quite surprised that he was still actively taking part in his academic activities and giving talks at his age. I know that Dr. Ramanna's contributions were not just limited to fission and heavy ion physics and nuclear physics, but he has made contributions in so many areas, scientific areas, in the development of science and technology in the country, and for which, so in the end, I once again offer my respectful homage and tribute to him.
as all of you are aware that now we will be moving to that talks for today. So before we start the talk, I will be requesting Dr. Ajit Mohanty, Professor Shailesh Nayak, Dr. V.S. Ramurthy and Dr. D.K. Srivastava and Professor K. Siddhappa to come up to the stage and just for the beginning session, and then you can come down. So then you can break for tea.
The stage has been prepared. I was wondering why it is empty. Yeah, I was also thinking.
Professor Siddhappa will be chairing the first session where the talk will be given by Dr. Amit Roy, and Amit Roy will be introduced to you by Professor K. Siddhappa. Professor K. Siddhappa, a well-known nuclear physicist and former Vice Chancellor of Bengaluru University. Sir, I request you to introduce our speaker, Dr. Amit Roy.
Good morning to the dignitaries of the dais and all my friends and colleagues sitting there before the dais. Well, it is my great pleasure and privilege to introduce one of the very great researchers of the country and internationally famed Dr. Amit Roy. Amit Roy completed his master's in physics from Delhi University in 1968 and his PhD from Tata Institute of Fundamental Research, Mumbai, in 1975, where he continued till 1990 as associate professor. He has worked at Florida State University, USA, KVI, Netherlands, and Argonne National Laboratory, USA. Dr. Roy joined Inter-University Accelerator Center, formerly Nuclear Science Center, as a senior scientist in 1991 and was its director from 2001 till July 2013. During this period, I happen to know him very intimately as council member and committee member of the then well-known Nuclear Science Center, and also 3 of my PhD students worked for their PhD in Nuclear Science Center. And here he led the team during that period of researches. He led the team for building the superconducting LINAC now known as IUAC, Inter-University Accelerator Center, and pioneered the department of the neobium superconducting cavity for accelerator in the country. He was a DI Raja Ramanna Fellow at Variable Energy Cyclotron Center, Kolkata, till May 2017. His research interests are in nuclear, atomic, and accelerator physics. Dr. Roy is a fellow of the National Academy of Sciences, India, and received the Eminent Scientist Award of the Indian Nuclear Society. He has served as the President of the Indian Cryogenics Council, as the Chairman of the Asian Committee of Future Accelerators, and as a member of the International Committee of Future Accelerators. He enjoys communicating science and has written the Great Experiments series in Journal of Science Education, Resonance, things like that. Thank you. I welcome Dr. Amit Roy to give his first inaugural lecture in technical sessions.
Thank you, Professor Dappa, for giving me, for making this kind words about me. To all the distinguished guests on the dais and many of my friends and colleagues and others who have come here. I hope there are some students as well. I will, when Dinesh asked me to assign me this topic of research in India, historical perspective, I think he thought it, because I was the most senior of the speakers, so he selected me for the historical perspective. Because once you are reach that age, you are no longer good for doing any new research, so you start looking at the history. Well, I have been actually interested in science history from my very early days, when I was doing my actively in research as well. So I will just take you through. Of course, this is history is always a personal perspective. So whatever I will talk about is from my own perspective view of development of nuclear physics. Many of you may not agree with all of it, but if you don't like it, you blame Dinesh for selecting it. Well, this is Dr. Ramanna. I want to pay tribute to him on this celebration event of his centenary. And you can see this picture with Pandit Nehru, Prime Minister at that time. This is from the inauguration of the TIFR building in 1962, January. And this is from the TIFR archives. And I wanted to show this particular slide because you see at the background behind Pandit Nehru, it says nuclear reactions. In fact, I joined this group in 1968, 6 years after this photograph was taken. And Professor Ramanna continued to be a professor of our group, nuclear reaction group. And in fact, when I joined there, he used to come to the TIFR only on Wednesdays to attend the physics faculty meeting, because that was held on Wednesdays. And at 8:30 in the morning, he would be there on Wednesday. There was a room for him in our group in TIFR, and he would come there. And I was the only other person in that whole group coming at that early, at 8:30, because I had to go there, because I had to go to the canteen for breakfast. So I used to meet him at the time. The first day he saw me, he said, so what are you doing here in this group? So I told him, I just joined as a student. So he encouraged me, he said, yeah, it's good, continue doing your work. So he kept me encouraging. So that was my first interaction with him. And in fact, after that, he was busy in many things. By that time, he had grown much bigger, and in his stature and went up in career. He became the director of ARC, then he became the Atomic Energy Commission, then he went to Delhi. And I left TIFR at the end of 1990, in January 1991. And before that, around the late 80s, he had come to the auditorium to give a performance, piano recital. And in fact, when he saw me, I was there in the audience, and then from a distance he saw me, and he immediately waved at me. So he remembers. I mean, his memory was phenomenal. I mean, I think Ramurthy will also verify to that, and others who have interacted with him, you know, his fantastic memory. If you knew somebody, you know the person and you remember him till his last year. So that was Professor Ramanna. Now I go to the historical perspective as how nuclear physics developed in this country. Well, so I divided into sections. One is the pre-47, pre-India independence. And in fact, nuclear physics started in India very early. I would say 1932 is the seminal year when nuclear physics was born. with the discovery of the neutron by Chadwick. Because with the neutron, there could be a probe which would start probing the nucleus without even any accelerator, with the natural sources that you could do. And that's how the nuclear physics, actually studying of nuclear inside the nucleus could appear. But Rutherford had given a call in 1927 in one of his speeches, asking for an accelerator device, an accelerator, which will accelerate ions to higher energies, say 10 MeV. That's what his goal was, 10 MeV, so that he could study the nucleus. By that time, he had already discovered the nucleus, and then with Bohr and Rutherford Bohr model of the atom was there, and he wanted to study, of course, the nucleus once it was discovered, what is inside it. So he realized immediately that since there is a Coulomb repulsion, the nucleus is a positively charged system, and any particles that you want to put in once it comes in, because he also realized that the nucleus is holding together, and the interaction will take place only when they come close to each other, almost touching distances. So nuclei do not interact through the strong interaction, the nuclear interaction, unless they are at touching distances of the order. So to come to that, you have to overcome the Coulomb barrier. So you need energy to overcome that, and you need an accelerator, which he thought 10 MeV would have been nice for him, because he had the highest alpha particle from natural sources, radioactivity was 7.7 MeV. So he encouraged his people, and of course Crockett and then Lawrence Berkeley, they started developing the accelerators, and nuclear physics progressed. In India, there were at that time great stalwarts, and who thought about they understood the importance of nuclear physics, and they thought we should start the study of nuclear in India itself. So they got hold of neutron sources, and so this is how it started, and that started in the city of Kolkata. And it was done by none other than Professor D.M. Bose, W. Bose. He is the less well-known Bose of the three famous Boses. The two others overshadow him. There is Acharya Jagadish Bose and Satyendranath Bose. But Devendra Bose was also an equally brilliant scientist. He was the nephew actually of Jagadish Chandra Bose. And he had worked with Rutherford's lab with Wilson, and he made the cloud chamber. He learned the cloud chamber, and he went to Germany after that. This was before the First World War, and he got stuck in Germany for 5 years during the war. He could not come back. And there he was working in Berlin with Wegener, a cosmic ray pioneer. And Wegener told him that since you have been to Cavendish and you have seen Wilson making a cloud chamber, why don't you make a cloud chamber for us? And he made the first cloud chamber outside England. It was done by D.M. Bose in Berlin. And when he came back, of course, he built the cloud chamber in Calcutta. He joined the Calcutta University. And of course, in 1937, after Jagadish Chandra Bose died, he took over the Bose Institute and became the director. He was there till 1960, or 30 years he was the director of Bose Institute. And his student, Shamadas Chatterjee, joined him also in the 1930s, and they started working with neutron sources and reactions. And 1939 January, fission was announced to the world in the paper. There was the Harman Strassman's paper in the German magazine, and Lise Meitner and Frisch's paper in Nature, which actually gave the name fission and explained the process that Hahn and Strassman observed. So with that, as soon as the news came, Shamadas Chatterjee, in the meantime, had learned to make Geiger-Müller counter ionization chambers, learning by talking to Radheshyam Ghosh, who has worked in Germany with Geiger, and he had come back to Calcutta University. And from him, he learned about the Geiger-Müller counter, and he developed it with local, whatever was available to him in Calcutta, with his own money. He got the gases and the wires and everything is to purchase out of his own money. And as soon as he heard about the fission, he had a radium-barium source, producing neutrons, And he bought 5 grams of iridium out of his pocket money. And then started studying fission. And he, with this IGM counter, he could see the pulses, and in oscilloscope he would show these fission pulses, and all the visitors that would come in, he would show it. He had moved to Bose Institute by that time, because with Devendra Bose, his student, and started doing the experiments. And then he observed that after, so when the radium source is there, of course you get the fission events. But when he took the radium source away, he still got some big pulses coming. So he was puzzled what was going on. So he went to Satyendra Bose and asked him, described to him what is this. He's observing some pulses. So SN Bose said that maybe the cosmic ray neutrons are coming in. So this could be giving you these pulses, causing fission. So he put lead, cadmium, all this shielding that he could gather and put that thing. Still, his counter was recording these pulses with the uranium present. And he took the uranium away, of course, nothing was there. So he went back to Satyendra Bose and said, what is going on? I can't still understand it. Even I put all kinds of shielding around it, and still these pulses keep coming. So Satyendra Bose said, maybe there is some, maybe uranium spontaneous diffusions. So he was encouraged. He said he did the detailed study. Then Satyendra Bose said that you write it up and submit a paper. So he wrote a letter to Science and Culture, and of which Devendra Bose was the editor, his boss. And at that time when he wrote this paper, D.M. Bose was in Darjeeling, away in India. When he came back, he saw this paper by Srivastava Chatterjee on his table. And so he called him. He said, what is this? So he says, as I've observed this spontaneous fission, and he says, oh, no, this is all wrong. In fact, in Bengali, this is what I have heard from someone who has heard from Srivastava Chatterjee. So it's a second-hand knowledge for me. But I have heard this thing corroborated by several others, to whom Srivastava Chatterjee has related this. So it says in Bengali, he told him, DM Bose said, fission to one mathay hocche. So fission is happening in your mind. So he said, so you withdraw the paper. So he forced him to withdraw this paper. And then he said, you go and study this further, more carefully. Because the reason I think what DM Bose said this, because by that time, Bohr and Wheeler's theory had come of fission. And that theory predicted that uranium can spontaneously fission, but the lifetime should be up to 10 to 22 years. And what Srivastava observed was lifetime he calculated the half-life of this fission, spontaneous fission, which he observing was 10 to 16 years. 1 in 0.3 in 10 to 16. So it's 10 million times faster. So that, of course, DM Bose didn't accept it. And so the unfortunate thing is within 2 months' time of that event, Teorov and Petrak in Moscow, they had studied this same phenomena and confirmed it with of course much more elaborate 6 counters, and they had a much bigger team. They went down to the Moscow underground to get shielded from cosmic rays, etc. And they published it. And there was a small footnote. Actually, it's published in Russian journal, and a small telegram-like thing appeared in Physical Letters in 1940, for the reference which is given here. You can read that. So that's one of the things lost. But then Srivastava continued further, and he did. And he was actually the first head of the Department of Physics in Jadavpur, and he was a pioneer on many things. He started radiocarbon dating, first radiocarbon dating lab in the country. He studied cosmic rays. He also studied the helium production from the springs, hot spring, and things like that. I mean, it's a brilliant experimenter. If you are interested, you can read this article which I had written in Resonance about him. And this is D.M. Bose and his student Viva Chaudhary. This is again another unfortunate, near miss again. They studied, they had set up, D.M. Bose, as I said, he set up all these activities, nuclear reaction fission, artificial radioactivity and neutron, ionization chambers, Wilson cloud chambers, photographic emulsions also they started. And with the photographic emulsions, B.Y. Chaudhary and Dave Bose, they exposed these photographic plates in Sandakpur, which is a little higher than Darjeeling and the hills. And from there, they developed these plates and they could see many tracks. And they observed tracks of a cosmic ray particle of the mass for which they calculated the mass to be 200 times the electron mass. So, and they called it the mesotron. They published in Nature the mesotron, estimation of mass of mesotron for photographic emulsion. This is a technique which was invented by B.Y. Chaudhary, how to estimate the mass from the track, the density of the track and the length. From that you could find, because density depends on the range, energy loss of the particle, which is again dependent on mass, charge and mass, and then the range gives you the energy. So from that you can find out the mass of the particle. So they estimated this, they actually discovered this method of estimation. In fact, this method was used by Cecil Powell for identifying the biomeson. In fact, B.Y. Chaudhary by that time had also been to Bristol. Here she was working with Blackett's lab, and with Powell was there. So they discussed the thing. And Powell actually acknowledges that they used B.Y. Chaudhary's method in his Nobel lecture, but not in his paper. Not in the paper which published the discovery of biomeson, but in his Nobel lecture he mentions it. You can read that. So this was in the other stalwart at that time, other stalwarts in the country were of course Meghnad Saha and C.V. Raman at that time, working in India at that time in the 1930s, and both were interested in nuclear physics. In fact, both of them sent their students, their favorite students, to study nuclear physics. R.S. Krishnan, Rapil Sangameswara Krishnan, who was in IASC. In fact, he was a student by the time Raman was in Indian Institute of Science director, and then he sent his students to Rutherford. In 1938, he wrote to him, and 1938, by the time Krishnan reached Cambridge, Rutherford had passed away, and the war had almost 39, he reached January, and the war soon broke out. So many people, like even Chadwick and all these other people, were taken into the war effort. So there was a cyclotron there at Cavendish, and Krishnan worked on the cyclotron and got his PhD in 1941, investigations in artificial radioactivity using cyclotron. It was highly praised by Chadwick and Crockett also. So when he came back, Krishnan wanted to build a cyclotron in Bangalore, in the Indian Institute of Science, but there are a lot of things happened in this process, and finally he couldn't do it. This is the picture, which is the arrow mark shows R.S. Krishnan, and he finally gave up nuclear physics, and he was the guy who started in solid-state condensed matter physics group in IASC. That was the beginning. And in Calcutta, Meghnad Saha was also interested. He had been to a tour of US in the 1930s. In 1936, he went to Berkeley, at Lawrence Berkeley Laboratory, and he talked with Lawrence, and was very much fascinated with the cyclotron. So he wanted, when he came back, he sent his student, B.D. Nath Chaudhary, to work with Lawrence, to build, and then build and get the parts, build the cyclotron, help ask Lawrence to help them build the cyclotron in Kolkata. Which Lawrence agreed. In fact, he took care of Nath Chaudhary, and he got his PhD in 1940 from Berkeley. And when he came back, in fact, he also, not only that, he got some funds, and he sent the money, and he bought some parts for the cyclotron and shipped it before he came to Nath Chaudhary, and shipped it to India before he came here. Unfortunately, it was coming in a ship, and when it came to the Straits of Singapore, that near the Malaysia-Singapore border, I think the war was going on, and Japanese U-boat torpedoed that ship. So that thing sank. So those parts are lying somewhere there. So he couldn't make the cyclotron before the independence. And after independence, again he took it up. He got some funding from the Tata Trust, and then the cyclotron parts were bought, and then it was assembled. And so this period, I call it 1945 to 1980, so starting from independence time. And this is the picture with A.B. Patro, V.D. Chaudhary and M.N. Saha with the 37-inch cyclotron which they got built in Kolkata. In the 1940, started in 1948. It was 53. It started internal beam, and finally being extracted by 1956, and the experiment started in Kolkata. And the three people here you can identify. The one on the left, A.B. Patro, who was the first director of Nuclear Science Center in Delhi, and the second position is V.D. Chaudhary, who became the Defense Science Advisor later on, to a science director, and then Professor Meghna Shah on the extreme right. And in Bombay, by the time Baba had already started the TIFR in 1945, and then in the 50s he also wanted to start the nuclear physics work, and in 1949 Dr. Ramanna joined Baba, and he had in that earlier club where the DAE offices were on Ajit sits. There were the two blocks which are called actually old TIR club's servants' quarters, which were the hostels for the TIR. I also stayed there for 3 years in that hostel. And when Professor Ramanna came in 1949 to India, he had a place. He stayed in that hostel, and Baba allotted 2 rooms to him on the 3rd floor. He got one for himself, one for his piano. So that was especially allotted in that hostel. And Ramanna's lab was the ground floor. And actually, these were the servants' quarters, which was converted into a TIR hostel. So this is the place where he was. And in the same block, I occupied many years later. I stayed there for 3 years on the first floor of the same building. And 53, he got the casket. He bought the casket generator, from Philips Eindhoven, and it was installed at TIFR in the hall, which today this particular casket hall is the electron user hall, and in the first user hall where the experiments were done, where Ramamurthy also did his experiments in the beginning, the early stages. And this is the casket copper generator, and Professor Dr. Ramanna was the first person to use this machine for doing neutron fission studies and neutron diffusion studies. In fact, when I joined in 1968, there were huge blocks of beryllium oxide, bricks of them. Tons of them were lying there and in one corner. In fact, these are the ones which he used for studying the diffusion field, the neutron diffusion for his reactor studies. Professor Ramanna. And in fact, I was the last person to use this machine for my PhD work, this particular quantum casket. And this is Professor Ramanna's, Dr. Ramanna's picture in the Old Beer Club building in 1956. This is again from TIFR archives. Well, at the time, to rush through now quickly, the situation in the 50s where there were a lot of activities going on and the accelerators were at the time were so small, and India could still afford to have some accelerators. There was a effort to make indigenous accelerators. In fact, in TIFR in the 53, 54, there's a group formed with A. George, A.S. Divatia, M.K. Mehta, Abe, Deshpande, Ram, and Varghese. This is they started working on the TIFR Van de Graaff accelerator, and they succeeded in making a 150 keV Van de Graaff accelerator. But for some reason, I couldn't figure out. Baba had stopped this program after this. He stopped all these, closed down the accelerator program, and these people were rehabilitated in different places. I know Dr. Divatia was the first director of VECC, and Dr. Mehta was the nuclear physics, and he started going into nuclear physics. In fact, Dr. Mehta went to Florida State University to his PhD, where I did my postdoc. And then the other places where the accelerator was built was again the person who was there, Piara Singh Giri and Arnam Singh Hans and Aligarh between 1949 and 62. They worked there. They built a 150 kilovolt cascade generator, and as a neutron generator, they started using this for nuclear physics. And there was later on in cyclotron, there was like when Hans moved to Punjab University, Chandigarh, he got a cyclotron from Rochester, old used one, and then they revived it, and it was run. It just started functioning in 1975, and it's still there, it's being used for some more. And then there was in 1963 we got the Van de Graaff accelerator 5.5 MeV came to ARC. It became a workhorse for the nuclear physicists in Bombay. In fact, I also used it for my PhD work, part of the work I did at which has been converted into a 7.5 MeV tandem later on. And there was a 2 MeV Van de Graaff at IIT Kanpur in 1968. It was installed. It was G.K. Mehta was there, who was looking after this. And there have been some people here. Ajit Mohanty is here, who got his PhD from that machine. And I happened to go there and use it also once. So in fact, I had the distinction of using all the accelerators in the country, which started from the very beginning till today. There was, in the 50s, the reactors came in and gave another flip to the nuclear physics researchers because you could get radioisotopes. So there was a lot of beta decay activities going on, and then isotopes had to be bought from outside. But once these reactors came in force, August in 56, the Upsaran and then Sidus, they started producing isotopes. And then, of course, neutron studies were continuing, as Dr. Mohanty also said. The nuclear fission physics activities went on unabated in BRC. For even today, there are the disciples, the grand and grander disciples of Dr. Ramanna, who are continuing this tradition of fission physics in Bombay. And the 50s, 60s, there was a vibrant community of theory and experiment. When I joined in 1968, there was really excitement in nuclear physics. There were a lot of theory people also in Bombay, in Kolkata, in Bhubaneswar, and Kalighat, Andhra University, BHU, there was Professor P.C. Sood, who was actually a mentor of Ashok Jain. He had a very vibrant group, theory of nuclear physics. So many places in Punjab. So nuclear physics activities was really thriving at that time, both in theory and experiment, complementing each other. And a lot of things, which I've just noted down some of the things there. And there was strong emphasis on instrument building, because money was scarce, so everything has to be built at home. Electronics were built, and radiation detectors were built. In fact, we started, and when I joined here, there was a program for making germanium detectors. It was made in our group. Germanium detectors, I have used them. And the silicon detectors, lithium drifted silicon detectors. I've used, in fact, the only paper I have in Nature is with that, with a homemade lithium drifted silicon detector. So, but then considerable slowdown started in the late 70s and then in the 80s. So why this happened is because the accelerators in the worldwide spectrum, the energy scales has gone up. People are starting using heavy ions and higher energies, which are not available to us. The bigger machines were costly and money was not available. Foreign exchange was extremely scarce. In fact, I had to wait for more than 7 years to get a $1,000 multi-channel analyzer. Because for that I had to work with a single channel analyzer and then shifting the spectra of gamma. Imagine taking a 10 to 12 MeV gamma spectra in a 400 channel analyzer, which is home built by the electronics division in BRC. That is the one I was using for 5-6 years. So we didn't have the money, and then many researchers of nuclear physics at that time started moving away. Some went to space, some into administration, some went to, and many of them converted, in the universities converted to themselves to solid state physics and material scientists. Because that was much easier to, the experimental setups were much easier to maintain and less costly at that time. Today, condensed matter and material science is equally expensive, and sometimes more than even nuclear physics. So this is the situation. But then it started, one event which actually changed the scenario in the country of nuclear physics is the construction of the very early cyclotron center, successful construction, indigenous construction of the cyclotron center. The first large machine made in India. In fact, it was, I would say, we went to the ridiculous extent of even making gate valves. in locally. So, which was not functioning all the time very well. Sometimes they would leave. So, this was actually making India into the extreme end. That make everything in India, nothing to be imported. So, anyway, it succeeded to some extent, but not to the level which as a researcher, I would have liked. But anyway, we did the experiments and could start publishing things. Power situation at those days was very bad in Kolkata. We used to work at night. The machine used to run only at night with diesel generators. And for diesel generators, 4 megawatts of power, captive diesel generators were installed in VCC to run this cycle from. And we could do experiments only at night. But anyway, this was how we did. Many of the other at the time, the people who grew up in the generation would remember that time. But this machine works beautifully even now, today. Of course, it has been refurbished with many of the things. Parts have been changed with modern things. And then it's actually today runs better than it was running when I was doing my work here. The other two things which also added to the two facilities which added to the nuclear physics repertory is the medium energy the heavy center at TIFR, BRC. This is a BRC TIFR project. This Pelletron at TIFR, CJJ TIFR, which again they added the booster LINAC, superconducting LINAC with the lead-based cavities, and that started functioning. And then the other one is the Inter-University Accelerator Center, which at that time was the Nuclear Science Center. The 15 UD Pelletron was installed. That's a watt machine, and then the linear accelerator which we developed there locally. So with this, there's a full-blown research in nuclear structure, especially experimental work, started in the structure of nuclei, interplay of single particle collective movements. You will hear more of the details of it from the later speakers. They will talk about all this high excitation energy in the nucleus, compound nucleus, high spin states and high isospin states. So these are the three areas to explore with the energy available and the variety of heavy ion beam and target projectile combinations. You could generate almost any nucleus at will and then study their properties. And then nuclear reaction dynamics, direct compound fission, fusion reactions, nucleosynthesis, reactions of nucleosynthesis interest, and so on. And I will give you a few random examples. It's chosen by me. 5 minutes. Yeah. A few random examples only, not to be taken very seriously, in the sense that not in the best contributions. This is one where the Ramur Theatre. In fact, some of the authors are sitting here in the audience also, along with Ramurthy. This is the first physical data paper from the Pelletron. And then this one is again from our group. I show this Mahananda, who is right now at ANU, professor at Australian National University. Her thesis work where we did the compound nuclear process. And then this is a beryllium-7's the solar neutron problem related S17 factor, astrophysical factor, done at UAC using the recoil mass separator to produce a very pure beam of 7 beryllium, first radioactive beam in the country, and then with that experiment was done. And then there is a structure work where I think Ashok's student Deepika Chaudhary's work on the structure of nuclei, showing the variety of nuclear shapes and sizes and motions that it can take under high spins and excitations. And then this one is from chosen from VCC work, giant resonances, which is a motion on the nuclei, the proton and neutrons against each other, sloshing each other. So that vibration set up certain states which are called the giant resonances. And if you measure the giant resonances, the widths of them, you can find out the viscosity of the nucleus, nuclear fluid, And they found out the eta by S ratio, the viscosity to entropy ratio, which is about 2.5 to 6 times the h by 4 pi kb, which is the estimate, and for a perfect liquid is 1 by 4 pi k. And this is a factor of 2. So these are also liquid, that means it's a liquid. In fact, it's very similar to what the high energy physics in high energy nuclear physicists have observed in quark-gluon plasma. The result that the eta by S there at very high energies and very high energy densities, the quark-gluon plasma becomes liquid, more like a liquid rather than a gas, which is surprising. So this shows the parallelity of the nuclear state in this very ground, near the ground state, small excitations, as well as in the quark-gluon plasma state. So there was a game changer came in 2000. I just quickly take your indulgence for another 2 or 3 minutes quickly to go through that. This actually game changer because this is the first time a large number of people from all various institutes collaborated in doing an experiment, type of experiment, set up an experiment. It's called the Indian National Gamma Ray. In fact, for that, a lot of credit goes to P.S. Ramurthy because he was the DSC secretary at that time. He told all of us that you are not going to get any money unless you work together. So this he told me. In fact, finally also this project wouldn't have come through unless it was him, because he came one day to my office in Delhi and said, Amit, you write me this particular letter. So I just wrote it down, typed it on my typewriter, this computer, and then gave him the same letter. I will not say what it was. Anyway, it was, so I gave him this that letter. With that letter, he got this money through. So this is how and this particular system has gone around the country, from Kolkata to Delhi to Bombay, and it has produced fantastic work. In fact, after this, people realized that if you work together, everybody wins. So that's what, in fact, gave us the confidence that yes, we can do it together. I remember once with Yogi, we started working, we are thinking of doing something together. And he said, everybody else is saying that why these two guys, how come these two guys collaborate? They are of the same age and at the same level. So we had a lot of development detectors and instrumentation. I will not go through that. And then we are emboldened because of this collaboration work, and we started having confidence of making things ourselves for doing research at the front end of the nuclear physics, cutting edge. Could get to go to the outside and work in the mega sciences in the foreign situation. This the relativistic wave and collisions were pioneered by the group at VCC, especially with Vigasina. We must give him credit for that. And not only just before that, only collaboration was going on from TIFR. The CERN collaboration was TIFR high energy physics group and particle physics group. This for the heavier, and the nuclear physics group started collaborating from that time onwards. A lot of people were gathered together. Many institutions in the country worked together for this work, and they first joined into. Yogi is there. He is one of the guys who was the guinea pig for the experiment, and he is going to CERN and for the experiment. Then later on in the STAR, and then STAR detector systems where he contributed, which led to the ALICE program, where again the Indian contributions are there. And they started the quark-gluon plasma, which is where we have seen, I just told you about, and they are now today continuing to explore the QCD diagram, the quantum chromodynamic phase diagram, how this liquid phase gas transition takes place or not properly. So that continues, and we have new facilities coming up. Spoken cyclotron has just started another instrument which has even joined a facility for the astrophysics. Purely at very low energies at Science Institute has started operating, and a high current injector for going into the LINAC in IUSC. High current injector has started operating. It has to be injected. That's remaining, so it should be done in a year's time. And then we have international collaborations with GSI Fairway contributing, GINR for superheavy nuclei, at LHC CERN for QCD and CERN more. With Fermilab, we had a collaboration for accelerator building as well as for neutron neutrinos. And this accelerator building is important because that has given us a proton accelerator project of DAE, which is where all the people are contributing, which will produce medical isotopes, proton therapy, and nuclear physics at very high energy, and transmutation of physics, fission products as well. and some free electron lasers are at IUAC. And the future is projected in the mega science mission. Yeah. Just to show you, and I will not speak about this, the spin-offs of this nuclear fixed pure activity, medical cyclotron, Dr. Mohanty talked about, produced isotopes. Now we have, BCC has a program of 18 MeV cyclotron, indigenous, which will produce the isotopes. Then we have electron DNACs from Samir. They have supplied some of them to the hospitals. The 6 MeV is already working, some 7 or 8 of them. 15 MeV is near completion, and 30 MeV isotopes also being considered. And then we have the MRI system, which is developed being jointly by IUAC and Samir. And then, of course, medical circulation and accelerated mass spectrometry, where Dr. Naik played a very significant role. He gave us funding for IUAC for the Earth Science, from the Earth Sciences Ministry, to have the radiocarbon dating lab. And I must say that this is one of the finest labs in the world. It's one of the 5 major labs which are in the validation chain for the carbon-14 standardization. And we are producing now more than 2,000 samples every year. And yeah, I think I remember today you telling me that it costs $700 for sending the samples abroad. So I think we have all that money which you are given in the IUAC has been repaid back. Thank you very much.
Thank you, Professor. Time is already over, but still I would like to give 1 or 2 time for 2 minutes to ask very short questions and brief answers. 2. Yes? Quickly, please. Yeah. Well, I have a question. What do you think, after hearing the wonderful lecture of Professor Mohanty, is there a lot of scope for nuclear research in the country, particularly with reference to his vision with respect to development of micro and mini reactors?
Yes, well, this is not my field as such, was the energy reactor division, but the reactor work. But I think, yes, certainly there is a scope for that, and already they have a program. I think the program is very well worked out. As he said, this three-stage theme of vision of Tata, which is being converted into reality today. It's gone to the 2nd stage, and 3rd stage should be there. In fact, I know that BRC already, Advanced Heavy Water Reactor already has a plan that I have, has already ingredients of thorium being put in that, so that it's already there. So only I wish that things speed up. That's all I would say. I think now the reason why I'm saying speed up is that India's goal is 0 carbon by 2070. So that's only not too much, 4.5 decades left. These technologies take decades to mature. We all know that any new technology is not easy. I mean, we have learned the hard way, but it is true for any new technology. Any technology takes time, especially the difficult technologies take 10, 20 years to mature. So when you go into the thorium mode, it will take at least a couple of decades. But I wish it can be speeded up, because there's not enough time to go to that 0 carbon thing. And in fact, we have to have, for 0 carbon, nuclear is a must. It has to play a very significant role because of base load. Base load is taken today by fossil fuels. Nothing more renewables can take care of the base load. So base load has to be taken care of by the fossil fuels or nuclear. And we know what is the consequence of having fossil fuels. Many more deaths, millions of people will die before we get any problem with nuclear, really speaking. So that's
okay. Thank you for your wonderful coverage of the program in the country.
Just one
yeah.
comment.
Please.
Yes. I think there is a lot of scope of nuclear phases contributing to the nuclear data production for our reactor designs. Because very accurate data, apparently we have to borrow from international. But if we can do a data production, very accurate one, large variety of data. That will be very helpful. You remember at Microtron Center,
Yeah.
we had moved this project to install an electron accelerator for accurate data production, but somehow it didn't work out.
In fact, we could do some photo fusion studies also using the electron accelerator there and study nuclear structure at very low excited states which could not be studied with neutron fusion. Okay, thank you. With this, I thank Professor Amit Roy for a wonderful coverage of the talk and the program in the country. And I congratulate Professor V.S. Ramamurthy, Dr. Sailesh Nayak and Dr. Dinesh Srivastava for organizing this very important event commemorating the centenary celebration of Dr. the great legend, father of the atomic energy program in the country in the true sense, Dr. Raja Ramanna. Thank you very much.
Professor Roy's talk was so engrossing that Professor Siddhapaji told me I don't want to stop Amitji, but what to do? I said that, sir, we have to think like clerks, that we have to cut it. So all the times that exceeds we will penalize from the tea. So we will sharply come back at 11:30, and in the next session it will start with Professor R.K. Chaudhary, and the session will be chaired by Dr. R.K. Bhandari. Of course, I will announce it that time once more. So let us break for the tea and come back sharp to start at 11:30. And I request all the eminent guests who have boarding passes and the cab bills with them, who have been intimated earlier, please submit it slowly to our this registration desk. We are collecting all of them for processing of reimbursements. Thank you very much.
बैठता हूँ महीने में एक आधा पेज देख के मुश्किल है।
Will be chaired by Dr. Rakesh Kumar Bhandari, who was a former director of VCC Kolkata. He is Dr. Bhandari is an internationally renowned accelerator physicist and major contributor to the construction and commissioning of variable energy cyclotron in Kolkata, and he was the project director for the construction, installation and commissioning of superconducting cyclotron, and also he is a member of the FAIR Council. So I warmly invite Dr. Bhandari to come out to the stage and take the seat there And Dr. Bhandari will introduce Dr. Chaudhary shortly.
Namaskar. Before I start the session, I'd like to say a few words about our little association with Dr. Ramanna. It's of course an honor to be a small part of this very marvelous and cute event. And I would like to thank the Ideator, Rudrodip, and the organizers for making it possible for me to be part of this event. My memories go back about 55 years from now, when we were constructing the variable energy cyclotron at Kolkata. It's fondly called the WEC, and I can claim that this was one of the dream projects of Dr. Ramanna, because in 1964 it was decided in the Atomic Energy Commission at the initiative of Dr. Ramanna that WEC would be constructed indigenously and a Bellatron can be procured. Well, he wanted the nuclear physics research to be raised to a very high level, a kind of quantum jump to be taken by the Indian scientists and to be at par with the rest of the world. So it was a big leap as far as the accelerator technology is concerned to take the decision to build the variable energy cyclotron, a huge machine, 280 tons magnet, to be built indigenously in the country. Dr. Amit Roy has given a little history of the accelerator development, and you can see that construction of WEC was a quantum jump in the accelerator technology. From the biggest one was 5.5 MeV Vendigram. And he wanted, as I said, to be constructed indigenously, Dr. Ramanna. And I consider 4 of us, 2 physicists and 2 engineers, very lucky and privileged people who have joined this project, the first lot from the training school. Once again, the creation of Dr. Ramanna. And since we were very young, so we used to in fact fight with each other who will go to receive Dr. Ramanna from the airport to bring him to WEC, because we used to get plenty of time, about an hour, to discuss with him the things and try to impress upon him about our little accelerator knowledge. And he was a regular visitor to WEC in Bombay first, in BARC, and then at the WEC site when the building had been constructed. Well, in fact, while the WEC was in the mid of its construction, I would say 73, 74, he started inspiring the WEC team to accelerators and the nuclear physicists to start thinking about the next facility. Because when we have constructed WEC, then what happens? Because the nuclear physics was moving at a very, very fast pace in the rest of the world. In fact, the heavy ion physics was the kind of fashion for those days, and machines had just started coming, like Super High-Lec in Berkeley. So in fact, some of us went to Super High-Lec, that is the initiative. But anyway, a lot of discussions took place, and the whole thing gathered momentum. The creation of a new accelerator facility under Department of Atomic Energy, it took off. In fact, there was a big meeting. But it so happened is the whole thing was started by the nuclear physics community about the new accelerator, but it was hijacked by the material scientists, because ultimately it was decided to build synchrotron radiation sources as the next accelerator facilities. Well, anyway, that was a very wonderful and very nice decision. Of course, one can see that today. And in fact, for the nuclear phases, it turned out to be ultimately the superconducting cyclone, which took a lot of time to construct. And not really construct. Construction didn't take much time. Of course, it was a large part was indigenous, but commissioning took time because I think the technology in accelerators, superconducting accelerator, is so compact that the charged particles cannot accept any deviation from the magnetic field, good magnetic field quality. But anyway, so it's now operating and the experiments are going. I would show just quickly just 2 or 3 pictures of where our Dr. Ramanna is seen. This is the construction of WEC building across the canal in 1971. One can see Dr. Ramanna sitting there. He was the chairman of WEC committee, and he used to, that's why he used to come also very regularly. Dr. Divetya is there, PT Professor B.D. Chaudhary is the first one that tried, Professor S.K. Bhattacharya, Ajit Saha, and D.N. Kundu and many other luminaries. Dr. Rajaman, once again at WEC, this is the resonator constructed as Central Workshop PARC. He is interacting with the young people. I can also be seen there. Dr. Divetya is there. And then Dr. Rajaman and Jyoti Basu, the Chief Minister at that time of West Bengal, he visited. The construction had been completed, and well, you can see Dr. Rajaman behind Jyoti Basu because politicians have a habit to take over everything once the things are done. So, okay, with that, I'd like to start the session. And the first speaker is Dr. Rajnikant Chaudhary. Dr. Chaudhary joined VRC in 1971. He received his PhD from Mumbai University in 1979. He had 2 postdoctoral stints at Texas A&M University, USA, 1980 to 82 and 1991 to 92. Dr. Chaudhary headed the fission physics section in VRC during 1998 and 2001. He was director of the Institute of Physics, Bhubaneswar, 2001 to 2006. He was the head of the Nuclear Physics Division, BARC, from 2006 to 2011. Dr. Chaudhary superannuated in 2011 as Outstanding Scientist, and post-retirement, he was inducted as a member of Physics Advisory Committee by DST from 2011 to 2014. Dr. Chaudhary has worked in diverse areas encompassing nuclear fission, heavy ion reactions, fusion, multinucleon transfer, charged particle emission, nuclear level density, etc. Relativistic heavy ion collisions, and he has published over 210 articles in international scientific journals of repute. So, very talented physicist. Let's hear his talk. Dr. Chaudhary,
I warmly request Dr. R.B. Grover and Dr. Aradhana Srivastava also to come to the podium, the stage.
Good morning. I thank Dr. Bhandari to say a few kind words about me. We have heard very elaborate and interesting talks from Dr. Amit Roy, who talked about the overall growth of nuclear physics and accelerated science in the country. Well, this is going to be a little more technical. I hope I will try to make it as simple as possible. And before going to the main talk, I just wanted to pay my tribute to Dr. Ramanna, with whom I joined after passing from the training school in 1970. I joined in 71. After hearing his reputation and the strong physics group that he has been building, I was tempted to join as a young boy and got a lot of patient hearing from him about my growth in nuclear physics. And later on, it continued till later years. The last time I interacted with him was when he was in Bhubaneswar attending a science conference in DAV school. He was so keen to meet students. I took him around and he interacted with them, and even at this time when he was already in the center, holding very important posts, he was still having interest in knowing what is happening in the area of nuclear fission and nuclear physics. He, even after retirement, he had been continuously trying to develop his interest in understanding nuclear decay. In fact, he started putting everything in mathematics to explain the decay properties of nuclear, and it was very nicely presented also when he gave a talk in Nuclear Physics Symposium in Bhubaneswar, University. And he never felt that he is in very high positions when he started talking to people like us, and always had a very encouraging talk with us. So let me pay my tribute to him on this occasion of his centenary, birth centenary celebrations. As everybody knows now, he was responsible in the growth of nuclear physics, especially nuclear fission, since he started joining the atomic energy establishment in Bombay, where Apsara was built in 1956, and he had already started his career in nuclear physics from 1949. So Bhava had put him in charge of running the programs in nuclear physics, and his main interest was to understand nuclear fission, and he had already gathered, when I joined, a number of very bright physicists like Dr. Kapoor, Dr. D.M. Nadkarni, Dr. Ramurthy, Dr. Aditanand, and Dr. Kataria. They were all predecessors to me, and I gained a lot by interacting with all these people. I am just sorry to announce that in July this year, Dr. Nadkarni passed away, and he was so keen to attend this seminar, but we miss him in this occasion. Well, as time flies, we learn a lot, and I will present a little bit about the growth in nuclear fission activities in Bombay. So I will be very specific about what is happening in the campus, Bombay campus, and I may omit certain things which are not related to neutron, because the title says neutron-based nuclear fission research. Well, neutron became a very important tool to study nuclear structure, nuclear properties, and of course, in 1932, when this was discovered, all the experimental techniques were so rudimentary, but you all can see how meticulously the experiments were being done to understand with the rudimentary understanding of nucleus. There were experiments, and alpha source was used to produce neutrons out of beryllium target. Even now we have radium beryllium sources, americium beryllium sources, plutonium beryllium sources. They are actually being used for many applications. Now, with that, the neutron was expected to be generated, and to detect a neutral particle, they had to put a paraffin block with hydrogen-rich material, so that the recoil protons can be detected with a GM counter. So it's a very simple but elegant and very, one can say, very intelligently planned experiment which detected neutrons. And after the neutron was really discovered and one knew how to produce neutrons, it became a very useful tool to study nucleus, and because of this neutrality in the charge, it can be also used to transmute elements. And in this process of transmutation, using actinide nuclei like uranium, fission was accidentally discovered in 1939. So once fission was discovered, it was such a unexpected phenomenon that most of the nuclear physicists, physics-wise, could not accept that. It was a chemistry discovery, and later on, within 2 months, of course, there was a good explanation given by Meitner to explain the phenomenon of nuclear fission by saying that the nucleus is wobbling and goes through a barrier and then undergoes fission. The main thing that attracted worldwide attention in fission was the energy release. Yes, a simple million electron volt or small particle neutron can break a nucleus as strong as uranium with binding energy so large. But the total energy release was also very large, like 200 million electron volt. And it was a mystery how this total energy could be generated by such a tiny particle. So this phenomenon even now attracts a lot of physics interest in order to understand the mechanism of such a phenomenon. Although a lot of things have been understood, but still there is a lot to explain about the behavior of the nucleus in the stages of formation of the compound nucleus, then stretching and going to the stage of breaking, that is called nuclear scission, and then post-fission phenomena. There are 3 stages. One is the pre-scission, at the time of scission, and post-scission. So all these 3 are being still investigated from different angles by nuclear physics community. Now, because neutron, of course, has a lot of other applications like not only nuclear physics, but nuclear energy, nuclear medicine, condensed matter physics, and so on. So neutron is a very important particle for not only nuclear physics, but for basic things, but for applied physics also. And it continues to be a sort of challenge to produce neutrons at a low cost and plenty to be used in various applications. I will also sort of try to say how neutron generations have been done and now how people are still trying to produce neutrons of good quality to be used in experiments. Now, as the Avasara became operational and Dr. Ramanna had actually started working in nuclear fission, Dr. Kapoor had joined at that time, Dr. Nadkarni, Dr. Ramurthy, and so many people had already started working with him. in the early stages, it was of interest to know how neutrons are generated in the fission process, whether they are emitted from the fragments or they are emitted during the pre-fission stage and post-fission stages. So this first experiment, which was very interesting, done at Apsara reactor, which lists the publications also carried out by the researchers at this time, that it was found that mostly it was expected that the neutrons are emitted from excited fission fragments, but the 10% of the neutrons were seen to be isotropically emitted, which means that they were not only not emitted from the accelerated fragments, but from a stationary nucleus at the time of fission. Similarly, gamma rays were also measured how nucleus de-excites in the process, and it was found that a large number of gamma rays are also emitted, which means that each gamma ray taking about 1 angular momentum, 8 to 10 gamma rays are emitted, means nucleus is generating at the time of fission so much angular momentum. Starting with 0 angular momentum or very less angular momentum, how does the angular momentum get generated during the fission process is a study that was being investigated, and now even this nuclear spectroscopy using fission fragments is a very upcoming area, because these fission fragments are the neutron-rich nuclei which are generally not produced in nature. So these are the experimental setups at that time, as we discussed about how to measure the neutrons with respect to the fragment direction. There was in the nuclear reactor at Apsara, there was a beam coming out and then generating the fission fragments. The fission fragments are generated and measured in a novel detector device called back-to-back graded ionization chamber. This became the workhorse of most of the nuclear fission activity at reactors, because it's a gas reactor, it was not suffering any radiation damage, and it is a 4-pi counter so that it captures all the fission fragments and gives good statistics, and also it measures both energy and angle of the fission fragments with respect to the electric field direction. So this kind of device was used in all the reactor experiments, both at Apsara as well as Cyrus, for various studies. This required actually a recording of many parameters like the fission fragment energy, fission fragment angle, and associated particles that are coming out. So for that, fission group became one of the demanding requirements for making multi-channel analyzers and multi-parameter systems. And Dr. Kataria, Dr. Ramurthy were very instrumental in building these multi-parameter systems, which now one can see how the growth has taken place in recording of multi-parameter systems. But at that time it was not so easy. Even we started with 2-parameter system and 3-parameter system and so on. And that was the time when we discovered many new things in the study of nuclear fission. Now, these are the main conclusions of the experiments done at Cyrus and Dhruva, Cyrus and Apsara. After Apsara, when the Cyrus reactor came in around 1963, Apsara experiments were closed down, and so when I joined in 1971, I was put in the study of nuclear fission using the Cyrus reactor, and again same instrument was used, a back-to-back ion chamber, except that the associated particle was different. As we know that fission is mostly a binary reaction where two major fragments are emitted and they carry away a lot of energy and excitation energy. However, it's also important for reactor physics applications that a small number of once in a few hundred fissions, binary fission, there is what is called ternary fission. And ternary fission means that there was some third particle is emitted, which is basically a light charge particle like proton, alpha, deuterium, tritium and so on. And this was important to measure those rare particles because they convey a lot of information about the nuclear breaking at the scission stage. That's how they were emitted during the scission process. And so this process was investigated at CIRUS using the same system, except that the detector that one now uses instead of neutron, a charged particle detector, a semiconductor detector, which at that time, as many of you have heard, we had restriction about import and we were supposed to only use the indigenous detector facilities. So we used to develop semiconductor detectors at in the technical physics division. I think Dr. Sekandraya was involved in that stage, who is now in the audience. So I used to go and bug him to get nuclear detectors, charged particle detectors to do the experiments. And it was very successfully measured, and we could measure the angular distribution of the charged particles, their energy spectra and their yields and various ratio of different type of charged particles like proton, triton and alphas. Alphas are predominant and they actually, I do not know how much it goes into the calculation of the helium production in the nuclear reactors, but it's a significant part of the particles that are released in fission. Similarly, triton is next to alpha particles and proton comes later. So what is interesting is that proton, which is a simple particle, doesn't come out at scission, but mostly clusters come out at scission process, which is like an alpha particle and a triton. They are more dominant than protons, which actually means many, it gives a lot of interesting information about the structure of the nucleus or the neck breaking at the time of breaking, which is a neutron-rich region, and neutrons try to get clustered like in a surface of a nucleus. In scission stage also there is a clustering, and mostly alpha particles come out with a stable cluster, and next to it is a triton. So this lot of dynamics and calculations have been done in order to understand the nuclear fission process using the ternary fission phenomena. As I mentioned that in Apsara the neutron emission was studied, and for the first time it was shown that about 10% is emitted. Neutrons are emitted in the isotopic level, isotopic condition, which means that they are emitted at scission. And this was pursued at CIRUS again in the 1990s, and same reactors, the equipment was used, but it was more detailed study was carried out, and one could see that the neutrons which are coming out isotopically, their yield or the ratio of that isotopic to focused neutrons increases as the kinetic energy of the fragments increase, which means that neutrons mostly become at the time of breaking. If the fragment has lot of kinetic energy, it emits a neutron at the scission stage. So this was a new result which was published in Physical Review. Now, gradually, CIRUS experiments are getting also closed down because of the development in accelerators. As talked earlier, BCC had come up in the 70s, late 70s and 80s. So we had moved to do experiments at VCC, and then in the 90s, Pelletron came up, and our focus was mostly on heavy ion physics. So mostly Cyrus and Apsara experiments were closed down after the last experiments were done in 90s. Now, before that, of course, there was an experiment done with Van de Graaff accelerator with fast neutrons, because it was known that thermal neutrons cause fission in a cold stage, whereas fast neutron fission gives certain energy in the beginning, and the mass distribution changes as we give excitation energy to the nucleus in the starting point. So the asymmetry reduces, but also fast neutrons provide a direction in which the beam is coming out. The neutron beam is coming. So therefore one can study the angular distribution or angular correlation of fragments with respect to the neutron beam. And that anisotropy versus mass asymmetry and anisotropy versus kinetic energy was also investigated. We are using 4.7 MeV neutrons produced in Van de Graaff. This was a thesis of Dr. Nadkarni at that time, and it's published. As you see, Dr. Ramanna was the guide of Dr. Nadkarni for these experiments. Okay, now let me digress a little bit from this recent part. I will come back to it later. We, in a chronological way, we have tried to understand neutron production in various situations. As I mentioned, neutron is an important particle, and one should also investigate how to generate particles, neutron in efficient manner, and also under different conditions. We had procured in the 2000, around 2000, a electron cyclotron resonance ECR source which provides very high current particles like protons to heavy ions. So this source was purchased, which gives about 300 keV ions. It's a voltage, acceleration voltage, and one can get protons to uranium. It was actually purchased to use as an injector to the Pelletron. However, because of restrictions in the space at TIR, it was shifted to BIRC, and we started using this for various other needs. This was one experiment which this was an experiment which was done with a metal lattice to see how neutrons can be produced. Deuterium of 100 keV was continuously implanted into the palladium foil, and the palladium foil was 25 micron thick, but the 100 keV deuteriums as the simulation shows that it was going up to 400 nanometer, and it gets piled up as we implant more and more. So therefore, DD reaction takes place in the lattice of the palladium to produce neutrons. DD neutrons, as you know, can give about 2.3 MeV neutrons, and the neutron rate, production rate, is shown as the dots, and the simulation shows a smooth behavior that neutrons should come out because of the growth in the deuterium in the foil. However, fluctuations were seen continuously, and the foil was cooled to liquid nitrogen temperature -80°. It was reaching -80° centigrade to trap the deuterium in that lattice, so that diffusion doesn't take it away. Therefore, it was after simulation was done, it was clear that lattice plays a role in the production of neutrons. And when we subtract the excess neutrons, about 3 into 10 power 5 to 4 into 10 power neutrons come just because of the lattice effect. This is a new phenomenon which was published in 2019, and NASA scientists also have shown already. 2020 they published papers saying that condensed matter effects also do play in nuclear phenomena. So this is still to be investigated, and we are installing this ECR in a new place to carry out these activities in more larger scale. I will go a little fast about recent studies now, what is going on at Bombay about nuclear data, as Ramurthy was pointing out. How do we generate various nuclear cross-sections and data in not only thermal systems but in fast reactor systems, where fast reactors now we are going to come out with ADSs and all that. How these higher energies with the actinide nuclei, how the decay takes place. So this is a result which was recently published about gamma ray spectra, fission gamma ray spectra for different actinides. Uranium, californium, they show structures in the 100 K region, whereas thorium and neptunium do not have any gamma rays in the lower energy range. This is a very new result, and it's not very clear how the nuclear spectroscopy can tell us why gamma rays are not, low energy gamma rays are not being present in some of these nucleides, which is actually happening with uranium and thorium systems. So this is a very important result which has come out recently, and a lot of studies are now being done using the modified accelerator facility, and Bandigraph is now called folded tandem ion accelerator. Well, but this now to continue this work, a gas cell has also been developed so that one can produce neutrons using PT and PD reactions and lithium, P-lithium reactions and so on in a inverse kinematic scale, so that one can focus the neutrons in forward angle directions. This is a gas development which is going on, and a new setup is now coming up, as I mentioned, in a new place which is now called compact accelerator driven neutron source. It is same ECR source coupled to a RFQ, then the DTR, and then the experimental area. There are two stages of development, ECR plus RFQ can go up to 1 to 1.5 MeV per nucleon, and with this a new scheme of using deuterium beam on lithium target gives a very high energy high Q value reaction, which can produce very high energy neutrons up to 15 to 16 MeV, which is a very new feature, and can give very high intense neutron sources at high energies. Now that the only way to produce 15 to 16 MeV neutrons was by DT reaction, which requires radioisotope targets, whereas with lithium on deuterium and lithium target, one can get similar energy range. So this is a simulation that has been done by pulsing the deuterium beam, just like in CERN TOF, one can have a low energy TOF facility, so that one can select by the time scale, one can measure, one can select the energy range of the neutron. So it can go from 1 MeV to 16 MeV by selecting the proper time scale. So this is a new setup that is going to come up in
Would you like to finish now?
Yeah, another 2 slides. This is the one that I talked about, inverse kinematics using lithium beam and proton target, where one can have a focused neutron beam, very high resolution and very highly focused, so that intensity of the neutron will be very large, and measurements can be very accurate because of the low background that this kind of reaction can produce. So this, therefore, let me summarize. We are now upcoming neutron facilities at Bombay, and in fact Bombay is known for reactors and neutron facilities, but high energy neutron facilities, fast neutron facilities are very not existent now. So this development with Dr. Manti, I think, has shown a lot of interest, and of course within 1 or 2 years we'll expect these facilities to be operational. So let me summarize. As I mentioned, that the nuclear fission has been studied, and with neutrons using both accelerators and reactors. Reactors of Apsara and Cyrus have been used extensively. Bandigraph was used for fast neutrons. Now Portia is being used with fast neutrons, and new developments and target developments are being carried out. And therefore this activity will pick up as we develop more and more facilities in the near future. Thank you very much.
Thank you very much, Dr. Chowdhury, for taking us back into the wonderful history of the illustrious fusion group of PRC and future directions. We have time for a couple of questions. Please.
The analysis is in progress.
Yeah, this is an idea that is there. We are testing it in Portia, but mostly it will be done with the ECR source, where high energy neutron beams can be generated, and it is a continuous spectrum. So in order to select the energy, one has to pulse the ECR source and then select with respect to the time the neutron energy. So this is the setup that is being set up.
So this is done at TFR. We have done at TFR. We have made the setup and all these things.
Yeah.
Okay. Yeah, Dr. Then.
These studies on the fusion embedded of neutrons embedded in lattice, are they still being pursued, or they are stopped?
Yes. So as I mentioned, after this first experiment at with the ECR source, we have got a new location, so that's being shifted there. And within, I think, next 6 to 8 months, the source will be operational, and we will be doing these experiments in a more controlled manner, and more beam time will be given, because when it was at Bandigraph, we used to get only once in a 6 months or 8 months time, because it was run in the same accelerator hub. Now with the new space that is coming up, this condensed effect or neutron production will be very one of the key areas of investigations. And not only with palladium, but other targets you would like to see, titanium and so on. And
We now go to the next speaker of the session, Dr. Ravi Bhushan Grover. Grover साहब आपको कौन नहीं जानता? But I still, for the sake of records, I will read it out. Dr. Ravi Grover is a member of the Atomic Energy Commission and chairman of the Board of Research in Nuclear Sciences. He graduated from Delhi College of Engineering, Delhi University, and received a PhD degree from the Indian Institute of Science. Dr. Grover was president of the Indian Society of Heat and Mass Transfer during 1930 to 2010 to 2013. He worked in the Bhabha Atomic Research Center, the Secretariat of Department of Atomic Energy, and Homi Bhabha National Institute. Positions held by him include Director Knowledge Management Group, BARC, Director Strategic Planning Group, DAE, Principal Advisor, DAE, Director and Vice Chancellor of the HBNI DAE Homi Bhabha Chair. Working in BARC, he specialized in nuclear reactor, thermal hydraulics, process design, and safety analysis. He participated in negotiations with other countries and international agencies leading to resumption of international civil nuclear trade. Very important job. He played a very significant role in conceptualizing and establishing HBNI, that's what we will hear today. And concurrent with other responsibilities, he was founder director and vice chancellor from 2005 to 2016. Dr. Grover was conferred with a Padma Shri in 2014. He is a fellow of Indian National Academy of Engineering, the Maharashtra Academy of Sciences, and the World Academy of Art and Science. Dr. Grover, please.
Thank you, Dr. Bhandari. Well, I think looking at the watch, time is running out, but I will take my half an hour or 25 minutes. Many of you have worked in the same field as Dr. Ramanna. I interacted with Dr. Ramanna in a different way. It was an interaction on a couple of occasions. The first was in 1983. I had attended a course on probabilistic safety analysis in Argonne National Lab, USA, and when I returned from that, Dr. Ramanna called me to his office in OIC and wanted to know about this field. And I noticed that when I explained to him the concept of importance factors of various systems and the mathematics behind it, he got very much interested in that field. Subsequently, I was working on compact nuclear reactor, to which Dr. Mohanty referred in his talk. In the process of that, there are several meetings where I had the occasion to interact with him. Then later on, around 2000, Dr. Kakotkar, when he became Secretary DAE, constituted a DAE Science Research Council with Dr. Ramanna as the chairman, and I was the secretary of that. So in that process, I attended several meetings with him. Well, I think coming to the topic here today, first of all, I'm happy to see many training school graduates here, many people who are associated with HBNI in various ways. There must have been a cabinet note on this subject, which I have not been able to locate. Maybe I have to work hard on this. So I'm relying mostly on articulation by about it in various, in the form of papers, the form of memoirs. After Apsara became operational in 1956, this idea of training school must have come up, and Dr. Darshanacharya writes about it in Current Science, saying that soon after this landmark achievement, Bhabha started an activity which has proved to be the most important foundational activity for the DAE, and tasked for implementing this activity was given to Dr. Raja Ramanna, then a young man of 32. I think many of you must have read the book by Dr. Venkatraman. He writes that in a sense it was like recruitment to the prestigious Indian Administrative Service, except that unlike the case of IAS, the recruitment here was via interviews by expert committees rather than via written examinations. Bhabha also campaigned, and I think this is a very important thing he writes here, also campaigned hard so that his trainees get reasonable salaries comparable to those offered in the IAS, besides similar promotion opportunities. Needless to say, all this was far from easy. Then again, Dasnacharya again wrote about it in the souvenir, which was issued by Training School in 2017. Training School, nurtured initially by Raja Ramanna, has completely justified the faith reposed in it. In the same event, Dr. Hariharan, who is again from first batch, he says 60 years ago, we, the alumni of the first batch, were uniquely initiated to the realm of science and technology in the training school. I am proud to say that it was also a beginning of an eternal connection to nuclear science and engineering, and significant contributions by these very first graduates. Our deepest gratitude for this goes to Dr. Bhabha and Dr. Ramanna. Some more comments. Bhabha himself spoke about it in his speech, Science and Problems of Technology Development, delivered in January 1966. This method of building up our staff does not drain away senior persons from the universities, but on the contrary, gives training, employment and opportunities to young graduates passing out of the universities. Now, I think this sentiment needs to be noted, because later on I will come to something which is opposite to this. Quoting Spenta Vadia, N. Mukunda writes, efforts to partner with the university did not make much progress. Professor Udgaonkar remembers Bhabha's unsuccessful attempts to modernize the university syllabus, after which he decided to start the Atomic Energy Training School. Now again, Venkatraman remarks that one great mistake Bhabha did was to bypass the universities. Now this is the reverse of what Bhabha himself said. So I am trying to provide all comments which I could get. It might have been expedient to do so at that time, but if there had been more strong men in the universities in the early days, they, that is the universities, might not have decayed so fast. Dasnacharya again wrote in Current Science, said there is an opinion that this form of recruitment might be leading to inbreeding. Dasnacharya refers to parallel recruitment now ongoing and writes, a measure of balance between the two types of recruitment without any compromise on quality has to be achieved. I think this is an issue on which I find there is a paradox or dichotomy. On the one hand, universities were reluctant to modernize the syllabus. They were worried about depletion of senior manpower in those earlier days. At the same time, there is a concern of decaying of universities. And if I see most recently, when I say most recently, it was about 20 years back, this kind of sentiment was expressed even in Parliament by Murli Manohar Joshi, who was MHRD minister at that time, when there was some discussion going on with regard to setting up of universities like ACSIR, to which he was opposed, saying that we should not be doing it. I'll come back to this again later. So what has been the outcome of training school? In my opinion, this has been one of the country's most successful personal training programs. Baba's vision that India will not have to look abroad for its experts, but will find them ready at hand, has been realized. Graduates of the training school occupy and have occupied top positions within DAE and also outside DAE. The inbreeding is a complex question, and it has to be examined considering the size of the organization and size of the organization, DAE organization, as Dr. Mohanty said in the beginning, we have 30 more odd institutions which are part of it. It's very large. Is the concept of inbreeding applicable to it? And also we have to know that DAE does provide opportunities to employees for collaboration, for rejuvenation as we proceed further. Can this program be embedded in our elite institutions? Here I think one has to look at the size of the faculty in our elite institutions. I think we see universities abroad, faculty strength in many cases going above 1,000, and we are somewhere around our institutions at 500, 600, no one goes beyond that. We did experiment in the 20 years back with IIT Kanpur, examined their syllabus for nuclear science and engineering, which they were running MTech programs, and found that certain subjects which we routinely teach in training school were simply missing from them. So we requested them that you have to include it. They said, we will include it, but you will have to send faculty from Mumbai for this purpose. And we did it for 2 years, and it was difficult to sustain because they said that for subjects like nuclear, chemical engineering, for example, certain aspects of metallurgy, they just didn't have any faculty to teach. So considering this fact that size of our university is very small, certain disciplines are totally missing from the higher education system in India, I think this particular concept is a good one, and there is an additional issue here. Let me cursor is not going. Okay, it's not going there. Let me. The additional issue is this concept I had to study a lot in the context of setting up of HBNI. When I was going through various documents, one document which I happened to examine was the report of Kothari Commission, which was issued in mid-60s. He clearly says at that time, the center of gravity of the Indian academics lies in the Western world. And later on, more recently I studied a book from German academics Elklana and Kluper. They again reiterate the same thing in 2018. Considering this was perhaps, I do not know whether this was a thought with Dr. Bhabha at that time, this idea that we embed an educational system right in DAE so that center of gravity or the attention of the students relate to the problems of DAE is a very important. So training school that as we see has been successful in my view, and this was a building in South Side 1970 to 2008 where training school operated. My batch to which Dinesh Srivastava and R.K. Chaudhary also belong, were the first one to occupy this building, and 2009 onwards the building moved outside to Anushakti Nagar, that is this building. On here on the ground floor and the first floor is training school, on the second floor is the central office of Homi Bhabha National Institute, and this now becomes a segue for me to move on to Homi Bhabha National Institute. Just a brief introduction to HBNI. It's a deemed to be university accredited by UGC in 2005 and is a grant-in-aid institution of the Department of Atomic Energy, and it nurtures the academic programs of several DA institutions, VRC, IDK, Ramanna Center, VCC, all of you know these institutes. But the last bullet here I want to highlight, and that is Homi Bhabha Cancer Hospital and Mahatma Pandit Madan Mohan Malviya Cancer Center at Varanasi. It has become a part of HBNI. Very recently, it's a part of TMC of DA. This is something, this is a new addition. I think this became a part of HBNI only in the month of June, so you may not be aware of it. And so on, HBNI becomes a sufficiently large system, and this system, the way it is moving, this MD, DM and MCH programs form an integral part of DA now, that is HBNI. Just see the beginning, 2010-11 only 4 seats. All these seats are approved by Medical Council of India, and the way beginning from 2010-11 the strength has grown up. And TMC, which runs this program, really is providing manpower in the area of oncology to the country. Of course, there are seats in BARC also for running MD, that is in the area of nuclear medicine. And the PhD, if you see how many students are graduating for PhD, numbers have steadily grown. We began low number. Prior to this, students were enrolled with the universities which were geographically located near their constituent institutions. Numbers have grown up. Now it is at 278, and I am sure we will cross 300 very soon. This is the most interesting part. In what fashion it has influenced publications. This is overall publication from all the institutions of HBNI, the way they have been growing. And you see here, this is BARC. Publications have been growing, but you see after formation of HBNI, slope has changed. Considerable increase after 2005. Same thing about IPR Gandhinagar. IPR Gandhinagar is a, one can say BARC is an R&D center. It is also influencing grant-aided institutions. Publications remaining steady and then suddenly going up. This is TMC Mumbai. Once they have more students pursuing postgraduate programs, publications increase. Not only contributing to manpower, there is a lot of research going on, and it's a sudden increase because of setting up of HBNI. Now, let me come to the history of how it all came about. There was a discussion in the DA Science Research Council. This meeting was held, I remember, in IPR Gandhinagar under the chairmanship of Dr. Ramanna. Then meeting in discussion in Chairman's Advisory Committee. The steering committee was constituted with Professor Ramanna as the chairman, and all institutions which now form a part of HBNI were individually consulted. I myself did that job, and I know there were debates in various institutions. I do recall the debate in Trombay Council, because at that time I was a member of Trombay Council, and there were both views were expressed, some saying supporting HBNI, some opposing it. Some expressed students, thought of students as burden on the senior scientists, some thought of students as a source of new ideas. But these two camps, after debate, decision was to go ahead with the setting up of HBNI. Finally, after all the processing, the approval of the government was announced by Prime Minister Manmohan Singh when he visited BARC on 4th June 2005, and subsequently went to the process of appointing deans, constituting a standing committee of deans, appointing faculty, and so on and so forth. All this process was done. Now this, earlier I talked about the idea of training school. Now I am coming to the idea of university. MHRD constituted a committee to examine all deemed universities and use 9 parameters for evaluation. We made a presentation on behalf of HBNI in September 2009 to all those parameters, and for the parameter idea of a university, we were given 0 marks. Of course, other parameters, faculties, resources, governance, research output, innovation, etc., there were some marks, but idea of university marks was 0, and the result was HBNI was placed in category B. Now here there was a very, very difficult situation for me personally, because I was spearheading this, and those people who were opposing me in Tombay Council, they started telling me, yes, we told you so. But I talked to members of the review committee, particularly one person who was approachable, and discussed with him. He said that you have gone through the process, you are quoting Dr. Ramanna and this and so, try to read the literature about it, then come back to us. Fine. That set me, it was a big job for me to study the literature, and it is in that process I studied Radhakrishnan report on education, which was published in 1949, Kothari's Commission report, and literature for the setting up of Berlin University, with a lot of dialogue started and so on and so forth. Well, I studied this subject, I still continue to study this subject, and found that there was intense debate in Germany during the first decade of 19th century prior to setting up of Berlin University. There were lectures by Henry Neumann in 1857 in Dublin on the topic idea of a university, and this debate has been continuing ever since then. In our country, this debate started before independence itself, but mainly debate became more focused after Radhakrishnan's report in 1949. Then I located a seminar in 2001 in Hiroshima University, Japan, and that summed up several ideas of a university, and they said several ideas of a university coexist around the world and in any large country. Even in one country there are several ideas of a university. The main thing which I came to know from this is the first mission which was assigned to university was teaching. The mission of research was added during the second half of the 19th century, and this was largely as a result of debate in Germany, which began at the time of setting up of Berlin University. And Humboldt was the person who wrote a memorandum on this particular topic. More recently, 3 to 4 decades back, service to society and industry has been assigned to university. I think many people still consider that dealing with industry is something like walking on the dark side. And this, I have heard this kind of comment even more recently. The idea of the fact that you should have an office of sponsored research, intellectual property rights cells, tech transfer offices, incubation centers, this is just 3 decades old even in advanced countries. And this is how the university concept has evolved. First teaching, then research, and now service to society and industry. This evolution has taken place, and this evolution continues. The emergence of several types of knowledge organization has taken place, and that is what is reflected in the way the idea of a university is evolving. Initially, it was testing laboratories, then came national laboratories. National laboratories were first set up in USA after Second World War. Department of Energy came, and Argonne National Lab and various other labs came up at that time, and now we are moving on to mega science facilities. How to bring these things together? On the one hand, we have universities, on the other hand, we have national laboratories. The first example which I could get was in USA, where they tried to bring together, where they have brought together Jet Propulsion Lab funded by NASA and managed by Caltech. Both Caltech and Jet Propulsion Lab, they stand together. There is a good movement of faculty and scientists between the two. Similarly, Plasma Physics Lab funded by DOE and managed by Princeton University, and Plasma Physics Lab laboratory is located on the campus of Princeton itself. So I was armed with all this knowledge. I first had a discussion with one member of the committee, and then we again was invited to make a second presentation after 3 years. Then it was in 2012, and as a result of all these arguments, HBNI was now placed in category A. From B we moved to A, and after that there has not been any going back. We have gone through 2 cycles of assessment by NAC, CGPA of 3.53 in 2015 and 3.40 in 2021. Good ranking in the INRF framework every year, and the latest ranking, which was announced just about 15-20 days back, as a research institution 6, as a university 16, overall 27. Now there is one parameter which reflects 10% in the overall marking, and that is perception. That is where we are not doing well. Rather, this perception has been criticized a lot. I think recently, yesterday or so, there was an article in the Hindu where several people have made presentation against this. Perception, we are getting big 0, a beginning, and now we are moving to 1, 2, 3. While there are institutions like, I think, IIT Madras, IIT Bengaluru, who get 100%. If we remove that parameter from the ranking categorization, overall rank from 27 will jump to around 15 or 14. It is this kind of difference it is making, because all the institutions are so close to each other. Nature Index,
3 more minutes.
Nature Index that places HBNI very high, but of course this is based only on one dimension, which is publications in select journals, not something to be done. I don't consider that very important, but more important is NIRF ranking. HBNI makes large university infrastructure in DA institutions available for doctoral research. Though we started in 2005, France decided to bring together several institutions, including laboratories and research centers, exactly same concept as HBNI, in all those institutions which are situated in Paris and Saclay, to form what they call as now Paris-Saclay University. It replaced Paris-Sud University on 1st January 2020. Paris-Saclay University has already been ranked high in the world university rankings immediately after it was set up. They have also gone for similar clusters. One cluster which came after Paris-Saclay was the first cluster. Second cluster is Grenoble Alps. All the universities, institutions situated around Grenoble have been clubbed as Grenoble Alps. And second cluster is Aix University in Aix-en-Provence and Marseille University in Marseille. They have been clubbed together to form Aix-Marseille University. And they do have many laboratories like we have in HBNI, ERC, ITCA, similar ways, CEA laboratories forming parts of these clusters. The other clusters include in Japan, Sokandei, which was set up in 1985. This was before us. HBNI in 2005. ACSIR by CSIR set up in 2011. The ACSIR cluster has been expanded to go beyond CSIR laboratories. Now ICMR laboratories and many of DST institutions also are part of it. It has now as many as 82 institutions. These are examples of clustering. So there is one particular aspect. Many of you must have studied the book, classical book, The Structure of Scientific Revolutions by Thomas Kuhn, published in 1962. There is a similar book with regard to engineering, The Nature of Technology, What It Is and How It Evolves, by Brian Arthur, published in 2009. He writes that novel technologies originate by piecing together existing ones and of course by capturing phenomena. Essentially, technologies originate by combinatorial evolution. This is what he explains in detail. Phenomena are simple natural effects and as such exist independently of humans and technology. A technology is phenomenon captured and put to use. Then he goes on to say, I like to think of phenomena as hidden underground, not available until discovered and mined into. Effects near the surface, say that wood rubbed together creates heat and thereby fire, are stumbled upon by accident or causal exploration or casual exploration and are harnessed in the earlier times. Deeper underground are seams such as chemical effects. Some of these are uncovered by early adepts, but their full uncovering requires systematic investigation. Continuing from Brian Arthur, the discovery of the mostly hidden phenomenon such as the quantum effects of nuclear magnetic resonance or tunneling or simulated emissions require accumulation of knowledge and modern techniques to reveal themselves. They require modern methods of discovery and recovery. They require, in other words, modern science. Science not only uses technology, it builds itself from technology. Science builds itself from the instruments, methods, experiments, and conceptual construction it uses. And science without technology would be a weak science. Technology builds from harnessing phenomena largely uncovered by science. Science and technology co-evolve in a symbiotic relationship. So, rationally, for setting up HPNI, it's a vehicle for promoting academic research to develop advanced technologies to meet the needs of the missions assigned to the Department of Atomic Energy. Why I have used the word academic research? Let me just go through it. I use that word academic research. Basically, I think before I say that, let me quote William Shockley, his Nobel lecture in 1956, where he opined that adjectives like pure, applied, unrestricted, fundamental, basic, academic, industrial, practical are being used by some in a derogatory sense. Some use it to belittle practical objectives, while others use them to brush off long-range values of explorations into new areas where useful outcome cannot be foreseen. But this basic applied nomenclature is so deeply embedded in the establishment that it will continue to be. But somehow I prefer to use a very simple categorization: academic research and post-academic research, which was first proposed by Professor Zimmern in his paper in 1996. Both academic research and post-academic research have epistemic and use objectives and outcomes, and many universities now are engaged in both academic and post-academic research. National laboratories have always been doing so, and to progress further for this country, we need both academic research and post-academic research. Paris Hackler, if someone wants to see detail, this one can see in Nature, and this is a quote from the Kothari Commission, first one, and second one is Elkanah and Kluper, where they talk about University of 21st Century. Thank you. And this is for further reading by anyone who is interested. Yes.
Thank you very much, Dr. Grover, taking us back into a wonderful research is required everywhere, science or setting up a university. So we have time for a couple of questions. Yeah, Dr. Dinesh.
Yes.
Can you go back to previous slide?
Which one?
Yeah. No, you had a comment that center of gravity.
Yes,
lies
Kothari
outside
Commission.
India.
This was a quote from Kothari Commission. The center of gravity of Indian academic life is largely outside India.
Can you please elaborate?
I don't have to elaborate it. How many, you see, if you go 20 years back, I used to talk to people working in health sciences. They say that people who work in non-communicable diseases, they find it easier to publish in Western literature. They prefer that. In India, communicable diseases at that time were more important. Non-communicable diseases have become important now. A similar way, I currently try to work in the area of energy studies, and I find everyone is looking to, I first said in 2004-2005 time frame how much energy India will need, and everyone said no, you are estimating you have to consider the fact that India is a tropical country, will not require energy for heating. And my argument used to be, what about air conditioning? No, India is a poor country, air conditioning will not be needed. See, post 2016, because of large scale use of air conditioning, the peak load itself now occurs at 3 p.m., which earlier used to be at 8 p.m. The air conditioning load is, sale of air conditioners is going up at a CAGR of 10%. Cold storage requirement, they are growing up at a CAGR of 20%. So I go back to 2004 when I used to debate this issue with people, everyone trying to quote from Western literature. Look at the ground reality as we move further, the way the load is evolving, it really reflects that we have to look at India. We don't have to look outside. So, health sciences, in the area of physics, perhaps when you are working on quark gluon plasma, this will not be applicable. There, things are of a different nature. But when you work on problems where there is an intertwining of science and technology with society, you have to look at Indian society. Yes, Professor Amit Roy.
I just want to add to your comment that you were saying that even in coagulant plasma or any other basic sciences, but we do, our fashions are dictated by the West, even in basic physics.
Yes,
so the emotional
that is right. But certain things like fundamentals of physics, they will remain universal, they will not change. But science and technology as with society means we have to look at Indian society.
As Ajit just commented on the side, that the emotional center of gravity remains in the West.
Yeah.
For most of our research.
That's a very bad thing for us culturally.
I think this is a very good discussion point at lunch. We have plenty of time.
I think this report in 1966, way back he has written, and this book by the University of 21st Century, this I read recently after my dealing with that MHRD committee was over, but I continue to look at this subject. This again is revealing. And after this I read a book by Dharampal, The Beautiful Tree, where he has tried to, this Dharampal is a person who has read archival research with regard to education system as it was before Britishers came in India. How systematically they spoiled it, and this is, he's quoting documentation produced by Britishers themselves. He spent maybe years together in the India Archives Library in London, and then he gives 300 pages of those books produces. In 100 pages he gives a summary on all these things. That book is worth reading.
Okay. Dr. Jan, lunch time में ले लेंगे? Yeah. बहुत देरी हो रही है. If it is very sharp, quick one.
Well, just a very thought-provoking lecture, and many things I came to know about SBNI through your lecture only. So I have been associated with universities, IITs, private university also. So when you talk about decay of the universities in India, my take is that there are two things. That administrative setup of the Indian universities has not changed since independence. It is rotten. And they don't want to change it. Nobody wants to change it. It is in the clutches of the registrars, deputy registrars, and so many babus. This is where IITs have succeeded, partly. And second thing is funding, of course. State universities are almost finished, except one or two. Whatever remains is in the central universities. So this is one thing that I wanted to comment. Second is about your perception of SBNI. The perception is not there because outsiders simply don't know anything about SBNI. What we feel is that SBNI, DI system has created SBNI for itself so that they can give degrees to their first people and they can they don't have to run to the universities. And that is perfectly okay because going to the universities was very tough. I know that earlier BRC used to give degrees, PhD degrees to Bombay University, and it was not an easy job. So you are kind of insulated and we don't know anything about it.
Here, let me say, only 25% of PhDs coming out of HBNI are employees of DA. 75% are outsiders. Let me make this very clear. Out of 300 numbers, 25% are employees. Not the remaining 75% are students who come for PhD and go back.
So this is something that certainly, I mean, there is no interaction with the SBNI because it is an university. It is basically an university now. So what is the interaction of this university with the other universities?
Oh, I think
I'm sorry. We
can debate this, but I think we have to respect Dr. Bhandari's constraints.
Getting restless. I am sure this discussion can go at lunchtime. Thank you very much for the I'm sorry about the debate. Next speaker is Dr. Aradhana Srivastava. After obtaining a PhD from Mumbai University, she was postdoctoral fellow at IBM Orsay, France, and GSI Darmstadt, and later on 1 year sabbatical at Ganil, France. Presently, she is head of the nuclear reaction section of the nuclear physics division of BAR. She is also professor at HBNI. She is a recipient of Homi Bhabha Science and Technology Award of DAE. She is the General Secretary of IPA, the Indian Physics Association. She has been actively involved in the R&D activities utilizing VRCTI for Electron Linac facility at Mumbai. Her interests are broadly in the area of studying the reaction dynamics with stable and weakly bound nuclei, shell effects in fusion fission reactions, neutrinoless double beta decay. She is a member of drafting group for the Mega Science Vision 2035 document, written on initiative by the Office of Principal Scientific Advisor to the Government of India. Dr. Aradhana Srivastava, please.
Thank you, Dr. Bhandari. Firstly, I would like to thank the organizer to make me a part of this celebration. So in this, I'll be speaking on low energy heavy ion reaction studies in India. And we are very much thankful to Dr. Raja Ramanna. Because of him, I'll be able to give some glimpses of the work done in India. So as we all know, we have heard to Dr. Amit Roy, that Dr. Ramanna was actually responsible for initiating the programs of development of accelerators in India and its utilization for nuclear physics. And as you can see in the picture here, Dr. Ramanna is present in the inauguration day of Van de Graaff accelerator in around 1960s. And he is also present while the installation of K130 cyclotron in Kolkata. And these two facilities were providing protons and accelerator, and they were workhorse for many years. And then came the next leap when BRC TFR Pelletron Linac facility and IUAC Pelletron Linac facilities became available. And I heard from my seniors that he was, Dr. Raja Ramanna was very much instrumental for these facilities also, and he was pushing these proposals. So as it was rightly said, that these heavy ion accelerator facilities, it became possible to do different kind of reactions. And now we are moving from neutron-induced reactions to heavy ion-induced reactions. And then because of these facilities, it became possible to overcome the Coulomb barrier and form different kind of nuclei. And as you can see, these three facilities, these two pelletrons came almost at the same time, and they both got boosted to Linac energies. And VCC also started providing heavy ions from 1998. So main goal of low energy nuclear physics I have listed here. So it was to quench our curiosity why there are only 300 stable nuclei around the nuclear chart. How can we reach nuclei which are away from stability? We form them by making nuclear reactions, and in the process you learn different nuclear properties. So what are the different nuclear reactions? At these low energies around the Coulomb barrier, there is a rich interplay of nuclear reactions and structure. So main reactions along the Coulomb barrier are elastic scattering, inelastic scattering, breakup when the nucleus is weakly bound, transfer of few nucleons, and formation of compound nucleus. So in this present talk I will be covering, it is not possible for me to cover all the good work done in all these three facilities. So I will be, for this reason, selecting only few. So my apologies to those if I have not selected a topic of their interest. So I am just apologizing from the beginning. So in this field of compound nucleus formation and decay, I will be starting with fusion fission dynamics, because this topic is more close to Dr. Ramanna, where he was working. So I start with the early days of studies with heavy ions in this accelerator facility and fusion fission dynamics. And this was like carrying forward the legacy of Dr. Ramanna, and whatever experience was gained with the experiments using the reactors by the Trombay group, it became very handy when the heavy ion accelerators became available. So all the detection and the analysis ideas of measuring fission fragment angular distribution, correlation between mass and kinetic energy, particle multiplicity could be applied to heavy ion reactions. And the heavy ion reactions not only brought the high excitation energy, angular momentum, but then the entrance channel dynamics also became important. Because the composite system of target and projectile not necessarily always will be equilibrated and compound nucleus, there are other processes which are non-compound also became important. And this is where there was a big contribution from the fission group, again carrying forward the legacy of Dr. Ramanna. So the electron was inaugurated in 1989, and 1990 there was a PRL from this group, and this, by measurement of fission fragment angular distribution, it gave a direct experimental signature of fission before the equilibration. So the new non-compound nucleus process, pre-equilibrium fission, when it is mixed with compound nucleus, these kinds of events gave the large anisotropy for certain systems. And then of course there is a concept, there is a BG critical mass asymmetry point when one is on the lower side of this mass asymmetry. Those systems gave a larger anisotropy, so I won't go into detail, but this kind of physics actually, in the beginning, early days of Pelletron, there were many experiments done and many PhDs done, and there were some shell effects were studied, and then also near the Coulomb barrier, the explanation was given for the larger anisotropy observed due to coupling. All this very interesting work were done in the early days. And then I found something very interesting when I was preparing this talk, and then this work was shown by Dr. Chaudhary also, that in the experiment done with thermal neutrons in Apsara, it was already observed that 10% of neutrons, they are not coming from fission fragments, but they are coming before the fission occurs. They are isotropic and they are coming from the compound nucleus, compound system. And it was also proposed at that time for such kind of pre-fission neutrons to occur. They can happen between saddle to fission, but the time delay required will be of the order of 10 to the power minus 19 seconds. So when the heavy ion machines became available, more excitation energy, more neutrons emitted, and then more statistics available. So this problem of whether the fissioning system is like a water or like a honey, viscous like a honey, became more important, and it could be addressed. So by the experiments performed by the same Trombay group, it was found that from the precision neutron multiplicity combined with the theoretical model that include viscosity, yes, indeed this kind of fission delay is possible, and the neutrons can be emitted in the path from right from the formation to the saddle point and till the scission point. Neutrons can be emitted more than they are predicted by the theories of a statistical model. These extra neutrons actually can be used as a clock because of the width associated with the emission. to get the fission time scales. And later when the first stage of LINAC became available, so in Pelletron first time we did the experiment by measuring all the observables, 3 observables, neutrons and charged particles like proton and alpha, and also gamma ray. Using all these observables, we tried to get the fission time scales. And the fission time scales with the heavy ion reactions was found to be around 36 to 41 zeta second. Zeta second is 10 to the power minus 21 second. So now when I come to recent times, the early days we had very few numbers of detectors, standalone detectors, and MCA kind of data acquisition system. But in all the 3 labs, with the time, there were a lot of advancement in detector systems. There were more detectors with high granularity, more efficiency, larger solid angle, and it became possible to do the reactions like coincidence reaction, gated reaction, and then a deeper understanding of different processes could be obtained. For example, these are some detection setups which And with this, with the power of this, even the heavier mass of the nucleus reaction products can be detected. And now, as I said, with this kind of nuclear detection system available, it became possible to do many correlation studies and study things like that. Kinetic energy of the fragments and the mass, they could be measured simultaneously. So I have selected some experiments, some studies. So this study, this is again fission in actinide region. So I'll be covering fission with actinide region, super heavy elements, and the pre-actinide region. So starting with actinide region. So very interesting thing which was done in Pelletron for the first time to observe the super short mode. So fission fragment with the combination of the final fragment, if it is the shell structure, is very important how the mass distribution take place. And when both the fragments they break like a liquid, drop of the liquid, the mass distribution is symmetric. And due to shell effect, if one of the fragment is having shell effect, then the mass distribution will be asymmetric. And this super short mode can be observed in nuclei where the compound system is formed such that the fission fragments are having a tin, which is a doubling magic, 132 tin, as a fission product. And because they are shell closed and they are more spherical, the mass distribution will be more symmetric and the kinetic energy will be high. So this is one of the rare modes which was observed by the coincidence measurement. And this is something very interesting. Experiments done at VCC using the alpha beam. So this was to see the shell effect and the constraining the excitation energy where the shell effect vanishes. So this paper by Dr. Ramamurthy and Kapoor It deals with the shell corrections in level density and fission parameters also. And according to this, shell effects vanishes at around 40 MeV. So this is a very beautiful experiment. It was done with alpha beam, therefore it gives you a low angular momentum, and then the causation and transfer induced fission like events are absent. And as you can see, the measurements of fission fragment mass distribution, one goes from 20 MeV to 64 MeV, so around 37 MeV or so the shell effect vanishes. So this gives a direct evidence of the vanishing of the shell effect, and it proves the whatever was proposed in 1970 in this paper. So the next item I have, the next research paper which I have selected is about multimodal fission. This also deals with shell effects. So this measurement was performed at IUAC using the power of NAND array and MWPC fission to detect the fission. So in this, because of this combination, one could do the mass-gated pre-fission neutron multiplicity measurement, and this is what it is plotted. So what was observed, it was done at several excitation energies. When the measurements are done at low excitation energies like 24 to 32, large nuclei is observed, and the asymmetric, in the correlation part, asymmetric mass distribution. And at higher excitation energy, it is mostly symmetric. So the conclusion drawn by this work is that this is due to, at low excitation energy, the mass distribution is due to low excitation energy after emission of neutrons. It is not the first chance fission. So fission is occurring after emission of one neutron or two neutron. And by the time the excitation energy of the fissioning nucleus has come down, and it is showing the shell effects. While at the higher excitation energy, one could not come to that low excitation energy for shell effect to be apparent. Similarly, in other work, which I'll show next page. So this, the earlier work I showed was for shell effect. Shell effect is very much important to be studied for the super heavy element formation models, because a super heavy element can exist only because of shell effects. So therefore, to understanding of this shell effect for different entrance channels is very important. In case of quasi-fission, shell effect helps the super heavy formation, and quasi-fission acts like a villain. More is the quasi-fission, the less will be the possibility of forming the super heavy elements. Therefore, this also is very important to be studied. So I have listed two work on quasi-fission, one done at IUAC and one done at PECC. So both actually very beautifully form the same compound nucleus and studied various different aspects. Work done at IUAC, the 208 RL was formed by using silicon and titanium kind of projectile on these targets, and then the nuclei was measured. So what is interesting is that this nuclei measurement was also compared with a system which is more asymmetric. So in both the cases which are heavy projectile, the nuclei is larger, but the interesting part is this, that in case of titanium, which is this projectile is higher Z, the nuclei is less. So the conclusion was that in this case, the fast quasi-fission is occurring. Okay. And the second work is from cyclotron VCC, again same compound nucleus formed, and in this case, the theory is that there is a quasi-fission, but the experiment did not see any quasi-fission for both the entrance channel. So the message from this is that a lot is still remaining in the theories to understand the quasi-fission phenomena, and more measurements are required. Now coming to this super heavy element region, and this work was done by VCC group, not in India but in Dubna, but it is really interesting to discuss this result, because we all know that Z equal to 118 has been found by calcium on californium, and going for higher Z will require either higher Z of target or of projectile. Higher than californium is not possible, therefore higher Z of projectile. So now one has to see that if you go for higher Z of projectile, the quasi-fission will increase. So how the time for making the measurement of such reaction or experiments will increase. So this kind of measurement was done not for Z118, but this could be done for lower Z, for example, Z equal to 114. So same compound nucleus for having Z equal to 114 was found using different projectiles from calcium to chromium. And their conclusion was, this experiment was done for around 1 month, that if you require 1 month of time for producing 114 using calcium, with titanium you would require 4 years, and with krypton you will require 25 years. So this kind of study is really important, therefore I showed this. So next I'll come to now nuclear level density, because that also is, okay, before that it is, I give a bird's eye view to mass distribution obtained through a nuclear chart. I showed about fermium, it is the symmetric mass distribution because of tin, and around the actinide region it is asymmetric. And then it was not expected that around the pre-actinide region, for example around 180, the fission fragment mass distribution will be asymmetric. Because fission fragment, if it is symmetric, it will be zirconium 90, which is shell closed, and according to liquid drop also symmetric, liquid drop model also symmetric mass distribution is preferred. So why 180 mercury was asymmetric? This was through beta delay fission. This became another branch of interest of nuclear fission studies in the recent time. So I'll just show 2 measurements in this direction. So this is, in this work it was one tried to see what is driving force in pre-actinide region. So from the measurement done in pelletron and also from the data available in literature, what was found then when the compound nucleus Z is increasing, the Z of the lower fission fragment remains constant. It is showing some kind of stability, and with increasing compound nucleus Z, the higher fission fragment Z goes on increasing. And this role gets reversed when one enters in the actinide region, because the heavier fragment gets locked into another shell stable configuration. So the conclusion from this work is that it is the proton shell which dominates the process of fission fragment through neck and then getting separated into 2. And then in pre-actinide region it is around 35-37, which is actually playing this shell close is playing, this is a deformed shell which was proved later by calculation, is playing the major role. And this is again in the pre-actinide region. The same compound nucleus was formed using the through entrance channel. With the oxygen, in both the cases the mass distribution was found larger than predicted, showing a shell effect. But in case of chlorine projectile, it was found that there is an extra component which is coming from the quasi-fission. And then through a measurement or through a literature data, when it was compiled, it was found that when Z is greater than 17, the quasi-fission becomes important. So all I wanted to say that quasi-fission, understanding this process right from pre-actinide to actinide will be very important for any understanding of the fission and for super heavy element region as a whole. Now coming to another important parameters which is related to decay of compound nucleus is shell effect in level density. So this was again predicted by the same paper by the same authors in 1970 on the nuclear level density, and a measurement was performed by a novel technique, because populating 208 lead is not easy. So in this experiment by Triton 7 lithium was the beam, and then Triton capture was used to populate lead, and another compound nucleus was also populated which was away from lead, and it was clearly seen that the shell effect as predicted by this paper around 13 MeV, when it was applied to lead, the level density could be explained. So this also confirmed, and the melting of shell effect from low energy to high energy. And using the same setup, other experiments were also performed on nuclear level densities to check for the collective enhancement, and this is very useful in neutron capture cross section for astrophysics research. And in VECC also several measurements have been done and are being done now to study different aspect of nuclear level density in terms of collectivity, in terms of isospin, in terms of pairing phase transition, and there are many interesting results on this. And as I said before, that level density is very important parameter for astrophysics, for reactors, for understanding the fusion dynamics, etc. Now coming to for nuclear formation part. So in the early 90s, it was very interesting to study the formation of fusion around the barrier to reach the super heavy elements and nuclear physics, astrophysics. But it was found that fusion is very much enhanced as compared to one-dimensional barrier penetration, and it was explained in terms of the other degree of freedom when you introduce that nucleus is not an inert spherical object, but it can have a deformation, it can have collective vibration, transfer of the nucleons, etc. And this kind of physics has been very, very extensively studied in Peloton and also in IUAC using HERA and in Peloton using INVIM on online kind of experiments to study different aspects like shell effect, transfer Q values, etc. The papers are so many that I can just say what is the final conclusion, but I think Dr. Sinha maybe will be covering this. So another interesting thing which in early century, which was of 2002, this was very challenging measurements of low cross section just below the barrier, and it was found that this cross section, this fusion probability is hindered. And there were two models. One was that called the sudden model, where two nuclei coming close to each other, the density overlap, and then poly-exclusion principle, and that will include some repulsive, and therefore the inner part of the fusion barrier will be shallow, and because of this hindrance in fusion is occurring. And there was a complementary model, adiabatic model. This actually I am mentioning because this is just a reverse of fission models. Their net degree to separation of nuclei, and this model takes the same kind of ideas, that two nuclei coming together, forming the neck and then fusing. So these are the two models proposed to explain this. And because the cross sections in this region is like a nanoband, there are very few, and all over the world the kind of tools used were like separator, recoil separator, magnetic spectrometer, and in Peloton we used a very simple idea of making the coincidence between offline gamma and X-ray, and we could measure up to 20 nanoband of cross section. And what we found from
to finish in 3 minutes
possible. So we could see that adiabatic model is more appropriate, and then the fusion will not be hindered because the cross section is falling for the astrophysical reaction rates, and the future plan is using the phenon. And then the next branch was fusion with weakly bound nuclei. Here also we did a lot of measurement in Trombe and in other laboratories also. It was to see how the low breakup threshold of weakly bound nuclei affect the other reaction channels like fusion, and it was observed that the fusion is enhanced below the barrier and suppressed above the barrier. And once you have RIB, there are other degrees of freedom also, like extended shape and then isospin, large isospin asymmetry, and there are very few measurements here, and then the expectation is not going as per theoretical predictions, because for 8 helium it was predicted very high fusion enhancement, but it was found that it is more neutron transfer which is dominating. So more such measurements are required. And then there were some other measurements also, whether the weakly bound nuclei, it is one-step process of, for example, 7 lithium, it will directly transfer triton or first break and then triton will be fusing, and these kind of measurements are very important for Trojan horse kind of concept, where for the astrophysics research. So in this case, by using the power of Inga and the charge particle, one could see the coincidence gamma and charge particle and the kinematics, and it was very, in a clean way, showed that the direct triton transfer is important. And then we try to do the cluster structure also. This is a very simple elastic scattering but high precision measurement, and then just by taking the ratio of the symmetric of the partners on the either left and right side, we could show that 8 beryllium is more like 9 beryllium cluster structure is more like 8 beryllium plus neutron and not like alpha plus 5 helium. And this is something very interesting which was done in our lab to study the 8 beryllium highly deformed cluster structure just by measuring the electromagnetic transition. It was very challenging experiment, and then the interesting part is that by such measurement you show that the 8 beryllium is indeed deformed and it is rotating. And this is the tiniest rotor one would say in the so far known, because normal is 5 centimeter and the size of this rotor you can see is in Fermi. So now the next step would be the future. So I covered the past and then the recent, and the future would be to go for the nuclei far away from the stability, and there are so many excitements waiting there from performing different kind of experiments like elastic scattering, transfer. One can study the different aspect of nuclei which are far away from the stability, and also you can see the very fundamental problems of the pairing properties and dynamic effect of NP pairing, and then also it could be a one way to make the super heavy element, because that has to be neutron rich and we have to start with neutron rich projectiles. So one such facilities which we know is coming up in Nanurib VECC, and in Vizag also we are planning to have another such facility using the power of in this Vizag complex electron LINAC and the proton 40 MeV LINAC is being planned. 40 MeV is a part of ADSS, and using them as a driver, fission fragments neutron rich will be formed, and in this same post accelerator can also be used to produce the stable beam, high intensity, high Z, and they can be used for super heavy element research. So this also is like a futuristic and something of the current interest. And then this also this proposal is going quite ahead. So now I would like to go a little bit flashback after showing the future, because these slides have been sent to me by Dr. Kailash. So I'll just quickly show that, and he has just requested me to just flash these slides. So in this, he's just mentioning some experiments which were done by Dr. Ramanna using the 1 million volt cascade generator, and the kind of experiment was mainly inelastic scattering, and then 5.5 MeV Vandigraph, what kind of experiments were done, and then he gives a list of elastic scattering and the isobaric analog state kind of a study. And this is a picture which he has shown from Vandigraph, and this is some interesting spectra showing the isobaric analog state, this kind of measurement done using the proton beam at Vandigraph. And then this is some optical model potential. This was also one of the very strong activity which was going in Vandigraph using the proton beam. And then this nuclear data activity, which he told me that I should tell the audience that this was initiated by Dr. Ramanna and Professor Tibetia, and then they actually coordinated to collect the data from reactors and accelerator and coordinate with the IAEA. So this is all from that part, and then with this I conclude.
Thank you very much, Dr. Aradhana, for a wonderful account of the experiments done using Indian facilities, and very interesting. One request, since there is so much of work done and so much work can be done, there is a request to Chairman Atomic Energy Commission to grant some more accelerator facilities in the country. Not very big ones, small ones, cute ones, where the students can work. The IUAC waiting time for an experiment is 3 to 4 years. Okay, we can have some questions.
You can come here and respond to
Okay, no questions? So let's thank Dr. Srivastava once again.
having lunch in the green room. My students and I will guide you to the green room. Because we are breaking at about 1:30, we will resume at 2:20. There will be 3 talks between 2:20 and 3:35. Because of the already overrun, we will cut down 5 minutes, so 25 minutes each talk. And then we will see that if very interesting things come up, so of course we are not going to stop somebody abruptly. Then 3:35 to 4 is the planned tea. Maybe we need to steal some time from the tea. Then 3 talks further will be from 4 to 5:15, again 25 minutes each. After that, we will roll out and see that how the time goes. So please let us proceed towards the last.
Now there are many students in Europe who are saying that we are not going to participate in
and we probably had a chat for almost 40 minutes having breakfast, discussing. He kept talking about various things. So that was the closest interaction that I had with him. He was a very charming personality. I have heard him playing piano on this hall itself in 2004. He was a pianist player, and there was a conference here. So Dr. Ramanna was quite gracious to give his performance here, the solo performance of piano. So I pay my tributes to him with these words, and let us start the technical session. We had some very talented Indian researchers with us, and of course a very experienced person also with us. So first of all, I will invite Dr. Srivastava Khan, who is a scientist at BCC Kolkata since 2005. He received his PhD in 2012 from HBNI. Then he went to the Oak Ridge National Lab, USA for postdoctoral research on nuclear density functional theory and its applications in nuclear dynamics. His primary research interest involves the theoretical investigation of the collective dynamics in heavy and super heavy nuclei, using state-of-the-art nuclear many-body theories such as nuclear density functional theories and stochastic Langevin dynamics. He has published several journal papers and review articles. He developed computer codes for nuclear fusion and fission dynamics, which are widely used by researchers for data analysis. So Dr. Srivastava Khan, 20 plus 5 minutes.
Thank you, sir. First of all, I would like to thank the organizers for giving me the opportunity. So initially my task was to talk on low and intermediate energy nuclear theory research in India, but I could not resist from selecting a topic where Dr. Ramanna worked, and also most importantly it is closely connected to the work I am doing. So that's why I selected the title like this, Low Energy Collective Dynamics in Nuclei. And here collective dynamic means there are three parts: fission dynamics, as well as low energy collective dynamics. But I will mainly cover the nuclear fission dynamics, and I will show how the work is connected with the proposal of Dr. Ramanna. So let me begin with the work of Dr. Ramanna. So he is the person who first proposed the presence of stochasticity in nuclear fission process, and he published several papers on this, and we have Dr. Ramurthy with us. So basically the concept is something like this, that fission can be explained by treating the process as a Markov process in which nucleons are transferred from one side of the fissioning nucleus to the other in a random way governed by the set of probabilities. So basically if we have one deformed nucleus and then we have nucleons in both sides, and these nucleons can be distributed following certain probability so that we can get the final fragments. And since it involves a random process, we get a distribution of fragments, and from there we can predict the fission fragment yield distributions. And this theory actually grossly predict the fission fragment distributions for thermal fission. There are certain fluctuations, local fluctuations, which cannot be explained with this very simplistic theory. And our whole task is to actually predict this fission fragment yield distribution very accurately, and this is the journey of my talk. So after the proposal by Dr. Ramanna, this stochastic dynamics, concept of stochastic dynamics is still there in nuclear fission process, but it is not actually the stochastic dynamics of individual nucleons, it is stochastic dynamics of nuclear shape, and it has been introduced in 1986, and still in present days we use this type of dynamics to get the fission yield distributions. So in a nutshell, we actually calculate the fission potential energy surface using an advanced model, and then on that surface we can perform dynamics, stochastic dynamics using different prescriptions, and finally get certain yield distributions. And this Lyachabar dynamics is one of such dynamics where we first generate the adiabatic liquid drop potential with shell corrections, and then we also need to calculate different inputs like inertia, level density, friction parameters, all these, and then we perform dynamics, we get the yield distribution and other observables like Newton multiplicity and then ER cross section, all of these. So this is a standard picture which presently widely used, and these type of model are also used for global surveys. Like here I have shown one global survey where fission yield distributions are calculated starting from neutron number 100 and then proton number 80 to super heavy region, and certain part of these are actually prediction from this model, and here macroscopic potentials are used. But the problem is that with this type of model we cannot venture into unknown domains where we don't have experimental data because of certain limitations. So one example I have shown here for 256 fermium and 258 fermium, the fission yield distributions are quite compact or maybe symmetric, but this model actually predicts asymmetric distributions. And there are similar examples in higher other isotopes also where this MACNIC model fails. Basically the failure comes from the not from the dynamical side, but mainly because of the interaction we are using, or maybe because of this liquid drop model which is very simplistic picture. So to get and survey like this, our ultimate goal would be to get a good interaction and start from there we should build a theory. So I am going to tell about a predictive framework for this. Now let me start in the beginning. So we know that for any model we first need to select our degrees of freedom. Like if we go to very high energy and we probe quark gluons, then the quark gluons are the degrees of freedom, and even if we in the MeV 300 MeV or of the order of energy, then pions are the degree of freedom. But when we talk about nuclear dynamics, we can still do our best with neutron and proton density distributions rather than considering neutrons and proton individual identity. So this density functional theory is an ideal tool to describe the dynamics in nuclei, and this fission process not only involves dynamics in different stages, it encounters different type of physics like fission isomers, then the dissipative dynamics as well as the non-adiabatic region. So all these phenomena we can explain with the help of standard density functional theory. So I will explain a bit more on this. So this is how the density functional theory is connected with the microscopic pictures. So if we start from the beginning, we have internucleonic interaction. This may be 2-body or 3-body. This can be generated from effective field theories. And from this interaction, we can use standard models like no-core shell model or Green's function Monte Carlo or this couple cluster theory, which actually connects these field theoretic interactions in nuclear physics, and it can generate the ground states as well as some excited state in lighter nuclei. Parallelly, in density functional theory, we have effective interactions, but we can actually connect the output of these interactions with that we get from these ab initio theories, and there is a good overlap between the output of these two theories, and that assures that this density functional theory is really a good starting point to study the collective dynamics. Now after this density functional theory, we have extension of dynamical extension of density functional theory. It involves like generator coordinate method or the time dependent DFT, and using these theories we can generate the fission outputs like fission fragment distributions and other reaction quantities. Now, these DFT actually are widely used for nuclear structure studies. It is also used for generating the global properties of nuclei as well as nuclear dynamics. Now, I will not go into the details of nuclear structure, but rather I will concentrate on this nuclear dynamics as well as what global properties we can generate in connection with the fission process. So these are some examples where this time-dependent density functional theory is used in case of fusion and fission process. So these are basically actual time evolution of the fusion process, where initially we have two separated nuclei and then they overlap and form a nucleus. And these also can be applied in case of fission, and we can generate the fission trajectory, and we can do it in different time steps and generate the whole time evolution process. And this is also this can be applied in case of quasi-fission, where we don't have the complete compound nucleus but it breaks before that. And this video actually showing how the fission is happening depending on the type of interaction we are using, and from there we can actually validate the theory also. But this type of theory, this time-dependent density functional theory, lacks something which is fluctuation, because this is a deterministic process. We end up with a particular fragments rather than having a fragment distribution. So for practical purposes, we cannot really use it unless we have fluctuations in this model. So we need some alternate pathway, and we follow this adiabatic approach where we generate this potential energy surface. Again, we can generate it from macroscopic model, as well as we can generate it using density functional theory, where we actually solve this Hartree-Fock-Bogoliubov equation in an iterative method, and we also constrain it, like for each deformation we have to minimize this functional and get the solution for that minimum energy solution, and in that way we can generate the whole surface. So it involves lot of computations. So if we want to generate the whole surface, it involves lot of computation, and not only that, it depends also on the number of dimensions we are using. Like here I have shown the potential for quadrupole moment, which is similar to elongation, and this octupole moment, which is similar to the mass asymmetry coordinate, but we can have more coordinates depending on our problem. So both DFT and dynamics are time consuming in that sense, because generating subsurface and as well as the whole dynamics on that, but we have done dynamics on this type of surface and we can get the result. But our goal is to use this type of surface for a global application where we can study the nuclei over the whole nuclear chart, and for that we have to compromise somewhere, and along this direction this nucleonic localization function is a lifesaver, because this functional actually gives us some hint of the fragment formation before actual fragmentation of the nucleus. So here I have shown one video which is showing the oxygen-oxygen collision, and this color contour is not really the density, it is the nucleonic localization function which we can derive from different functionals, and it gives the information of how the nucleons are localized in a dynamical framework, not only in static densities. So we can see that here after this 2000 Fermi over C, these red regions are two alpha clusters, and then we have carbon rings here. So these are the this is the after certain time the collision of oxygen-oxygen, and this localization we cannot get from density distribution so vividly, and we can apply this picture in case of fission process. So here these these reddish panels are basically scalar densities, where we have neutron densities as well as proton densities, and these lower panels are nucleonic localization functions, and we can see that this type of function generates some circular structure, and from this structure we can see that there is a similarity of what structure we get in the fragments that are generated quite well before the actual scission. So this type of circular structure we can use to identify the fragments before actual scission occurs. So it can reduce our complexity of calculation. And this localization function we have actually used to identify the fission fragments. Now for that, suppose, so here I have shown one potential surface for 254 fermion, and this surface actually gives us symmetric fission as well as asymmetric fission. And before going to the actual scission, if we consider this nucleonic localization function at a point which is much before the scission, then the structure will look like this. And here we can see that from the localization function we can identify the structure of the fragments. These we call pre-fragments. And apart from these pre-fragments, what we have is the nucleons which are around the neck region. So these structures are driven by the nucleus shell structure, and we conjecture that the shell structure is stabilized well before the scission, and the rest of the dynamics is just the distribution of these neck nucleons rather than any structural change in the pre-fragments. So with this idea, I again come back to the words that Ramanna told, that we can distribute these nucleons among the two fragments using certain probability distribution. And we have actually done this, and we have used the probability governed by the simple liquid drop model without any shell structure, because we assume that the shell structure is stabilized, and we have shown it in other words also that this nuclear shell structure is well stabilized well before the scission. So using liquid drop model, we distribute the neck nucleons and we generate the fragment distribution for several reactions, mainly spontaneous fission and thermal fission. And we can see that this model, which is basically these cyan regions, it has certain uncertainty because of the theoretical modeling, and these red dots are the experimental data. We can see that it can reproduce the data very well, as well as the odd even staggering in the charge distribution. And even for this fermium isotopes, our calculation gives better result compared to this macroscopic microscopic modeling and other models like scission point model. So in general, what we develop actually following the same logic, that it is similar to what Dr. Ramanna conjectured. Now let me proceed a little further. So once we know the distribution, then we can actually use the model to proceed further for multimodal fission. So basically this is a method which we call nudged elastic band method. This method can identify the fission pathway very efficiently, and let me show you the video. So this is basically the calculation in real time, and we can see that even if we start with a different pathway, this nudged elastic band method can give us the minimum action pathway as well as the minimum potential pathway. So basically it is like a stretched string, and then we apply the method of steepest descent, and from there we get this minimum action path as well as minimum potential path. And not only that, if we have different modes, like here we have two different modes which are visible on this artificial potential surface, and one mode is going in this direction, another is in the other direction. So if we select different independent endpoints, even then we can actually end up with the two possible modes after a certain time of convergence. So we can see that all the parts converge to the two final points. So this method can be used to search for different modes in fission dynamics, like on the potential surface, and that is what we have done here. So these are again, so as I told that our aim was to reduce the amount of calculation, but as I told that calculation may increase depending on what are the coordinates we are choosing, and if we want to be more precise, we need to consider more dimensions, and these are the calculations with this octupole moment Q30, this quadrupole moment 20, as well as hexadecapole moment, which gives the neck region, and these are the these nucleonic localization functions which are calculated at the outer turning points. So these pathways are basically the minimum action pathways starting from a nuclear isomer state, and these are calculated using this notch elastic band method. And the beauty of the calculation is that the calculation itself selects the different pathways as well as the modes. So we don't have to control it from outside. The whole calculation is done automated. And we finally get different modes, like these are the modes are called like weakly asymmetric mode, strongly asymmetric mode, compact symmetric modes, and this elongated symmetric modes. And these pathways also we can calculate the fission probabilities along these pathways, and this is the calculation for 258 fermion, and we can rightly get that this compact symmetric mode contributes 79% and weakly asymmetric mode contributes 21%. So this is a first in class calculation where we first time actually calculated the percentage of different modes. So this is the calculation for multimodal fission, and now this whole theory is quite capable of, we can apply this theory model for large scale calculations, and this is one representative calculation for super heavy nuclei also. So these are the predictions, and we found that for this super heavy, which is actually under study in laboratories to form this nucleus, and we found that it only breaks under this asymmetric mode. So these are the predictions. So with this,
5 minutes.
yeah, I am almost done. So what I told is I am now done. So everything can be found in this literature. But what I want to emphasize is that now we have started from with the direction that we want to reduce the computational load, but as I told that if we want to know more details on this subject, we need computation. So for that, what we need is exascale computing facility, and this should be the direction that we should have to proceed further along this direction. So with this, thank you.
Thank you very much, Neelam, for a very, very nice talk. The talk is open for some short questions and finish.
Congratulations, Neelam. Just for the general public, I would like to make one comment.
Generally, have mic.
When Neelam did the fission of plutonium-239, I was very excited because this was one of the first microscopic calculations of fission of plutonium-239.
And I took the preprint from him and gave it to Dr. Kapoor. Dr. Kapoor was very pleased. He said, "Ye man ka kaam hua." Then he said, "Can you ask him to calculate neutron and gamma emission?" I came back and I told him, and Neelam said, "Oh, here it is." He had calculated neutron and gamma emission, and that was one of the rare occasions. Dr. Kapoor was a man of few words, but he was wholeheartedly full of praise for Neelam's work. I thought I will just tell you
this incident.
Yes.
Your previous slide you have shown more results for super heavy.
Yeah. Not audible.
As a demonstration of the model, I have shown some results for super heavy with 100% mode of weakly asymmetric breakup. But we understand generally such system prefers alpha decay than efficient mode. Please your comment on it.
Yeah, basically it is the part of so their alpha decay is more probable than the fission. So it is like when it fissions in asymmetric mode. And not only that, these calculations are done at zero excitation energy. So when super heavy is formed, it has a certain amount of excitation energy, and these actually washed away the shell effect. So finally we may get symmetric fission. So
yes, but
do you have any calculations for prediction of very elongated shape of fission fragments?
yeah, so this is, you can see here. So here I have shown two modes. One is compact symmetric, one is elongated symmetric. So these two modes are basically this is elongated symmetric mode and this is compact symmetric. So both modes are symmetric modes, but they are ending at different Q40, that means different neck radius. So we can, but what we found is that this elongated mode does not contribute for this system, but this may be useful for pre-actinides.
I am talking about the fission fragments, elongated shape of fission fragments.
Well, so basically when this type of modes undergoes fission, those fragments will be elongated fragments.
What is your opinion on younger generation choosing nuclear physics as a career?
Yeah, so this actually, in the perspective of this research, there is a huge career in this field, and what we need actually is what we are lacking is, so this will be a part of computational nuclear physics. Now we need good computing facilities which will enable even university students to access good machines and have good quality research on that. And not only it is now nuclear physics, it is like interdisciplinary physics. So it is combination of nuclear physics, computational physics, as well as contribution from statisticians, because those type of inputs are required in, so it cannot be single nuclear physics, nuclear theory, we cannot say like this, but these are the resources we need, and definitely the career is huge. I mean, this is something new opening, and we can, as I told, that the whole fission, nuclear fission chart can be done with this type of modeling, and I have not covered the other parts, so there are good opportunities also.
Okay, I think we cannot have any more questions now for the time constraint. Thank you, Dr. for excellent talk, and this was a very nice presentation on modern view of modern theoretical understanding of fission. Next speaker is Dr. Rudrodip Sinha. Dr. Sinha is an old friend, and he is nowadays a frequent flyer to Roorkee, but doesn't inform us. Dr. Rudrodip Sinha obtained his PhD in nuclear fission from IIT Kanpur in 1982. He taught for 5 years as a lecturer at Christ Church College, Kanpur. Later he joined as a PDF at Indiana University and then University of Bonn under the prestigious Humboldt Fellowship. He was a senior scientist at IUAC from 1987 to 2000 and built a recoil mass separator as the group leader, which is still working there. This was the first ever facility of its kind in Asia, and advanced heavy ion reaction research was established. later a world-class radioactive ion beam facility for nuclear stoppages along with an RMS-coupled nuclear spin spectrometry facility was also added. Later, Dr. Sinha took charge as Center Director of the Kolkata Center, IUCDAE at that time, which then became Director of UGCDAE CSR in Lahore. He worked successfully in Kolkata toward building a large multi-element gamma ray spectrometer facility, INGA, leading to a nuclear structure program at the national level. Post-retirement, Dr. Sinha joined Pune University as Honorary Adjunct Professor in 2020. Presently, he is working as an Honorary Advisor, Teachers Training with the Bharatiya Shiksha Board at Patanjali Yogpith, Haridwar. Patanjali Yogpith, Haridwar. Okay, yeah, District Haridwar. Good. So okay, you have 15 minutes as you said?
Yes. In the morning.
Okay.
Yeah. Give me a poking. Time starts now. Huh? So I thank the organizers for giving this opportunity, and obviously Professor Ramanna students here for us, most of us, and I only enjoyed his piano once when he played this in Auditorium, I think so. And obviously I had interactions with the next generation of Ramannas, which includes Dr. Kapoor, who was my thesis examiner actually. Dr. Ramamurthy also was along on the experiments, Dr. D. Makhani, Dr. Rajnikant Chaudhary that time, and many others. And both of us, me and my colleague Dr. Sharma, who was a student at that time, were very scared of Dr. Kapoor because we always suspected he will find out a flaw in some argument which you're putting, and our whole thesis will crash down. So that kind of sort of complex we had. Dr. Ramamurthy was very quick always, even now he just asked me a question, what are you doing now? So, so it was very, very sharp questions, and then I had some difficult problem for him, I thought, but he said he solved it in a few seconds and everything was fine. So Professor Mehta was the third person who is part of my thesis gurus, thesis guide gurus and everything, and they actually are very close. And you can see that the research in the universities later benefited a lot by the three of them, and then the camaraderie also in some sense from the three, Dr. Kapoor, Dr. Ramamurthy and Dr. Mehta. The nuclear physics became a very exciting field with the heavy ion accelerators and the experimental facilities which were set up in the 80s and 90s. The founding directors of IUC, I like to also include their names, Dr. Paswar and Dr. Mehta, who played a great role in developing this program in the country at a national level. There has been a strong collaboration of university groups. I have already mentioned Dr. Mehta, Dr. Kapoor and Dr. Ramamurthy is a part of the collaboration, which is sort of a seed. Professor Patna himself is a science institute DA faculty. So I think DAE has also been a major contributing factor in the enhancement of the university research, especially the directions which we have been talked about in the session so far about the nuclear dynamics involving relatively more precise systems. There are two reviews. The most important review is here, Dr. Muralidhar, Dr. Madhavan, and so on, all his, my colleagues in the last stint which I had at the MSc, at IUC, and I'm happy that Dr. Madhavan happens to be here. He is actually the corresponding author of this review. This review was published 2 years back, and it covers extensively the work done at IUSC, and which is most of the university research, except I will also refer to the work done at VCC, huge amount of work, and also experiments have been done in collaboration at the TFR accelerator. So this is a huge journey, and the last 40 years, so many things have been done. I think the publications overall which have come out in hardcore nuclear physics high quality journals ranges 600 or more, and Dr. Madhavan will perhaps help me there. I have downloaded 300, 400 papers to review what Dr. D.K. Srivastava has asked me to do. And this has almost increased my weight by factor or something. So reading so many things has been a little bit difficult. And then of course I had a small review of the INGA activities. That is basically responsible to Dr. Khalid because he forced me to give a small review in 2012, and that also has been there in the symposium proceedings. In the universities, the nuclear physics scenario over the last 35 years, exploited a range of nuclei as an all-around quantum laboratory. And we'll see where the quantum laboratory aspects of the nuclei has been exploited by the nuclear physics research in universities through this. There is a book by R.F. Gaston, and I find that if I read that book, then the entire nuclear physics scenario in the low energy region which we are talking about becomes quite understandable, and I started enjoying the other part of the field, which is the structure part, which has not been yet covered in the talk so far. But a huge amount of university research goes into the structure, nuclear structure, and there the single particle orbitals, how they control the nuclear behavior, the interplay of single particle and collective modes, and the coupling of nuclear states. This kind of a concept which is a quantum concept. When you have two states and there is a coupling interaction, you end up having two different energy states, which are, one of them is a lowered energy and the other is a high energy. And this is a sort of a running concept in most of the interpretations of the physics, including the subbarrier fusion which we will talk about, even the way the deformation driving orbitals concept has been used, all the signature splitting, anything which you talk about, it runs around this 2 by 2 matrix, which is not written here, but it is basically the coupling interaction and the way it lowers the energy, the kind of ground state which you get in nucleus is basically because of this extended use of this phenomenon, the lowering of the orbitals, which is then in a way gives you a ground state in a nucleus, and then you have an extended state which is at this fuel maybe above, and you get the separation between the ground state. So this kind of a concept is basically running through the whole scenario of nuclear physics structures, and the driving engines of nuclear physics university research is of course the vagaries of expertise available in the university system, teaching institutes and the DAE labs and institutes, and plus also the requirement that PhD has to be finished in a reasonable time. So most of the research projects which have been conducted through the university groups also have this underlying requirement. So we have to see it in this perspective. The driving engines which have been driving the nuclear physics research in the universities include many of the facilities like large gamma arrays with special accessories, GDA, INGA, RDM, CPDA, and so on and so forth. Large neutron array, so-called NAND, National Neutron Array. The special scattering chambers, large gas detectors, even the two-dimensional silicon detectors, high-density electronics, advanced data acquisition systems, digital data acquisition systems. In fact, this was the first digital data acquisition system was with Dr. Pauli's lab collaboration, and that way again the university research started. You can give you an example of collaboration at the technology level, where the research has been driven through this kind of technology-driven engines. At the end, I also mentioned the most important thing for us, for me as a personal thing, and my colleague Dr. Madhavan here, who is actually leader for the second part of, as well as he was effectively leader for the first part also. The advanced required mass separators, the HERA and the HIRA, and then later the use of it in terms of the RIB, in-flight RIB system of the country. It's the first in-flight RIB system of the country, which was proposed, developed, and used for experiments. The first section of the university research which has been effectively covered in the talks, the subject-wise that has been covered. I'll just mention some of the experiments which have been done. The hot rotating fissile nuclei and survivability against the major split, directions being towards super heavy element. The HIRA project was what actually approved, and me and Dr. Madhavan, actually Dr. Madhavan made the presentation for the DST for HIRA project. And what impressions I got from Dr. Kapoor, who was actually part of the committee there, that are you going to work towards SHE? And Dr. Kapoor actually said that this is the HIRA, and that's what actually it is. We need, of course, few more ingredients, the accelerator, the higher current, and things like this. So this is still ongoing effort, and on and so forth. So super heavies, and I'll skip this. There's a sea of instability somewhere in here. You're not able to read it properly. So anyway, it just talks about where the shell model or shell connections actually changes the scenario of the nuclei. The entire nuclear chart is an artifact or this expression of the shell correction, in fact, you can say. And the first paper which has been, I am very happy that so many people have already talked about this. This is a citation energy dependence of shell effects on nuclear level densities and fission fragments. Dr. Mumbai, Dr. Kapoor, and Dr. Kataria, 70, this has been talked about. And I'll just show you some papers which have used this. I just mentioned the work from Chandigarh group. I'll perhaps miss some of the groups, and it is not actually meant to be a detailed description of all the activities. I have picked up a few of them. And here it was the use of the spectrometer RMSs at NSC, where they measured the cross-section for ER, the evaporation residues, which are formed in reactions involving fluorine-19 on 3 different isotopes of platinum. And they all lead to compound nucleus where the neutron shell closure occurs. And they expected a better stability against fission, which was not found. And this is the nutshell of this. The shell effects are somehow getting affected either through the collective enhancement, level density enhancement, or some such thing. This is an exploration report. This is one of the work which was done. The second work which I mentioned again it has been mentioned by others in the morning. The interpretation of fission fragment angular distributions in heavy ion fusion reactions. Dr. Mumbai, Dr. Kapoor, PRL again 55. And then, for example, I just mentioned the work here. This is a work from, I'll say it's a UDC or University DA collaboration work done at IUAC, but this was the initial line which I mentioned, that how the DA input has come into the university research in terms of fissile nuclei research. And this one actually talks about the fission fragment anisotropy, which is going anomalous at near barrier and below barrier, and except in 2 mass combinations, which are blue and green, and this apparently has to do with the ratio of the fission barrier height and the temperature. This seems to be interesting. I have just put one of the examples here. And this, of course, involves Dr. R.K. Chaudhary also, Dr. Alok Saxena also, as a collaborator in this publication. This was the Bengaluru group. I feel that this was actually supported by the university, UDCDA consortium at Calcutta Center. This project was, but I am not totally sure of this. So I have just took 2 examples of this. Then I changed a little bit the direction of the research. And I talk about compound nucleus formation in heavy ion, the process of itself, process of compound nucleus formation. And how, for example, there are rivals which compete and deplete this process from actually achieving the goal of forming the compound nucleus. So these are incomplete fusion, pre-equilibrium fusion. I'm using a pre-equilibrium fusion word. Actually, the word is fission. And I somehow thought it is finally this only, which is leading to fission because of the heavier systems. And then there's a quasi-fission. Also, quasi-fusion, I have used the word. it is not fusing completely. So why should I call it fission actually? And the process itself is affected before actually we targeted to form a fusion compound nucleus, but it is not happening. The fast fission actually is not interrupting the compound nucleus fusion process. Compound nucleus is formed but doesn't have a fission barrier. So I have put a cross there. So these are the directions of the work which have occurred. And the first work which will come in the next slide is actually okay. This is the latest publication. I have some limitations of accessing the papers. So I spent a few days at NSC before, as soon as Dr. Ramanna sent me some program with both of you. So I went through all the publications, download, but this is very recent, and somehow I have a research, there's a research group, something which gives you the permission to download papers. This is a 2024 paper from, I will say, a very big group, very good group from Aligarh University. And they have been working for, right from the beginning of the IUSC, and they have actually stuck to their guns of using offline counting, and have done a very elaborate work based on different techniques which have been exploited by them, including the one which was shown in the beginning slide. I show it again, part of it. Now this is as an incomplete fusion, where they have fluorine on thulium-169, and they have picked up from the offline counting 177 tungsten as a residue. And then they found that this is coming through basically 3 different fusion-like processes. One of them is actually complete fusion process, and other 2 are not. The one which is on the red, on the extreme right, is actually a complete fusion process. But for this nucleus of residue, that's a very less dominant process actually.
It's around 15 minutes over.
Okay, sir, fine. So I just quickly skip all this. And so there are examples of this group, and we go to the next one. This is a continuation of the same group. Then we have a very complex experiment done at Nuclear Science Center, where we have actually, this is actually, except the NSC people, it is all DAE people, and it is actually a publication in 2019, where they made, you can see it's a very complex system. This fission fragment detector and charge party detector, coincidence was put, and then the incomplete fusion was picked up by the folding angle distribution institute for each event and things like this. Then there's another, this is a neutron correlation. Again, they have a big neutron array, and many experiments have been done. Again, it is driven by a lot of input from the DAE groups. And there are more possibilities actually which can be further exploited to achieve certain understanding of the process. So this is a complex detector system, and so on and so forth. And this is one of the recent work from university. Again, it is a mass distribution of 3 nuclei, and the shell effects are still there in terms of formation of the fission fragments. This is under publication. I think it has been published now or accepted for publication, 2024. It is again a combination of DAE and the university. I go to the third section of my work, our university work, spin distribution as a probe to investigate the dynamical effects. There are 2 spin spectrometer RMS configurations. The one which is shown here is a HIRA plus RMS. There is also a similar one with the HIRA, where the spin is measured along with the direct detection of the residues. There are 3 observers. I mean, if you look at this here, the big one, the sigma LER is actually measured. Sigma L cap, there are only 2 observable. Either you measure the cross section of sigma ER, or you measure them as a function of L. These are the 2 observables from the nature has given us, and then you try to decipher the information of the remaining through their dependence and the modeling. The components which have been identified here. So this is the way we have been trying to understand this incomplete fission or quasi-fission process competing with the formation of compound nucleus. One of the major work which actually, see, there was a work in 2001 by Bergman, and they showed that there is a certain fraction of incomplete, not incomplete, the pre-equilibrium, another quasi-fission depletion of the compound interest formation process. And they did it with a combination of 3 different beams. A very extensive confirmation of this came where the mass asymmetry has been quite close to each other. And this is a work which was published in 2008. Dr. Mumurthy also is a co-author here. And this actually, I'll say, it should be seen as one of the experiments which establishes for sure in a very independent fashion that how a small change of mass symmetry across perhaps the Boussingault or Bengaluru point changes the scenario of fusion, and you start seeing a 30% depletion of compound interest formation right at systems like this. Oxygen plus tungsten and fluorine plus tantalum. They are forming the same compound interest, and this has been extensive work. And I think Dr. Madhavan actually was fully in charge of this experiment at that time, and it is a beautiful experiment to confirm that how we can use the spin distribution and the cross-section measurement both and confirm a physics phenomena in an unambiguous way. And then there was also an experiment of this kind before, a little bit earlier, where we had measured the spin distribution for fluorine lutetium, and this was more in the direction of looking at how the fission delay affects the process. The neutron yield has been, for example, found to be excess in excess. Gamma ray yield also has been found in excess, and so this is how this was done. This was a good work. Then I'll skip all this. This in-flight adaptive has been already mentioned. We had a good experiment there, and we had the S17 factor with the beryllium. I have already mentioned this. This was, then there's a lot of experiments done in the equilibrium barrier, crossing the equilibrium barrier, and people have measured the mass distribution and the cross sections. I'll skip all this. This is quite detailed actually. And then you have seen the slides where the fusion, submarine fusion enhancements has been interpreted in terms of the channel coupling, and a lot of work has been done in that direction. For example, here. The transfer data also was measured, and that was used in providing a coupling parameter to show the enhancement can be explained by coupling with the channel, with the transfer channel. This is another example of the same thing. I'll skip this. And I just show you here, this is a criticism which Dr. Ramamurthy had long back told us that you people don't talk about what we have done in our country, channel coupling, channel coupling, channel coupling. And this is actually the so-called the energy and spin angular momentum dependent fusion barrier potential, which is actually a PRL from Dr. Mohanty himself and Dr. Ramamurthy. And what I show here is something which we have done, but we have not published this work, where we do a spin and angular momentum dependence of heavy ion fusion potential, but we don't put a priori dependence behavior. We actually go ab initio and actually vary the potential, so we get a proper fitting of the fusion cross section by assuming no a priori assumption about how the dependence of the potential is on the energy and the angular momentum. And this leads to different type of structure sometimes, and we have to understand this properly. In many systems we have tried to fit it, and then we get eccentricity. I take few more minutes and then come to the most important part, which I have not understood, is not my field. This is about the cold rotating excited quantum eigenstates. So this is one of the major work of the universities, which is not initiated through the DA collaboration, I would say. Rather, it has happened that large number of university projects have gone back onto the DA, and they have started doing beautiful work in the study of these cold rotating eigenstates. And instead of getting into so many, I'll just show you slides. I'll stop at the most important slide in my view presently, which I am sure, see the quantum, a classical top rotates about the axis of symmetry but not the quantum top and things like this. And they want to show rotation of nuclei about various axes where symmetry is not there and things like this. A lot of work has been done. In fact, I think 200, 300 publications of very high level. Dr. Jag himself is one of the major contributors in this field through various publications. Of course, was also making indicia in magnetic rotation and anti-magnetic rotation and so on and so on. So I'll skip all this. This is only thing to point out this small picture here. The deformed bands were known in 1951 except alpha decay itself. So we know that the deformed bands exist, but and this is the Inga collaboration. I borrowed this slide from Dr. Palit's talk, which he didn't block in the internet somehow, so I could download. And this is pictures of various things. This is the thing which I prepared. There are about 17 nuclei which were studied in 2012 in various mass regions, weakly deformed and strongly deformed regions. And this actually was summary of the existing Inga-based nuclear spectroscopy work in India that time. And the weakly deformed regions is the region where you see a lot of instabilities, and you can actually build up your theory and then find out whether it's a magnetic rotation or the tilted axis calculation based, the wobbling mode or the chiral modes, and then all other vibrations. And at IUSC and IS Nuclear Science Center, we also use something called aerogel. Many people will not know what is aerogel, perhaps not so commonly talked about. We know about other things, but aerogel is actually, if I show you aerogel, it will look like a cloud to you. It's a solid cloud. It has a density which is about 1/50 of a solid material. One of the lightest material is actually, not one, the lightest material is aerogel, a solid material. We use it for measuring the Doppler shift analysis, attenuation method analysis using this. This is actually Dr. Dugre's work, but we have not yet published. He actually manages a lot of things, and then I think we will go further in this. And this is all the little bit of theory. I'll skip all this, I'll stop. There is a lot of work at isomers. Isomers are difficult to study because if you use a required separator, they become easier. And this is one of the work where, again, it's a DAE university collaboration using the HIRA, and I just bring it out because this is where we have the nuclear physics, the structure nuclear physics, high-speed spectroscopy structure has been implanted into DAE now very well. We have a VCC group of Gopal 30, and then we also have a few others at the DAE, including Dr. Vishwas, who has resigned now. Oh, who was superannuated, sorry. Yeah. So I just skip all this, and the last one I'm coming. These are other works which we did here. Yeah. Yeah. Yeah, this is the work which I just want to show at the end of my. This is actually a latest physical review letters from the work done at VECC using INGA and a 20 neon beam published in 2020, I think. So you can see the participants in this. It runs across the universities and the DAE, and it is actually a very good expression of the neon beam, which is only exclusively available only at VECC, and it will be only available at VECC for long time. Neon cannot be produced, any of the tandem etc. And they have, this group has made very good use of this. They have observed the first ever multiple transverse wobbling bands and this and that and so on. I have gone through all this, but I don't have time to show you what I have read about. But to me, it appears to be a very good demonstration of a culminated picture of how we can combine together. And this field has become also a very, very...
you have exceeded your time now.
Yes, done, sir.
Sinatha.
Yeah, thank you. So this was Dr. Your work now. I'm finished. The D. Chaudhary and a lot of work from Dr. Jan's group and many others who have talked about magnetic rotations and various things. And this is the end of it. So this is a publication which is an archive publication, 2024. And I have highlighted some lines. I have put the word heavy iron storage ring. I have marked somewhere that is actually a work at Germany now using this project where we are supposed to be part of the GSI FAIR facility. They have already done this experiment and it's actually in the archive right now. They have measured neutron spectra and the gamma ray yield cross sections without measuring anything, any one of them. They have not measured neutron, there is no detector for neutrons, there is no measurement system for the gamma rays. They measure the particles. PP scattering actually is done in inverse kinematics. There is a ring where the beam is moving around, the heavy iron beam, and it is actually hitting a gas target. And then there is a recoil. Recoil depends upon if it's a neutron which is emitted or a gamma ray emitted. And the same set of magnitude slight modification is used as a recoil mass separator, which is also highlighted here, used as a recoil spectrometer, part of this ring. And I think this is the future of our. In fact, with this, they are able to measure the neutron gamma cross section, I mean the PP prime gamma cross section, N cross sections across the binding energies, across the when they become open to decay, neutron SN or separation energy. Around that they have measured. I don't have the printout of this, but this I think is a possible direction of nuclear physics research for our nation. Funded as one, I have now become at least as if I am the god of the whole world, so I am saying something like this. Funded as one university DA collaboration with a common multi-departmental funding, we make a heavy iron storage ring with excess facilities and all this. I think this could be our future instead of making many accelerators or things like this. So thank you. So thank you very much.
Thank you, Dr. Sinha, for a very nice presentation. I think there is no time for any question-answer session, but if some brief comment or mark is there, somebody feels quite anxious to make any. Yes.
I see very large number of students from the universities. Do you have any data on how many of them are getting jobs in nuclear physics?
I don't have a list right now, but I gave you an example in the beginning itself. The Aligarh University group, for example. There's one behind you. Yeah. I mean, I can actually give you the from memory.
One is not enough.
A very good number. I mean,
one fellow does not.
Lucknow University.
Somewhere.
No. From this group, Aligarh University group alone, Lucknow University, then there's Bareilly College, and 5 or 6 people of then Ranchi, and then he there behind, and many of our own students have gone to Calcutta University, for example. Almost everybody is in a job.
If you are happy, I'm happy.
No, in fact, what I'm trying to say is that whether they are getting beam time or not right now, that would be a good question. Because somebody mentioned, I think Dr. Bhandari mentioned, very thoughtfully he mentioned, that it is taking 4 years for getting a PhD thesis experiment beam time, which was not earlier. So definitely the university groups have expanded and they are stably located, embedded somewhere in universities here and there, and they are driving the force for the work.
University people are very powerful. Let them create one more.
Universities are powerful, but each of them are opposite to each other, so it doesn't work out. The vectors don't add up. This is our problem.
Mr. Ajit, that work with the neon beam at VECC, PRL work, Can it be extended with the superconducting cyclotron because neon beam is available there? Higher
I
energy.
talked about something called cold rotating eigenstates.
Yeah.
Normally you don't want to go much above, let's say 10%, 20%. You need to put some angular momentum. You should be about 10-20% above the barrier. But if you go much above the barrier, then you will not find out the nucleus is formed at all. But yes, I think.
Yeah, it's a multi-institutional.
I think that people are working in this direction. Already Dr. Guri was saying that he is getting some experiment done. Maybe Dr. Guri can tell what is the experiment you're doing at right now. Right now he has come and there is an experiment going on at superconducting cyclotron with him as a there's a collaboration of using.
Okay.
Yeah.
I think we can continue this process, Dr. Sinha. Very pleasant person to talk to, and you can keep on discussing with him after this lecture in the tea. So I invite now Dr. Muhammad Sajjad Akhtar from Aligarh Muslim University. He is a professor there, a particle physicist and theorist. His research primarily focuses on neutrino interactions with matter, hadron physics, and electromagnetic probes. Nearly 30 years of experience, Professor Tata has made significant contribution to the field and published over 80 papers. He has co-authored a comprehensive book on the physics of neutrino interactions, published by Cambridge University Press. He has held various positions abroad at University of Tokyo, University of Valencia, etc., including a stint with 2015 Nobel laureate Professor Kajita to study atmospheric neutrino flux. He is involved in international collaborations like Minerva and Lab and neutrino scattering theory experiment collaboration, SNOMAS collaboration, neutrino panel of international IUPAP. His expertise is further recognized through his membership in the expert panel for the Indian Mega Science Vision Report 2035 that has been released recently, and the DAE's committee overseeing India's contribution to the NDR-DUNE collaboration. Dr. Akhtar, you have 20 plus 5 minutes. I will stop you at 20 minutes.
Thank you. Good afternoon. First, I would like to express my gratitude to the organizers of this seminar for the opportunity to speak on physics with neutrinos, past, present and future on the occasion of birth centenary of esteemed academic legend, Dr. Ramanna. And to cover the past, I have divided it into 3 epochs, starting from the observation of continuous nature of beta decay up to the establishment of V minus A interaction theory. Then the second epoch starts with the development of accelerators for the neutrino beam and also the development of standard model of electroweak interactions till the observation of W and Z bosons at CERN. Then the third epoch starts with the development of various neutrino experiments up till the award of Nobel Prize to Takaaki Kajita and Arthur McDonald. Then I will talk about the current status and future goals. Presently, we believe in the standard model of particle physics, where there are 3 generations of leptons, and to each generation we have a neutrino, electron type neutrino, muon type neutrino and tauon type neutrino. And each of them has been assigned independently a lepton number. Corresponding to each particle, there are 3 anti-neutrinos, and virtually we are living in a sea of neutrinos, where trillions of neutrinos are coming from the several directions, like from the core of the sun, from the Earth's core, from atmosphere and many other places. Even a single banana emits 1 million neutrinos per day. And the various sources that we talk about regarding the neutrinos, like cosmic neutrino background, Big Bang neutrinos produced during Big Bang nucleosynthesis, or solar neutrinos, geoneutrinos, atmospheric neutrinos. The energy spectrum, if you look at, it starts from microelectron volts, and for cosmogenic neutrinos, it covers more than electron volts. And this particle physics impact on physics is highlighted by 13 Nobel Prizes, which has been either directly given to the field of neutrino physics or in the field where neutrino physics has played a very important role. And the history of neutrino physics has been full of surprises, challenging our expectations about symmetry principles and conservation laws in nature. Therefore, in this brief period, I worry that I may not be able to cover all the significant events. My apologies in advance. Let me start with the first epoch. As we know that in 1914, continuous nature of beta spectrum was observed, and it was confirmed by Ellis also that really this is continuous. Then Ellis and Worcester found that the ejected electron has a fraction of missing energy, and then in 1928-29 it was observed that there is a problem with nuclear spin. Therefore, if we assume that a parent nucleus decays into a daughter nucleus and an electron, then there is a problem with energy and angular momentum conservation law. Now, starting from 1914 till the mid of 1930, everybody realized that there is some missing thing, and in the words of Lise Meitner and Ottman, the need for an elusive nuclear particle was strongly felt. Then in December 1930, Wolfgang Pauli hypothesized a neutral particle to save energy and angular momentum conservation law. It was in the form of a letter which was open to the participants of the Tübingen conference, in which Lise Meitner and Geiger and others were present. In the Pauli's neutron, Pauli called it first as a neutron. It is a constituent of nucleus. They don't travel with the velocity of light. Their mass is similar to the electron mass. They have a finite magnetic moment, and it shares the available energy with the electron, and that is why the spectrum is continuous. Now, the Pauli's neutron is a hybrid of neutrino, which we know today in the standard model, and the neutron, which is a member of nucleon isotopic spin doublet. Now, in June 1931, Pauli himself talked about the idea of new particle in the APS meeting, and then he also here abandoned the idea of the new particle being the constituent of the nucleus. Then a conference held in October 1931, Pauli spoke to Fermi privately about this particle, and this conference was presided by Mussolini. And Fermi at once showed a lively interest in my new idea and very positive attitude towards my new particle. And in this conference, Perrin was also present. But this idea was disliked by many, including Niels Bohr, Sommerfeld, Eddington, and many others. In 1933, of this Pauli's idea, Fermi built the famous quantum field theory of beta decay in analogy with the theory of quantum electrodynamics, and he wrote the beta decay Hamiltonian, considering the interaction to be vector in nature and the outgoing neutrino-electron pair carrying zero angular momentum. And here Fermi considered the neutrinos to be massless particles. Part of Fermi's conclusions concerning the shape of beta spectrum and zero rest mass were also drawn by Perrin around the same time. Then in 1934, Bethe and Pius estimated the cross-section for the inverse beta decay and found it to be smaller than 10 power minus 44 centimeter square. This is a Nature's paper, and therefore they concluded that it is impossible to observe such particles. A year later, Meyer floated the idea of two neutrino double beta decay. Then in 1936, Gamow and Taylor observed nuclear beta decays where there was a change of angular momentum of Fermi's theory, and they extended the Fermi theory to accommodate nuclear beta decays where there is a change of angular momentum by 1 unit. Then in 1937, Anderson and Neddermeyer, they observed another charged lepton, which we know by the name muons, and if there is a charged lepton, there must be a neutrino associated with it. And 10 years later, in 1948, it was found that this muon, when it decays, it gives rise to continuous energy spectrum. That means, again we need 3 particles in the final state. And in fact, in the words of Monte Carlo, at that time, people started believing that there are 2 neutrinos in the final state besides an electron. And in fact, they were called neutrino and nitrito. And in the words of Bethe and Becker, in a detailed review article, he writes that there is a considerable evidence for the neutrino hypothesis. That means theoretically people started believing in neutrinos. And in fact, in 1937, Rambaud, Roberts and Hastel introduced the Greek letter nu for the neutrinos. Therefore, nu was introduced in 1937. Then in 1937 itself, Majumdar gave the symmetrical theory of weak interactions where neutrino and anti-neutrino were indistinguishable particles, hence the name Majumdar neutrinos. And in 1938, Bethe wrote the celebrated paper on the theory of thermonuclear synthesis where neutrino was an essential component. Then in 1942, Fermi constructed a nuclear reactor which was assumed to be a good source of neutrinos. And in 1946, refuting the idea of Bethe and Pearls, Pontecarvo proposed a radiochemical method for the detection of neutrinos. And in fact, this idea was used by Ray Davis almost 30 years later in the observation of solar neutrinos. Then, for the first time, the idea of universal weak interaction came when Pontecarvo and his collaborators wrote papers on the muon capture and electron capture on the by nuclei, and they found that the strength of interaction which derive these 2 processes, they are of the same order of magnitude. A year later, Tomno, Wheeler, Klein and Poppy independently gave the idea of muon-electron universality, and assuming that for the muon decay, neutron decay as well as for the muon capture, the strength of the interaction is of the same magnitude, and this is the famous Poppy's triangle, assuming the same strength of the interaction. Then in 1953, Konopinski and Mahmoud and independently Marx and Zeldokovich, they gave the universal Fermi interaction, and they were the people who for the first time introduced the idea of law of lepton number conservation. And today we have 3 independent lepton number conservation for electron family, muon family and tauon family. But this time in 1953 there was only one type of neutrino and anti-neutrino. Therefore this lepton and anti-lepton number were introduced in 1953. Now when Fermi extended the idea of Gamma Taylor extended the idea of Fermi, the general Hamiltonian that was written had vector, axial vector, tensor, scalar and pseudo-scalar components, and most of the experiments were favoring tensor and scalar interactions in the Hamiltonian, and the consensus at that time before 1955 was that the beta decay weak interaction has scalar and tensor nature, while there were few experiments which were supporting for vector and axial vector interaction. In the meantime, in 1953, Rice and Cohen, they for the first time published a paper on the detection of free neutrinos. This experiment was performed at Hanford reactor, and they used liquid scintillator technique to observe the neutrinos. Now 3 years later, in 1956, they performed another experiment with bigger target and better cosmic ray shielding and confirmed their hypothesis of the detection for the neutrinos. Therefore, generally people know about 1956 paper, but it was in 1953 when they first published the detection of free neutrinos. Now, after 30 years of this Pauli's proposal, Ponte-Carlo said that it is difficult to find a case where what intuition characterizes a human achievement better than in the case of neutrino invention by Pauli. Around the time when Grimes and Covans were performing experiment at Savannah River reactor, Ray Davis, based on the suggestion of Ponte-Carlo, was performing radiochemical experiment in which he was looking for electron in the final state, and the results were negative. Therefore, it was concluded that electron type, there are two types of neutrinos, one which we call it as electron type neutrino and the other which we call it as electron type antineutrino, and these two are the different particles. I will come back to this reaction again when we have a radiochemical experiment and looking for the electron in the final state. Then in 1956, to solve the theta tau puzzle, Li and Yang proposed the parity violation in weak interactions, and for the first time they talked about this particle in April 1956. But before I move ahead, allow me to go a few years backwards in time. In 1952, when Abdus Salam was defending his thesis, Rudolf Piles was his thesis examiner, and he asked the question, the photon mass is zero because of Maxwell's principle of gauge symmetry for electromagnetism. Tell me, why is the neutrino mass zero? And neither Salam nor Rudolf Piles were knowing the answer for that. And Abdus Salam thought about this, and after 4 years, he came out with the idea that the analog for the neutrino of the gauge symmetry for the photon existed. It had to do with the masslessness of the neutrinos with symmetry under the chiral transformation. That means the idea of first time the two-component theory of neutrino was given by Abdus Salam. And then he communicated this idea next year to Rudolf Piles, and Rudolf Piles told him that I would not touch such ideas with a pair of tongs. Salam was not satisfied. Next day he communicated to Pauli about this idea by writing a paper, and this paper was delivered by Villards. And Pauli replied that give my regards to my friend Salam and tell him to think of something better. Everybody knows that Pauli had a sharp tongue. Therefore, this was his reply regarding Abdus Salam's idea. But what happened? Next year, Wu observed the parity violation in nuclear beta decay, and in fact, in the same volume, there are another two papers on the parity violation in beta decay. One is by the Lederman group and the other by Friedman and Telegdi group. Therefore, when it was established that parity is violated in weak interaction, Pauli realized his mistake and wrote somewhat an apologetic letter to Abdus Salam on 24 January 1957. In the meantime, in the early 1957, ideas similar to Abdus Salam about chiral symmetry were expressed independently by Landau and Li and Yang. But what happened? Abdus Salam got encouraged by the letter of Pauli, and therefore he extended chiral symmetry to electrons and muons, assuming that their masses were a consequence of what has come to be known as dynamically spontaneous symmetry breaking. Again, he communicated this paper to Pauli, and Pauli replied, for quite a while I have for myself the rule that if a theoretician says universal, it just means pure nonsense. Then, around 1955, ECG Sudarshan joined Robert Marshall, and he was asked to do work in the field of neutrino physics, weak interaction physics. And he went through all the papers of Fermi, Gamow and Taylor's and many others, and he found that most of the papers are suggesting the weak interaction Hamiltonian to be scalar and tensor in nature, while there are papers which suggest vector and axial vector to be the nature of weak interaction Hamiltonian. He thought that not all of them could be true at the same time. And he was convinced by himself that the nature of the weak interaction should be chiral V minus A interaction. And he spoke about this idea to Marshek, Gelman, Matthews, and many others who were present during a private lunch meeting. And in fact, after a few months of this meeting, Feynman and Gelman wrote a paper on V minus A interaction, while Sudarshan and Marshek wrote this paper later. And what happened that everybody thought that V minus A interaction theory initially was given by Feynman and Gelman. In 1958, when it was found by the Goldhaber that which determined the helicity of the neutrinos, that all neutrinos are left-handed, it was established that the nature of weak interaction should be V minus A. And all those experiments which were probating Sudarshan to say that weak interaction Hamiltonian to be V minus A nature, they turned out to be wrong. Then people also convinced others that in the scientific community that it was Sudarshan who first talked about the V minus A theory. Therefore, publicly Feynman in 1963 made a statement, the V minus A theory was discovered by Sudarshan and Marshek and publicized by Feynman and Gelman. And this is in literature we call by the name comedy of errors. Then we have the beginning of second epoch, when the idea of accelerators came, and it was by Pontecarvo, Markov and Schwarz. And also in the same volume where Schwarz has published this paper, another paper is by Lee and Yang on the theoretical discussion on possible high energy neutrino experiments. And from here muon type neutrino was obtained, and for the discovery of muon type neutrinos, Lederman, Schwarz and Steinberger were awarded Nobel Prize in 1988. Then 1960s were the years when the standard model of electroweak interactions was developed by Glashow, Slam and Weinberg, and Higgs boson, the quanta of Higgs field was an important component of this model. This is another story of development of standard model of electroweak interaction. I am not going to go into the details of this. Then in 1965, the Polar Goldfields in Indian scientific community, in collaboration with UK and Japanese scientists, built a detector in the Polar Goldfield mines, and they looked for atmospheric neutrinos. Around the same time, Ryan's team also developed a detector and did perform the experiment in South Africa for the atmospheric neutrinos. In fact, it is said that Ryan's first came to India to have such kind of experiment, but there were some political issues, and therefore he was not allowed to do this experiment. Then 60s were also the years when Beckel and Raymond Davis developed the home stake experiment to detect the solar neutrinos, and on the advice of Luis Alvarez, and they found that the theoretically predicted value of solar neutrinos by John Beckel does not agree with the experimentally observed number. The experimentally observed number is only 40% of the theoretically predicted value, which we know in the literature by the name solar neutrino problem. Now in the early 70s were the years when we had the development of many accelerators at Fermilab, in CERN, in Russia, as well as these were the years where we had the development of various bubble chamber experiments in Gargamel, at ANL bubble chamber experiment, BNL bubble chamber experiments, and in fact the Gargamel experiment discovered the neutral currents in July 1973, and we had AXER, big European bubble chamber experiment, and the other bubble chamber experiment was built at the Formula, the 15-fifth bubble chamber experiment. Then in 1975, tau lepton was discovered at Stanford positron electron accelerating ring, and when you have a lepton, that means there must be a neutrino associated with it, which was discovered 25 years later by the donut collaboration. Then 1974-75 years, also the years where in the neutrino scattering experiments, first indirect experimental evidence of charm baryons came. Then the idea of neutrino flavor oscillation came. First it was by Monte Carlo in 1957. As we know that rumors travel faster than the speed of light. Therefore, a rumor came to Monte Carlo that Ray Davis has observed electron in the final state at the Savannah River reactor. Therefore, he proposed the idea that like K0, K0 bar oscillation, you can have left-handed neutrino to right-handed neutrino oscillation, or left-handed anti-neutrino to right-handed anti-neutrino oscillation. And this is what today we call by the name sterile neutrinos. But it was found that this information was wrong. But at the same time, in the early 60s, when accelerators...
I'm sorry, but you have to stop.
Give me 2-3 minutes.
Yeah, 1 minute. You have 1 minute on.
Okay. Then the oscillation idea came, and then nu mu and nu e electron oscillation experiments were being developed, and where it was found that muon type neutrino or electron type neutrinos, they travel in the different mass eigenstates, and that is why in the literature now or worldwide there are many oscillation experiments to determine the several neutrino oscillation parameters. This stands for cos theta 12, that is theta 12, theta 13 and theta 23 and delta are the different neutrino oscillation parameters, and therefore you have the mass differences square of the eigenstates for which the experiments worldwide are being performed. These are the different accelerator, solar and reactor experiments which are determining the value of these different oscillation parameters, and these are the current values of these oscillation parameters, but we need precise experiments. Then the other concept in neutrino oscillation came where people talked about matter enhanced neutrino oscillation, which was given by Wolfenstein, Mikhaev and Spinoff, which we know in the literature by the name MSW effect. Then we had the third epoch when we had the development of reactor experiments, accelerator experiments, as well as atmospheric neutrino experiments. And in fact, at Supernova 1987 event is very important, where 3 different detectors, Kamiokande, IMB and Baxan, they observed supernova neutrinos, an important prediction from the theory. Then in 1989, LEP experiment discovered that there are 3 neutrino species only, and in 1998, Super Kamiokande collaboration confirmed the hypothesis of neutrino oscillation in atmospheric neutrino experiments. Then in 2000, tau type neutrino was discovered by donut collaboration. Sudbury Neutrino Observatory confirmed the solar neutrino oscillation phenomena, and Davis and Koshiba, they were awarded Nobel Prize for the detection of cosmic neutrinos. Then the beginning of 21st century were the years when the neutrino oscillation experiments came with the accelerators like K2K, MINOS, T2K and many others. In the meantime, in 2012, Higgs boson was discovered at CERN by the ATLAS and CMS collaborations. And then the other major discovery was also the observation of theta 13 by the Deape reactor, which was confirmed also by Renu and double shower experiments. And they found that this sine theta 13 is non-zero, which gave the idea just that CP violation, we can study CP symmetry using lepton sector. And in 2015, Kajita and McDonald, they were awarded Nobel Prize. Then 2016 was another interesting year where Ice Cube collaboration for the first time observed beta-electron worlds of neutrinos, and it is attributed that they are not from within our galaxy, they are from some brazzers. And what they have done, they have developed a cubic kilometer of transparent natural Antarctic ice into a Cherenkov detector, and they are detecting neutrinos from there. Then we had I am leaving this. Then we have the.
You cannot go on like this.
The just last two slides. The problems today.
It's concluded.
Yes, the problem today is to determine neutrino mass eigenstates states. The problem today is to determine the masses of the neutrinos. We have the upper limits, but we want to determine the masses of these particles. Then we want to determine the parameters, for which we have two different experiments. Then we can study about the Earth's course using geoneutrinos, and recently Ice Cube collaboration along with Pingu and KM3net, they are studying the tomography of the Earth using Ice Cube. Then the last is the multi-messenger astronomy is currently in a topic where people are using gravitational waves, electromagnetic waves, as well as neutrinos, and these are the various detectors worldwide to study these neutrinos and to get a comprehensive picture of astrophysical events. And neutrinos can also help us to track the nuclear vapors. Therefore, worldwide, lots of activities are going on to understand this elusive particle, and they can be of help to know the other astrophysical phenomena in the universe. Thank you.
I think there is no time now for any more questions. So we will conclude this session here and thank Dr. Sajjad Athar for a very comprehensive historical perspective on neutrinos. He probably required much more time to finish his talk in a relaxed manner, but that can be done in some other platform. Thank you very much.
We will break for tea, but we have to come back very soon, maybe possibly within 15 minutes, very strictly, because we have another 3 talks going on. And those 3 talks, I do not know how much chopping we have to do. But yeah, sufficient time will be given, but at a rapid pace it should be over.
He is afraid. How much
I again request you that those who have produced bills, please sign the forms, otherwise without your signature and bank account details, reimbursement cannot happen. So please do that. And Dr. Balasubramanian, we have your cab going at 4:20. So if you are around, please catch the YP Vyogi. YP Vyogi is an internationally renowned experimental nuclear physicist, leader of the Indian team for CERN WA93, WA98 and ALICE collaboration, as well as BNL relativistic heavy ion collider star collaboration. He is a recipient of the Helmholtz Prize for discovery of azimuthal flow in relativistic heavy ion collision of nuclei. He is a former director of Institute of Physics, Bhubaneswar. I warmly request Dr. Vyogi to come up to the stage and assume the chair, sir. And along with this, I also request the speakers of this session, Dr. Raghunath Sahu, Dr. Rupa Chatterjee, and Professor Nadeshan Ramamurthy, Dr. Nadeshan Ramamurthy, to also come up to the stage.
Professor Ramamurthy, भाग्य क्या? सब भाग्य। दिनेश जी, Raki Saab, Grover Saab. Actually, I have to tell just a couple of things because we have assembled here to pay our tribute to Dr. Ramanna, and I just found out a few photographs in my old album. It actually is from Dr. Ramanna's visit to BSc. So you see the photograph actually, and Dr. Dibatia is there, Dr. Ramanna you can recognize, and by his side, lean and thin, you recognize the person? That lean and thin person? By the side of Dr. Ramanna on the other side?
I recognize, but I don't
You recognize. Oh, उस समय का टीके से वास्तव है। उस समय का टीके से वास्तव है। Anyway, so this was the better aspect of the same meeting, and some more photos. And there is another photo I have, which is scenario now, and that is also Dr. Ramanna did it, but now you see this photo where Ramanna Saab, now Vikasina appears. And Divaja Saab is gone. But Vikasina appears, Manoj Pal is here, I am still there, and in those photos, somehow I don't know which event was that, but I didn't find Manoj Saab को भी याद होगा या नहीं पता नहीं. Nobody from the accelerator side was there.
No, this is when Biren Rai was trying to make that stupid auditorium. Biren Rai was trying to make the stupid auditorium in SINP. That is when Dr. Ramanna came to lay the foundation stone.
He came and never did go ahead. Anyway,
it was supposed to be in
matter. And one more point I want to add you that in 1983, the nuclear physics, annual nuclear physics symposium was held in Mysore. Ramamurthy Saab was the convener, and that time my first flight invited was there in the symposium, not on any physics topic, but on data acquisition. That time I was a data acquisition man, and Dr. Ramanna strenuously He attended the full talk and then he made a comment. After the talk, he also made a comment. Whatever technical comment is not important, but he told after Yogi went to Kolkata, he became 70% in yogi. Now, whatever it means, I don't know, but he did make a comment in Mysore in the symposium. Okay. Last time that I met Dr. Ramanna was in this campus, the director's office. I don't know, this was one of those building the offices here in the building. I had come here in '93, I think, for a discussion with Bell for the development of silicon flat detectors with them. And there they had advised that since Bell is a defense lab, I should push it through Dr. Ramanna. So from Bell I immediately took auto and I came here and talked to Dr. Ramanna. And he was very supportive. Although that time this work didn't go through, later on we had, and now in fact we have produced a lot of silicon flats from Bell. So with these words, I finish, and then I have my next job to introduce the speaker to you. The first speaker, Dr. Raghunath Sahu. Dr. Raghunath Sahu is Professor of Experimental High Energy Physics at IIT Indore. He did his MSc Physics from School University in Bhubaneswar in '99 and PhD in Experimental High Energy Physics from Institute of Physics Bhubaneswar, working in the STAR experiment at Brookhaven. Later he was a visiting scientist at IOT Bhubaneswar, University of Cape Town, South Africa, before joining Suache in France under the CNRS fellowship for his first postdoctoral studies. He took up second postdoctoral at INF in Padova, Italy, with the prestigious INFM International Fellowship to work in the ALICE experiment at CERN for the creation of quantum plasma through the well-known Big Bang experiment. His association with large-scale high-energy experiments goes back to 2001 when he started working simultaneously at Brookhaven and the CERN. Currently, he is the team leader and principal investigator of ALICE and CVM at DSI, Germany, the experimental projects at IIT Indore. He serves as member of the ALICE and CVM collaboration boards and member of ALICE India Management Board. He is also a member of the Scientific Council of JNI Tugna, Russia, the largest laboratory in Russia. So, with this introduction, I call Dr. Raghunath Sahu to give his talk. Already lost 1 minute. I will give you 20 minutes only. Your 20 minutes started from so exactly at 5 o'clock, I have to talk.
Okay, so good evening to all of you. I feel a little nervous because I found many of you are, either my teachers or my PhD time directors, including Dr. Yogi and Dr. Chaudhary and Dr. Srivastava and Dr. Mohanty. So they are gracing the occasion today, and they are my external examiner of my PhD thesis. So I feel a little nervous, and of course with the time constraint, but I feel privileged and thanks to the organizers for this opportunity to stand before this August gathering. And just to quickly introduce my group, which we started, of course, after a review during 2013. So we are almost 10 years old into the game of high energy physics after I joined IIT Indore. So we are a part of the ALICE experiment, which is the running experiment, and in the future experiment CVM and the EIC in Brookhaven. This is the composition of my group. And for a cosmic hadronic air shower comparison with heavy ion collision, so I am also a part of the GRAVES experiment in UT. And before I proceed, so I have been instructed that I should connect nuclear fission to heavy ion collision, which is a difficult job for me, but I will try my best. And again, given the time constraint and our tight chairman of this evening, so history is a powerful resource for shaping our understanding of the present and future as well as the past. And as Rutherford once said of the scientific hypothesis, the more attractive clothing
they can be wrapped in, the better. So, but for the present, the being ignorant about past is the privilege of the youth. So, falsifying this statement, so NIAS has done a good job of making a remembrance of Dr. Ramanna and his contribution to building the nuclear infrastructure in the country, and of course taking us to the different landscape of quark-gluon plasma, which is the frontier of high energy physics in the energy and luminosity frontier. And the way I have made the composition of the talk is essentially to address the gathering where we are celebrating the centenary celebration, and this talk is supposed to be little relaxed. That is the way I have made it, and of course this will encourage the next generation. So the accelerator which was used was a tabletop with 30 centimeter length, and with the discovery of isotopes, essentially different same place in the periodic table but different weights, and this gave rise to Soddy getting Nobel Prize, but this was not understood from the then available nuclear model of proton and electron. And the discovery which I like the most is the neutron discovery, because you see the way it happened. So this has little remembrance with the billiard ball collision. Essentially the masses should be similar, and that ruled out the existing subatomic particles like gamma rays to be the the particles coming as unknown radiation. So this was actually came out as charged neutral, not getting affected by the magnetic field and more penetrating, and this was the interaction, and the mass of the unknown radiation was comparable to the proton, which we learned from this experiment. And again, this 1932 is the year which is called as the year, marvelous year of nuclear physics, because James Chadwick's discovery of neutron, and again Krukop and Walton's artificial disintegration of the particles, essentially bombarding proton on lithium, and which breaks to helium. And again in the same year the Carl Anderson's discovery of positron and electron. And Newton essentially simplified the nuclear theory and became a key ingredient in the discovery of artificial radioactivity. And nuclear fission came up with Otto Hahn and Strassmann and Meitner in the 1938. And as I wrote in my earlier slide, it is essentially science for peace and war. That is the Kaiser Wilhelm Institute of Chemistry in Berlin, where this nuclear fission was discovered. And somewhere I happened to be in last March in the Free University of Berlin, and I was just taking random pictures, and I found that this is a beautiful building, and later on I came to know that this is the building where nuclear fission was essentially invented. And then going back to Dr. Ramanna for one slide, he was the first Indian scientist to my knowledge who was trained as a nuclear fission scientist of the country. And then we had first nuclear research reactor coming up named as Apsara by Pandit Nehru, and of course that took us to Pokhran 1, and he was the leading member in that team. And the game which started is atom smashing, and this is from Cambridge to CERN. And Cambridge we started with a 30 centimeter length accelerator to almost now touching 27 kilometer accelerator at CERN. Of course there is a degree of magnitude changing the degrees of freedom, namely from nuclear degrees of freedom to quark-gluonic degrees of freedom. So then the journey towards the discovery of quark started. So we went to SLAC, and the energy of electron on proton was around 42 GeV, and then accelerator length also expanded, and we through deep inelastic scattering, so we started discovering the quark structure of proton and neutron, and this is already discussed. So we have 3 generations of quarks and leptons. And then the game for finding free quarks in nature started, and this is the guiding principle, and the conclusion is the basic property of QCD interaction is such that we cannot find free quarks in nature. So we didn't stop there, and these are essentially the guiding principles which came up. And 2004 Nobel Prize was given to Gross, Wilczek and Polizer. Of course, another additional stuff is QCD predicts the normal nuclear matter can undergo a phase transition to quark-gluon plasma with a very tiny lifetime, of course, strong interaction lifetime. And we can produce a locally thermally equilibrated state of matter, and our game essentially started to the beginning of the universe. And you see the collider experiments versus fixed target experiments, so those came up, and our aim is essentially to produce a debris which can give us a hint of quark-gluon plasma. So that is why this cartoon shows that this collider experiments are better preferred, and this one can show with a back of the envelope calculation that energy available for particle production is much higher in the collider experiment, which goes like twice of the beam energy. So with this we started accelerating nuclei, essentially the heavy nucleus, and you can see that the Lorentz contraction in the longitudinal direction, and we get into the debris. And if you ask the question how high is the energy, and since we are looking into quarkonic degrees of freedom, and energy goes like 1 over the size, the energy is very high. And once we have very high energy available, so what we can do is we can produce multitude of particles in the final state. That of course gives a different avenue of applying statistical mechanics and other techniques like machine learning in the final state. And that also takes us to the early universe scenario. As you can see, E is equal to KT is connecting to early universe through very high temperature. So then essentially the Big Bang collision in the laboratories like the RIC, Brughaven laboratory and CERN is taking us 13.7 or 13.8 billion years ago. And the way the dynamics of quark-gluon plasma happens is we have a longitudinal contraction, this nuclei look like pancakes, and after the contraction happens, there is a pre-equilibrium dynamics, possibly there is a quark-gluon plasma formation which has to be characterized, and through this complex dynamical system, so we detect at the end different subatomic particle tracks in our detectors. And these are highly sophisticated multi-purpose detector which I will show you quickly. So the accelerator facilities for heavy ion collision, if you see, so it started with the 1984 from Bevlak experiment to LHC. Of course, India had the opportunity to participate in several experiments, and our journey to the high energy physics, high energy nuclear physics part of the landscape started a new era of nuclear physics in India. And I should remind the audience, and of course this is important for the next generation to know, that with the leadership of Professor Vikas Sinha during 1986, so there was a meeting which was in Bombay, and you can see some of the people like S.S. Kapoor I was expecting to be here, and Professor Ramurthy, Professor Vyogi, and so many people are here who are very instrumental in starting this landscape of quark-gluon plasma physics, which is the frontier of nuclear physics. And then Indian quark matter community started. Of course, we have to go parallelly with the theory and experiment, and many people gave a big hand like Vikas Sinha and Srivastava, Shivaji Raha, Jane Alam, and TFR, Lattice QCD group also. These are also, just to name a few. So parallelly, starting from CMOL, some people also started joining, and we had a national laboratories and university collaboration which participated in this quark-gluon plasma service. So if you see where we start as of today, we participated in SPS, RIC and LSC activities, and I collected the information from our existing collaboration last 15 days. I was happy to report to the people who originated this program that total number of PhDs produced in the QGP experimental stream is around 147, of course with number of 5 error, and almost 55 students are continuing PhD right now. So this is talking about the growing Indian team with a global footprint, because once upon a time 50% of the LSC PGP publications are from India. So our journey started in WA93 experiment, and we started with a scintillator pad with wavelength shifting fiber. And you see, parallelly our MOU with CERN for technology transfer and everything should go on. And thanks to then AEC chairman P.K. Iyengar and Director General of CERN Carlo Rubbia. So DAE CERN protocol and LHC collaboration started. Of course, subsequent renewal has to happen. Then our to the elliptic flow. Of course, that was not named elliptic flow at that time. And then this PMD model fabrication started for the star collaboration. This is purely Indian effort, and the way it is termed, it is industrial production of proportional counters in our Indian laboratories. So that is the way it started, and this is the star experiment picture in Brookhaven, and this is the close-up view we can see. And then we slowly, parallelly entered into the domain of LHC physics doing QGP at tera electron volt energies. And you can see this is the dedicated experiment for QGP. Of course, we have equal participation in CMS experiment, which I am not going to cover. So ALICE collaboration is 40 countries and 171 institutions and almost close to 2,000 members. And this is the picture of Indian QGP community, experimental QGP community, and it is growing every day. People are joining in the effort for short-term parallel plasma. So my involvement in ALICE or STAR experiment towards the hardware happened during my PhD time at Institute of Physics. I was quite fortunate that this was the only time I had the opportunity of doing little hardware. After that, I could not get any opportunity of doing hardware, and how difficult it is to set up a hardware lab in the laboratories. People who have done, they know it. And I thought I should show this thing. And without any experiment, I remember any experience. I remember Dr. Byogi deputed me to CERN, and I participated in this test tube experiment, and I learned a lot from that, which I show everywhere. So this was the only opportunity. So I urge our next generation students who are doing experiment, please do little hardware to have a different exposure. And this is the again ALICE experiment where PMD and neon is our Indian footprint, and this is PMD, the detector view, and you can see this is fabrication happening in VCC. Dr. Vikas Sinha, Dr. Srivastava, Dr. Bhandari, Dr. Byogi. So these people are leading our Indian efforts in this direction. Thanks to all these people, so that many people they have made their career in the frontier of nuclear physics. Okay, so these are a couple of pictures. And if you look at the Large Hadron Collider at the moment, so nowadays after the discovery of QGP at the relativistic heavy ion collider Brookhaven, so main focus is on PP physics, so I will cover a little bit on that. And now the question is, do you see QGP in proton-proton collisions in 3 energies? Because so far the characterization of QGP in heavy ion collision, PP has been taken as the baseline. So now the discovery came through again our understanding of strengthless enhancement, and I remind you that the beam we are taking for collision, so strange quark is not part of the beam, because this is neutrons and protons are part of the nuclei. So what is happening is, any production of strange quark and enhancement with respect to the baseline can give us the hint of quark-gluon plasma, and this is called as a smoking gun signature of quark-gluon plasma, because these are all QCD level production. So first we observe this strengthless enhancement in heavy ion collision. You can see the multi-strength particle enhancement with respect to the PP baseline, and there is an enhancement here. And again going to LHC PP collision, if we see, again PP cannot be taken as a baseline. So what we have done is, we have taken the ratio of this multi-strength hadrons with respect to pions, which are abundantly produced in the system because of the low mass. So if you see, depending upon the strengthless content, so that is an increase with respect to the particle multiplicity in the final state, which combines PP to heavy ion, irrespective of the system size. So this gave a hint of final state particle density driving the particle production mechanism. And if I try to fit Blaster kind of description, so what I find is the extracted kinetic reserve temperature and the radial flow velocity is comparable to what we have observed in heavy ion collisions. So this also gave a hint of collectivity in PP collisions. And again, there is a hierarchy in strengthless enhancement, and these are confronted to the 2010 measurement of Reese-like structures in azimuthally collimated long range, means large delta eta and near side, which is small in delta phi, Reese-like structures which were seen in copper-copper and gold-gold collisions at Leak. So this gave a hint of collectivity, and just to confront to this data, when we compare with E plus E minus collision data of Bell, so we found there is no Reese-like structure in E plus E minus collision. So that means PP high multiplicity is giving a hint of collectivity like heavy ion collisions. So now other signatures also we have to confront to before we declare that we have seen QGP in PP collision. So then taking this ratio, which is essentially a jet-like signal in X collision, X I am combining nuclear, hadronic and nuclear collisions, and then this is with respect to the medium bias PP collision. Now the phase space I have divided in a way, so this is leading particle which is Z, so this angle is essentially towards the Z and this is away side Z. So what is shown here is when it is plotted as a function of mean charge particle multiplicity, so in heavy ion collision, so that is a increase towards the particles towards the Z direction, and there is a decrease or the suppression towards away direction. So this is telling me that the Z suppression in the away side, and that is an enhancement happening in PP heavy ion collision. But however, that is not seen in PP collision and P-led collision. So what the message I am trying to give you is, in PP and P-led collision, although strangeness enhancement is seen, Z-like suppression is not seen. So that is why we are not in a position to declare or announce that PP high multiplicity has a QGP signature. So with this, during the COVID time, I engaged myself and wrote this possible early universe signal in PP collision and collider, and I found just last week of August, almost 700 people have read it, and this is a popular article published in Current Science, bringing the highlighting features of QGP in PP collision. So then just spending 2-3 minutes on the ALICE upgrades. So in the round 4, which is starting after, there is a shift now, so after 2025, so we will have a forward calorimeter where India is trying to participate, and we will also replace the tracking system. So we will go to ITS-3 with complete silicon architecture. And if you look at the ALICE timeline, so this is where round 3 PP data taking is going on, and we also plan to take light ion data, for example, P oxygen and oxygen, which will have a cosmic correspondence. So that will be for one day. And this upgrade I talked about, and then I think I have come to the end of my lecture. And I should acknowledge DAE DST for generous support to this mega science project in India, and of course to Dr. Y.P. Byogi, the experimental endeavor started by him, and some of the slides, although not explicitly mentioned, it is taken from him. And Dr. V.C. Sahani, former director RRCAT, I also collected some slides on RRCAT contribution to this program. And of course, the chairman of DAE, starting from Dr. P.K. Iyengar to Dr. A.K. Mohanty, for supporting this endeavor in the nuclear physics landscape. And Professor Atul Gurtu, who was former India CMS spokesperson, he also gave me some historical MOU and the documents which I am keeping for the next generation. And sound management, of course, sound management also gave lots of documents. I have all the MOUs signed by India Sound. I am keeping the copy for record. And of course, the ALICE India Collaborating Institute and the vibrant team of PhD students, which is the workhorse. And India became associate member of SON in 2017. Thank you.
Okay, since we are running out of time, so there is no discussion, but if you have questions, that is the speaker during the triplet later. And now, Rupa, run to the dais before I introduce you. Next talk is by Dr. Rupa Chatterjee. Dr. Rupa Chatterjee began her research career in 2005 as a PhD student in physics group at the Variable Union Center, Kolkata, under the supervision of Dr. Srivastava in the area of high energy nuclear physics, specifically quantum-plasma phenomenology. She obtained her PhD in 2010 with a thesis entitled Consequences of Electric Flow in Relativistic Heavy Ion Collisions, primarily investigating the anisotropic flow of photons. She was involved in the first time prediction of electric flow of thermal photons produced in relativistic heavy ion collisions, which has since become a key observable for studying the hot ended initial state generated in these collisions. In 2010, she joined the Department of Physics at the University of Jyväskylä, Finland, as a postdoctoral researcher,
Later they joined DSC again in January 2013 as a Dr. K.S. Krishnan Research Associate. She has been a scientific officer at DSCC since 2014. Her research interests are focused on studying electromagnetic probes in relativistic nuclear collisions, which are considered among the most efficient and clean probes for the investigation of properties of the evolution of plasma state. Rupa, go ahead.
Thank you.
Your time is 20 minutes.
Yeah.
And finish.
Okay. So, first of all, I would like to thank DK sir and all the organizers. I am extremely honored and grateful to be part of this birth centenary celebration of Dr. Ramanna. And from the morning, I've been listening to the wonderful talks, and it's been a very enriching experience for me to know so much about the nuclear physics research in India and also about Dr. Ramanna. So I'm going to talk about relativistic heavy ion collision and coagulant plasma from that. So let us start. Okay, so the primary goal of relativistic heavy ion collision is to study the properties of nuclear matter under extreme conditions. And let us start from the beginning. So if we ask two very important questions, that is, one is that what are the basic building blocks of matter, and second one, when was matter created? So the study of coagulant plasma basically helps us to understand these questions. It is the coagulant plasma, or QGP, is the primordial form of matter and the root of various elements present in the universe. Now, what is basic building block? That is basically the elementary particles. So matter is composed of elementary particles, which are the most basic units that are not known to be made of anything smaller, and which are basically the quarks and leptons. And the normal everyday matter is basically made of proton and neutron. The nucleus is made of proton and neutron, which are nothing but the first generation of elementary particles, that is the up and down quarks. So what is coagulant plasma? Coagulant plasma is basically a deconfined state of quarks and gluons in local thermal equilibrium. It existed a few microseconds after the Big Bang and possibly at the core of massive neutron star. And it can be created in the laboratory by colliding heavy nucleus at relativistic energies. So how to produce coagulant plasma? By colliding heavy nucleus. So if we ask what happens to matter if we make it hotter and hotter. So with increasing temperature, matter undergoes several distinct phases or transitions. And at very high temperature, high means of the order of 10 to the power 12 Kelvin or so, one gets the coagulant plasma, which is basically a deconfined state of quarks and gluons. Now it all started way back in 1973 with the discovery of asymptotic freedom. So where it was shown by this trio, Professor David Gross, Frank Wilczek and David Pulitzer, that the QCD coupling that basically gets weaker at high momentum transfer or at very small distance. And as a result, the quarks and gluons, they become asymptotically free. Whereas at relatively larger distance, they are confined within the hadrons. So isolated quarks and gluons cannot be observed, only color neutral hadrons. And the QCD potential, which is basically has two parts, and this term, the linear term, is basically responsible for the confinement. And after the discovery of asymptotic freedom in 1975, soon after 2 years, in this work by Collin and Perry, they first time showed that, or they argued that the core of massive neutron star, the density, the matter density is few order of magnitude larger than the normal matter density. And that might result, or one might expect, that hadrons to overlap at this very high density and their individuality to be confused. And therefore they suggest there is a phase change and that the nuclear matter at such high densities is a quark soup. And in the same year, in 1975, after that, Cabito and Paris, they first time they showed that they argued that the exponential hadrons are not necessarily connected with the limiting temperature, rather a different phase in which quarks are not confined, this suggested. And they showed this very simple phase diagram, QCD phase diagram, temperature versus barrier density, which showed the two regions. The one is the confined phase where it is hadronic, whereas the unconfined or the deconfined phase is QGP is this region. And soon it was realized that this new state could be created and studied using relativistic heavy ion collisions. And that simple phase diagram now has, it shows a very rich structure basically. So the theory group at TIFR, the lattice QCD group, they have done significant work in this. And the matter created, the transition, the matter created in the laboratory by colliding heavy nucleus, basically the temperature, one can say that the temperature is very high, of the order of 10 to the power 12 Kelvin or so, and it is 10 to the power 5 times larger than the core of the sun. And the experimental form, Professor Raghunath Sahu has already talked a lot about this. So it started way back, but then in 2000 with the gold-gold collision at relativistic heavy ion collider first provided experimental evidence of quark-gluon plasma formation, and later it was confirmed by the late-late collision at the LHC energy. So this is a schematic showing the different stages of heavy ion collision. So to Lorentz contracted nuclei, they come, they collide. Soon after, a quark-gluon plasma phase is formed, which cools by expansion, and it hadronizes, and the particles reach the detector. Now obviously the central or the head-on collisions are of special interest because they produce the maximum energy density and temperature. However, there are some phenomena, interesting phenomena, which are only possible when the collision is not central but peripheral. So I shall be talking about that. So it is a typical collision geometry. So as I said, the hot and dense matter produced in the heavy ion collision is expected to have a very transient existence. That is, its lifetime is of the order of few Fermi over C, which is of the order of 10 to the power minus 23 seconds. So it makes it quite challenging to extract information about the initial state and the properties of the earliest hot and dense stage of the collision. And information about the whole space-time evolution of the system is obtained from the various observables measured in the final state only. And among the observables, basically the two observables which provided strong evidence of quark-gluon plasma formation at relativistic energies. One is a large elliptic flow, the observation of a large elliptic flow at the relativistic heavy ion collider, and also jet quenching or suppression of high-pitty particles. Now, one of the most successful frameworks that to study the evolution of the hot and dense QGP formed in relativistic heavy ion collision is relativistic hydrodynamic model. And it has shown first time that clear mass ordering in the particle spectrum measured in the detector. So hydrodynamics predict clear mass ordering not only in the spectra but also in the electric flow. So what happens is basically as the collective radial motion boosts particle to higher average velocities, heavier particle gain more momentum than the lighter ones, and leading to a flattening of their spectra at low transverse momentum. And this also leads to the different different slope of the anisotropic flow, or in particular elliptic flow of hadrons. Now there has been significant work done in the relativistic hydrodynamic calculation, and in VEC also Dr. Sushant Singh presently he has developed a code of relativistic hydrodynamics, and also in NICE Dr. Victor Rai and Amresh Jaiswal, they have done extensive work in this relativistic hydrodynamics model. So as I was talking about elliptic flow, so what is elliptic flow? Basically one of the prominent signatures of QGP is elliptic flow. It provided the information that there is a conductivity in the non-central collision of two spherical nuclei or central collision of deformed nuclei, the overlapping zone between the nuclei, it is no longer circular. So this spatial anisotropy in the overlapping zone, basically that gives rise to azimuthally anisotropic pressure gradient, and also the particle distribution shows a azimuthal anisotropy, and that is quantified by elliptic flow. So it shows here that if we take a small value of elliptic flow, this polar plot of azimuthal distribution of different Fourier expansion, one can see here that for finite elliptic flow, it shapes the distortion from the center. Circular shape is like this, and also the elliptic flow has been found to be significant, and hydrodynamic model has been able to explain the elliptic flow of charged particles up to a very large value of transverse momentum. Now, initial all calculations basically were done considering a smooth initial density distribution, and soon it was found in the experiment that as the origin of elliptic flow is initial spatial anisotropy, even for most central collision, the experimental data shows significant elliptic flow results. So, and it was realized around 2010 that event by event fluctuating initial hydrodynamic model calculation is more realistic while explaining the data rather than a smooth initial density distribution. So this calculation basically here the initial temperature distribution using a hydrodynamical model at different tau values on the transverse plane has been shown here. So one can see that this very pronounced hotspots can be seen here due to the event by event fluctuation. And not only that, it can also give rise to significant initial triangular geometry, and as a result one gets the triangular flow also for charged particles. Jet punching, I am skipping this part as Professor Ramanna has already talked about this in detail. So, photons are one of the key observables studied in relativistic heavy ion collision. That has been considered, they have this advantage of that their emission is very sensitive to the initial state of the produced matter. Even a slight modification in the initial condition that gives rise to significant different result in the final state. Whether it is spectra or an isotropic flow, a small change in the initial condition would result in significant difference in the final state observable. So in that respect, they are one of the most promising observables. And there has been significant work done in India, in BEC especially. It started with Dr. Vikas Sinha, and then Dr. Dinesh Srivastava, and later Dr. Jane Alam. So many things has been studied theoretically using photon observables, like the initial temperature of the plasma forms some idea of the initial temperature, intensity interferometry, its evolution, its system size. Now one thing is that this thermal spectra basically, so Dr. Jane Alam and collaborators, they have done extensively in the photon production from the hadronic phase. And this one plot, basically here it is showing that one of the first signatures that there are thermal photons, and one can basically see a clear signature of the TGB phase from this result. So the direct photon data from heavy ion collision basically matched with the results from PP collision, and it was found that at low PT there is an excess of direct photon heat, and that was attributed to thermal photons, the photons produced in the thermalized coagulant plasma. Now theoretically, experimentally it is not possible to differentiate between the photons from experiment and from the different sources. However, theory can be used to calculate the thermal photon spectra, and it was matched very well. So this excess photon production from compared to the PP collision has been matched with the theoretical thermal photon production using a hydrodynamic model, and it matches well with the data. Now this one work I would one of the first calculations where in our group, Dr. Srivastava actually initially started that first time we showed that the elliptic flow of photons, it basically shows a very different nature compared to the elliptic flow of charged particles. So unlike the elliptic flow of hadrons at very large VT, the photon elliptic flow basically goes down. So it is only possible when we get competing contributions of the photons produced both in the QTP as well as in the hadronic phase. And these remain one of the talked about problem. Basically, there are many studies. Actually, the experimental results show similar qualitative nature of photon V2. However, there is a gap between data and theory. So that is popularly known as direct photon puzzle. So there has been significant work in last 10 years to understand the puzzle, but still it is not resolved fully. So not only the elliptic flow of photons, there has been calculation of elliptic flow of dielectron as well, which shows very different nature again compared to the elliptic flow of hadrons, and the data is still remaining to be published. I mean, the data with very little error bar. Data is there, but it is still in not that form. So, please keep this. So, various things has been studied already, but still we are not very sure, or we don't have precise knowledge about the initial state, like the formation time, the lifetime, as well as the freeze-out temperature of the system produced in heavy ion collision. So there are many things we need to know about the initial condition. Also the search for critical point. The QCD phase diagram which I showed, there is a critical point, end of the first order phase transition. So there is a beat energy scan program going on to detect the critical point. And also recent time there has been some work, especially in the critical point which show the potential to study nuclear structure or the nucleon level geometry using the relativistic heavy ion collision. So I will just show a couple of slides on this. So as we have all known, this clustering has long been known to play a key role in the understanding of structure of light nuclei. So it started with the study of this Polish group. So they showed that actually they argued that relativistic nuclear collision may provide experimental evidence of clustering in light nuclei. They illustrate the feasibility of this idea by colliding heavy nuclei with a light carbon nucleus with alpha cluster structure, and the results showed significant qualitative as well as quantitative difference when the same collision is studied without considering the alpha cluster structure in carbon nucleus. Also, as we know that there is the upcoming O collision at 7 TeV at LHC, so one can get basically experimental verification once the data is there for this cluster structure. So this is one theoretical model calculation which is showing that if we consider a triangular alpha cluster structure in a carbon nucleus, then we collide with a carbon with a heavy ion gold or lead. So due to this clustering structure, there is an isotropy of the temperature as well as energy density distribution in the initial state, and the results here are shown for 4 different angles. So this is for theta 0, some other angle theta pi by 4, and this is one configuration where we are getting a peanut-like structure. And of course, if we don't consider any cluster structure, then the energy density becomes like the distribution of energy density becomes smooth like this. Now, when we calculate finally the photon observable, one is the elliptic flow and the triangular flow, what we see is basically that due to this initial triangular eccentricity, the triangular flow of photon, which is normally one sees that triangular flow is always smaller than the elliptic flow. However, for this particular case, what we saw is that elliptic flow is significantly smaller than the triangular flow parameter when we consider the initial state cluster structure. And the clustering structure is considered in a carbon nucleus. So with that, all I want to say is that there has been significant advancement in the theoretical framework as well as in comparison with the high precision data in last 10 to 20 years. We also have some new ideas, new model, experimental access to wide range of beam energy system and observables. And with that, the future of quark-gluon plasma looks quite bright.
Good, thank you. Again, questions during tea time, and I quickly now I introduce to you the last speaker, my own batchmate, Dr. Tata.
No partiality.
No partiality. Now, whatever is written here, I read partially, that is the partiality. Dr. Tata has been an adjunct professor at IIMS, Bengaluru, since 2016 July. He is also engaged in academic roles and advisory consultancy functions for ARG, DAE, and ORM, IAE. Dr. Ramurthy is an expert in the field of production and utilization of radioisotopes and radiopharmaceuticals. His interests also encompass radiation technology applications and associated areas of radiation safety and security of radioactive materials. He has got 45 years of professional and managerial experience in development of products and services, as well as in fostering the effective and safe deployment of the applications at national and international levels. He has served as the chairman and chief executive of Board of Radiation Isotope Technology, DIT, senior technical advisor to the Secretary, DAE, chairman of the Energy Commission, Mumbai, director of the Division of Physical and Chemical Sciences, IAEA, Vienna. Dr. Ramurthy is recipient of many awards and recognitions in India and at the IAEA. Now, what probably most of you don't know, probably none of you know, Dr. Ramurthy is the recipient of 2 Nobel Prizes. He even has, this is not just a joke. He showed us the Nobel certificate in our 15th batch WhatsApp group. And this is not published on 10. So that was only in the discussion of our 15th batch WhatsApp group that he once showed him. He doesn't deny it, but he doesn't propagate it either. But he has 2 Nobel Prizes when he was at IIT.
Thank you, Yogendraji. I think a very good afternoon to all of you, dignitaries, co-participant, scientists, delegates for this event, and some dear teachers and students. So it's put a nice opportunity, and when Professor P.S. Ramurthy, my mentor, and for me everything he is. So then he suggested suddenly on telephone, hey, you come and talk on that day. So I was quite pleasantly surprised, because it turns out that Dr. Grover and myself are the only 2 non-physicists who are talking today. The rest are all physicists, so to that extent, we are really honored that we have been able to be included in that. And when we discussed the topic, what came up was, we are all going to hear from so many of you on the nuclear physics and Ramanna as a nuclear scientist, nuclear physicist. That's all very well known. But he was far beyond that. He was also a great science program manager, science leader, and science collaborator builder, whatever you say. Like, a lot of unfriendly adjectives have been given, and I can't really be doing much to add to that. So I decided, let me bring up the point of the intergovernmental organization, International Atomic Energy Agency. Those of you younger students who have not seen, go into the IAEA website, you will get a host of information about that. And the DAE has some very close relationship. And that's what prompted me that let me pick up on this as the topic in my coverage. But as always, there has to be some basis why and I am doing it like. There had been a very long association with BRC for me. I had an entire career spent there. And also the knowledge of historical features of both the IAEA and DAE function, because I have been part of it. And also India's close special association. Many of you will know how Dr. Baba, preceding the formation of IAEA onwards, have played a great role in that kind of international organization forming. And because of that, we also have a link to Dr. Ramanna, whom Baba has taken along with him for many of the initial meetings. There are plenty of things to say about that, but at least some glimpses we should cover. And what could be a better basis for me? Dr. Ramanna himself has penned down a nice small piece in a book brought out by IAEA in 1997 called Personal Reflections by a variety of people who have been associated with IAEA in one form or the other, preceding its inception right up to the 97 point line. There the Indian opportunity to represent and give the article went to Dr. Raja Ramanna, and I have really banked much on that because I don't want to do my own imagination or digging up on the history and the idea. Plus, of course, I had some other project done for IAEA through which I had the access to their archives and personal lot of information could be seen. It so happens, I have been also a participant in the IAEA General Conference both during my tenure at IAEA and subsequently as a part of the national delegation. Having said all that, whatever analysis I am attributing as traits and credits, that's all completely personally my own analysis. Please do not attribute them to DAE or IAEA. It's not there. This very small part of nuclear physics, after all we are in a nuclear physics, so I should not go away without mentioning, even though much of this has been known about, this timeline is important. Key historic nuclear developments and DAE and IAEA will follow very close things like 35 was the nuclear fission discovery, so much has been said, we don't have to say that. But more important was the 42 Chicago Pi and the concept of the nuclear reactor. And then we all know the 3-year Manhattan project and what ended up as the August, we happened to be just finished the month of August, the dropping of the atom bombs there. But what's much less said is the June 1954, the first nuclear energy electricity production, 5 megawatts at Obninsk. That's again in that same timeline. Then comes the 55 conference on the peaceful uses of atomic energy, which was done and which led to the IAEA 57. Shortly about that we will see. So this, if you take as the key historic nuclear developments, like come to our own part. Dr. Baba's letter to Dorabji Tata Trust in late 44 and TFR is born in June 45. And Atomic Energy Commission created on August 10, 48. It was already mentioned, the department came into existence from August 3, 54, that's why the 70th year, our chairman already mentioned that. And then the Atomic Energy Establishment, Trombay, which we today call Baba after the Baba's demise. And also the Apsara reactor, the first in Asia. If you see the timeline between whatever has happened in the initial nuclear part and then the DAE, you will see the extreme close. So therefore Baba was extremely closely linked with the IAEA part, in addition to all his contribution to the Indian part, as the head of the AEC, DAE and AET, until his untimely demise on January 24. And actually he was on his way to IAEA for a meeting which we will talk about later. Therefore, it came. So these key developments and the date lines are extremely important, and that's what brings. And what about the birth of the IAEA itself? Obviously, having done the 1945 bombing, US was trying to do a lot of things, and then came the famous Atoms for Peace address to the UN General Assembly. But in those days, the big problem and tussle between the US and the USSR and all. It was an extremely laborious process, but a lot of science diplomacy synergy helped to bring about people together and think of an intergovernmental organization under the United Nations. And as you know, the United Nations itself was at the time like in a turmoil post the Second World War timeline, and at that time this being created was very difficult, but a lot of historic information is there. We don't have time to go into that, but that all evolved around bringing out about the 1955 conference on the peaceful uses of atomic energy, the Geneva conference, the proceedings, where plenty of information was shared and exchanged by people. And Dr. Baba was the president of that conference. And that continued in the other subsequent conceptualization, formation of IAEA, and again agreeing for a statute. Statute is something like your constitution. So that again all the countries with such huge differences, US, USSR divided, remember that to our period. But finally it was done. And then October 23, 56, the statute was approved. July 29, 1957, it could come into force, and therefore IAEA came into existence as a intergovernmental, but I added the word techno-political organization, because there is the science technology part of the nuclear, but nuclear was already shrouded with the military defense purpose angle, therefore it was also the political. And in those days they had the luxury, the first general conference was over 3 weeks. Dr. Mohanty may note that they go now for a Monday to Friday, and often he has to come back on Wednesday because there are calls from Delhi to him to return quickly. But in those first very one they have had for 23 days in that part. Now, we can go about telling how IAEA grew over probably probably next 1 hour, but we have no time to do that. But important point is the various mechanisms, means and mechanisms which have been evolved over a period of time, and where plenty of contributions of many of the leaders of the Indian Atomic Energy Program have been there. And as always in the beginning, because of the post-war time, like you are trying to give the goodies of the nuclear to the world community, the very first important point was technical support, technical assistance. This whole technical assistance, which was earlier there, has been subsequently changed. The assistance gives the impression of somebody like a giver-taker. To make it more acceptable plainly, it becomes technical cooperation. So the department which was long back known as technical assistance became technical cooperation. What it had contributed is to capacity building in nuclear area in different parts of the world. To the extent they need, somebody may need it only for a industrial application or education research, some other case it can be medical, not necessarily only the nuclear power production, but variety of things. Then the other important mechanism had been coordinated research project, which is probably one of the greatest of networking synergies. I can read the individual titles, but I don't want to take too much time, because overall time is restricted, and despite my batchmate chairing the session, I don't want to put him in awkward spot on that. But there are plenty of advantages, importance in that, because it's bringing together an international consensus on specific areas. Like for example, the safety standards to be decided, and then the safety stipulations to be done, etc. It will come. The same thing is about review missions. You may be doing a good job, you want to get your quality audited, you bring somebody from outside. Same way now here it is being done under the banner of IAEA. It's all being done by scientists from the world only. Different countries are all only called. It's not only the staff of the IAEA they come, but when they do the review mission, you get a stamp of an independent review mission. We have had the benefit of India taking it with reference to our nuclear power program as well as our regulatory programs also. Like that, plenty of other countries are doing. What more? Some of the countries you may be not getting full support from your government. What do you do? So these ministerial conferences which are supported and sponsored by the IAEA, which helps to engage them at the highest governmental level. Many will know about the nuclear military purpose or nuclear energy. They may not be so much aware of what all it contributes in terms of other areas like industry, medicine also, which were all also nicely alluded by Dr. Mohanty in his presentation this morning. So those kind of things become extremely important through the ministerial conferences. Then of course the so-called watchdog duties of the treaties under the IAEA, they are all there. In all these cases we have had contributions. We have also done sometime our own exhibitions, like, I don't think this works for me easily, but doesn't matter. You can see in the right hand side corner, sometime we put up an exhibition also in the general conference time. And interestingly, just for the historic information's sake, long back some of the general conference used to be held outside Vienna. Now no more. That was stopped long back. But India hosted one of them, and that was in 1979, and in the first week of December it was held in Delhi Vigyan Bhavan Conference Center. And there was a small group of people who were actually interested, so they were flown down to Bombay and they visited Bombay, our laboratories, etc. I vividly remember it. Now we come to the means and mechanism, the second part. This is like to say they were all the means, how much, what have all been the growth which has taken place. The very first one I am trying to more link with the period in which I was more personally aware, because it was Dr. Mohammed El-Baradei was the DG of the IAEA when I joined there, and he introduced during the General Conference week a 2-day thematic scientific forum. See, the 5-day General Conference is like, the national statements being read, the other kind of political, other resolutions being passed and all that, along with budget, finance, all those type of things. But then he created this thematic of 2-day scientific forum, which was extremely a nice, important one, and at the end of it, summary of the scientific forum finding will be presented to the General Conference. Our Professor V.S. Ramamurthy had the privilege of doing it once in the IAEA. Then of course came the 2005 Nobel Prize, because of which I would like to correct what Yogi was telling me, all the staff who were there on the date of announcement of IAEA being selected for the Nobel Prize award, they were all given a certificate approved by the Nobel Council and issued by the head of the institution, that's IAEA. That certificate we all proudly hold, and that's what he had shared also, so which he is mentioning. And that's the same period, within another few years came Atoms for Peace, the first half century, 1957 to 2007 events. So this period was one which was sort of important, because El-Baradei turns out to be the first DG of the IAEA who had come from inside the house itself. The previous DGs who were there in the earlier period, Eklund, the very first coal, Eklund, and the Hansplicks, they came from outside. Whereas Elbrade has held the position of international dealings as well as legal dealings within the IAEA, and he came. So he was sort of, extremely highly prepared manner, and that helped him a lot. I will mention the same thing here. In the Nobel Peace Prize, as he is receiving, the other person with him, many of you would have known, that is Yukio Amano, because he was actually the chairman of the board of governors on that time. So he, on behalf of the IAEA, and the award was to IAEA and its DG. So Elbrade, they both received. I always say that perhaps that day Amano decided, I will try to become DG IAEA. And he did get it, and he became in 2009 when Elbrade left, and he was through 2010 very lightly at that time, because we had come about 25 years away from the Chernobyl accident. There was plenty of good positive thinking about nuclear power. He was really giving a thrust to it. Unfortunately for him, within a year of his tenure came the Fukushima, which totally that Fukushima impact changed his orientation and the thing and it took several more years now for Rafael Grossi to once again bring it up. He of course, Amano shifted the focus to cancer care, agency labs, renovation, which was one very important one. They had a lab, but as we all know, the equipment will get old, we need new ones, renovation, upgrades and all that. That needs to be addressed, and that got done through him. And it goes to his credit again. The ministerial conference, beyond being only for safeguards or safety type of topic, to bring it for the applications areas, nuclear applications and technical cooperation, that he started. And Amano also brought in the type of the board that our contributions are going towards the UN Sustainable Development Goals. The text logo, which used to read Atoms for Peace, got changed to Atoms for Peace and Development in that period. Then came Rafael Grossi. He again, like Elbrade, had seen, he worked with actually Amano in his office as the chef de cabinet, and he has also been in the embassy and Argentinian program. So he again entered on day one as a very strong person, and he has been going all guns about all the applications of nuclear side, not just only the power production. Every one of the aspect and for so many of the sustainable development goals it contributes, and that full base, and right now also on the low carbon basis he has been, this is one of the kind of a paradigm shift in the IAEA approach or the functioning that had been there. So these are all the part of the IAEA part. We come to know our side of it and Ramanna's we have all seen so much had been said about, so therefore I cannot really be adding anything much. But more important was Baba and him, they met in 1944, and that was to do with a common music interest. One of the scientist music person introduced them, and 3 years later Ramanna received a job offer, and he completed his PhD, and then only he can join. So that's how he came and joined in 1949. Then we know the rest is history. He has held all forms of positions and private, done everything to the nation. But on a personal note, it so happens that we are from the 15th batch is 1971-72. 71 end we actually lost Sarabhai, then Setna became chairman, Ramanna became director bar. So the Ramanna becoming director bar from director physics group took place during our period, and his kind of affinity for the training school was so much. After taking over as director bar, he came once and addressed the trainees as which is something very special. He did not do it at all, he's already gone up. But his attachment to the training program and the importance of that was so much came at it. And I happened to be radio isotope program and all my life. And in that sense, again, we are grateful to him because he gave a boost to the isotope program. He held the program-wise reviews in those very early days. In our old C block auditorium in the TSC meeting room, that he used to do program wise and I remember that was part of a contributor towards the isotope program being shifted up, and then also he ensured through an AP Shah committee to think of the future. That of course came through MRS period, MR Srinivasan period, but it was Ramanna who had created that eventually led to the formation of the Board of Radiation and Isotope Technology grid, which Dr. Mohanty referred in the morning. Now, what was Ramanna's one of the key role, which probably earlier Dr. Baba has also done, is what is known as IAEA Scientific Advisory Committee, SAC. This was formed within a year of the IAEA being formed, because you have now created a structure that institutions head and their staff themselves, they cannot be really driving or managing. You need to ensure what should be addressed, that advisory support will have to come, and for that at the highest level, there was kind of a scientific team with reference to the UN Secretary General, and the same 7-member thing, like Dr. Baba was a member in that, like, and this was giving the very, very valuable inputs in terms of the scientific thing, and also maintaining a delicate balance between the IAEA Secretariat to be accountable, reportable to their Board of Governors, and also at the same time ensuring the aspirations of the developing countries, what all can be done by nuclear and what should be contributed to that. In addition to your producing nuclear energy, nuclear power, that type of support, essentially one of enabling pursuit for larger goals, dissemination of knowledge and information. That was the key feature, because IAEA cannot go and build a building everywhere like or industry there like, but the dissemination of knowledge and information as a key feature, that was the great part. Into the same committee, Ramanna, when he was the chairman, he was the member from here. It's a very small group even later on, like, and he had the chair position for 4 years. But unfortunately, that was a time of handsplits, and for certain political differences amongst countries, they didn't want to have such a kind of a powerful scientific advisory body which is sort of overseeing the entire thing. Like. So it was put to a kind of a tapered, closed down situation at the end of 1987. In fact, Ramanna says, for reasons unknown to me, like he has made the remark in that book, like, but he also attributes what could have been the possible truth. I don't want to go into it now, but that was the last meeting in there, and he was actually the chairman. So India had the influence, impact to make such a kind of a global thing on the world thing. Like. Now, quickly finish it. Ramanna as a scientist in the IAEA. I was in the morning very impressed that nice, I think Amit Roy only mentioned about the collaboration. Imagine Ramanna in 1962, a young, bright thermonuclear scientist doing things like he recognized in one of the IAEA event related to the reactor utilization as an eye-opener how such a forum can really help so many of those countries to come together, collaboratively work and manage. And that's in fact the essence of IAEA's contributions all the time. So that's where I think goes beyond being a scientist, the manager, far-sighted, visionary approach, like he had used that word, an eye-opener to him. Imagine at that time with his standing and so he need not have, he could have been a scientific view and come out but he recognized that and utilized it in many, many forums and places. Many countries came together to produce, be it mutants or study materials using new isotopes, etc. And also the IAEA providing a forum for topical events. One of them was the heavy water based small reactor, where Ramanna happened to be the chairman of that program committee. In addition to being a scientist interaction, he also had the official interaction as the leader of BARC and DAE. And in that, there is 2-3 things to say. One is, around 1980, he and of course the Indian government made the thing, we are like a developed country, so we will only be a donor for the technical cooperation, technical assistance program. We will not be a recipient of that anymore. And then he had, May 74, you all know, PNE, so much has been talked about it, and just after that he was in the IAEA also, so he had directly felt the heat of it. And it happens that in 1986, when the Chernobyl took place, he had the role of being the chairman of the General Conference, because the turn of India was that year, the General Conference presidency was to be with India, and he as the leader of our delegation was the president. So he had the first-hand feel of the Chernobyl, the global response reaction to that. Again, kind of the maturity of him that, in the handling and doing all the kind of the things So Ramanna is a scientist, Ramanna is the head of the BRC and DAE and the IAEA. We have had continual roles of the atomic energy program leaders, subsequently also influencing, impacting the IAEA programs. And I don't want to get into, because of the time and not to put again Yogendraji in trouble, I just want to take 2 examples of people who are very close associates of Ramanna also. Chidambaram was associate and a colleague there, and Ramurthy, as we know, was his ward, and we have seen him. So they are again bodies through which the global impact influence could be very nicely be done in the kind of the thing, and that is what had been achieved. What Elberade, again I go back to Elberade, what he did 10 years after the expanding of the scientific advisory committee, which I mentioned, where Ramanna was a chair, he decided that we need a senior experts group to review the program and then give some advisory, etc. Because he had known the advantage of SAC probably, but he knows that it had got disbanded. And that senior experts group had Dr. Chidambaram as a member, and he was also chair of one of the working group number 4. The path was to advise a lot of things. There was a lot of interaction troubles in IAEA. The technical cooperation and the nuclear application should be merged, in which case the science component and the kind of the project management delivery component would have been really got merged, and there would be dilution. Those kind of things to be averted. All this Dr. Chidambaram could very effectively do. And I had the fortunate lucky thing because of that working group 4. At that time I didn't know what and all about it, but I was lucky to have been involved. So I have personally perused those documents, helped him to do. I only want you to just see the dates of the meeting. May 98. You all know what was important for May 98. It so happened one of their meeting was just within 10-12 days after the Pokhran our thing done, and Chidambaram was travelling for that. And friends, April when the papers were coming, I will be called for one Sunday right in the morning, another day evening. I will get my papers, do the work and give it back to him and come back to him. But fortunately because of this, I had the privilege of directly greeting him within days after the Pokhran in person. That's a personal thing. But more important is, one of the creation out of that SEG committee was individual departmental programmatic advisory group, and there the scientific advisory group for nuclear applications, the very first founder chairman was Dr. Ramurthy, selected by Elbrade, and he served for a record 10 years. For none of the similar bodies they have had one, they would change in 3 years. Again goes to show the kind of the broad-based leadership guidance, what could be done, and bringing together the people part of it. That contribution of it is what was contributed. I will not go into the details. Just one more thing about the Chidambaram's contribution, because after the SEG is created, this was all going on. But again, Elbrade, knowing that he will be completing his term and there should be some long-term vision, like many of us will know, in DAE we did the Vision 2020. So Elbrade asked for an arrangement through a group called the Commission of Eminent Persons. In these type of things, there will be nuclear scientists as well as political governmental leaders. The one important point is there was only one common member between both SCG and CEP, and that was Dr. Chidambaram. That's again to do with this rapport with Elbrade and the important part of what all could be done. And that committee gave a large amount of nice records, which are all now also guiding them, and it's going through.
I think you should conclude now.
Yeah, I'm just concluding remarks. So India continues to be actively engaged in all the programs, and apprehensions were cited by Ramanna that could be still recalled because they are valid today whenever you find some differences in the views between some countries and all. The science-driven approach, striving to counter any political impact, that has been the key. Science-driven approach, striving to counter, that has ensured it remains a global forum. Ramanna was not alive to see the IAEA and its DG receiving the Nobel Prize in 2005, but would have been very happy of all his contributions. It's again a sheer matter of coincidence that Ramanna breathed his last in Mumbai in the same week as that of the IAEA's General Conference when it was going on. I wish to conclude with a quote from Dr. Ramanna himself. He says a word about the future, how the work of the agency will go, the promotion of the peaceful use of atomic energy and policing of the world. This conflict type of vis-a-vis, like managing, balancing, check, balance, control, that will remain a major question. It has remained in the past, it remains, it will continue to remain, but that is a main thing, like he has said. But he also adds, my wish is the positive side of the work of the IAEA will come into greater force early in the next century. I am really happy that I got this opportunity, thanks to Dr. Ramurthy, Dr. Dinesh Srivastava and others, to be able to address on this particular topic. And I thank you all for your attention. I know there are many questions and answers. My email is there. Comments, questions, criticism, all are more than welcome. Thank you all very much for your kind attention. Thank you.
Thank you, Ramurthy, and I thank all my speakers to maintain time.
Thank you, Dr. Yogi and our eminent panelists. Now I would request Dr. Dinesh Srivastava, the fulcrum of this event, and eminent nuclear physicist, former director VECC and currently INSA senior scientist at NIAS, to give his observations, and after that we will close with my vote of thanks. So thank you for your patience. We are just for
इसको बंद करो. Can you switch it up?
Yes.
Okay, good evening, ladies and gentlemen. Imagine two people walking in a desert, but there is not a single drop of water, and then coming into an oasis, even a salt-lipped oasis. That is the reaction of me and Dr. Ramurthy had last so many years we have been starved of news about nuclear physics, and today we were soaking nuclear physics from morning to evening, and it has filled us with bliss. So we have just experienced an intense, invigorating day full of nostalgia, satisfaction of fulfillment of dreams, and visions of even bold, loftier dreams, discussing nuclear physics, past, present, and future. In the fervent hope that these discussions would have pleased the colossus among nuclear physicists in the country who gave a direction and presided over it for decades, Dr. Ramanna. Among many memories of Dr. Ramanna, 3 memories stand out when I think of him. The first one is of summary talks that he traditionally delivered at the end of annual day nuclear physics symposium. Dr. Bhandari, Dr. Chaudhary, and Dr. V.S. Ramurthy will remember. This was originally called Nuclear Physics and Solid State Physics Symposium. It used to be full of insights, valuable observations, and future directions. He rejoiced in the hard work and exciting results of colleagues. He created consensus on creation and utilization of new facilities, and especially he identified promising young researchers from across the country, and it was always full of humor. He was quick to spot brilliant students and made a point of his seeking them out. We have heard from many speakers today how he did it. He was quick to spot brilliant students and made a point of seeking them out and encouraging and enthusing them. And of course, he was an excellent communicator. Dr. P.K. Iyengar, his equally famous successor, famously called him an energizer. Nothing could be better and closer to truth than that, as he remembered even the junior-most employees who were contributing to our programs. He was always forever alert to openings and opportunities which could help his colleagues and nuclear research in any manner. The second one involves the electrifying moment as he entered the jam-packed and completely overflowing Central Complex Auditorium of the Bhabha Atomic Research Center in Bombay a few days after May 18, 1984, after returning from Pokhran, to a tumultuous standing ovation lasting till our palms ached. The last and most sacred memory of him I have is that of his visit to Variable Energy Cyclotron Center, Kolkata, to unveil a statue of Bhabha and to inaugurate the newly constructed Meghna Saha Auditorium in our campus. The most delightful part of that event was an hour-long mesmerizing celestial piano recital by him, followed by a santoor recital by Pandit Kumar Sharma. The two giants also played a short and delightful piece together, to the utmost delightful of all of us. This was especially nice as we saw his facets as a great scientist, a great speaker, and a great musician within a span of about 2 hours. The studies of nuclear physics in the country have progressed from simple beginnings using alpha, beta, and gamma sources, neutron generators, a small cyclotron, a Van de Graaff, a variable energy cyclotron, and the 2 pelletrons with superconducting Linac boosters, to the access to relativistic Hadron Collider at Huxman National Lab, Large Hadron Collider at CERN Geneva, and facility for antiproton and ion research that is FAIR at Darmstadt. India is now part owner of the FAIR facility. In addition, our researchers have been participating in experiments at all major experimental nuclear physics facilities across the world, individually and as a group. There is a phenomenal and exponential change in the energy of projectiles and complexities and reach of the detector systems during this period. And this brings one memory of Dr. Ramanna
of which I am made aware every now and then with the only other nuclear physicist on the campus, Professor B.S. Ramanna, who is the driving force behind the present event. Dr. Ramanna, in the early 1960s, proposed a nuclear ion exchange model utilizing random walk to explain the mass distribution of fission fragments, about which we have heard repeatedly today, which generated a lot of interest across the world. Professor Ramamurthy tells me that in 1965, the annual nuclear physics symposium was held in Calcutta, and they were taken on a boat trip on the Ganges. During the boat trip, Professor Manoj Banerjee of Saha Institute, who was still at Saha Institute, commented that Dr. Ramanna, no amount of discussion is going to resolve this issue. And the only way to confirm and validate this theory is to bring two heavy nuclei close to each other where they overlap and see what happens. That was an impossible dream at that time. One of the last acts of Homi Jahangir Bhabha was to take a decision to build a barium-mineralized cyclotron at Calcutta. Years later, Dr. Ramanna was to persuade Mrs. Indira Gandhi to agree to buy a pelletron heavy ion facility for BRC TFR Bombay and build a multi-GeV synchrotron radiation source for condensed matter studies. The pelletron facilities at Bombay and Delhi were upgraded with superconducting linear accelerators developed indigenously for heavy ions to study fusion fission dynamics, which among many other things repeatedly confirmed the mass distribution mechanism envisaged by Dr. Ramanna. Their Center physicist at Barium Cyclotron Center went on to build and commission a superconducting cyclotron. The Radha Ramanna Center for Advanced Technology participated in the construction of the Large Hadron Collider and opened the doors for India to become major participants at experiments at CERN and participate in the discovery of Higgs boson and quark-gluon plasma using detectors conceived, designed, developed and constructed in India. India is now an associate member of CERN, about which you heard. The nuclear theory scene has progressed from simple Hauser-Feshbach and optical model calculations and simple but profound nuclear structure calculations to ab initio cell model calculations. You just heard beautiful talk by Chilam using density of functional theory to study dynamics of fission of heavy and super heavy nuclei. The contribution of our researchers to the theory of electricity heavy impulsions and quark-gluon plasma is both profound and extensive. Neutrino studies, as we heard from Professor Tata, especially neutrino-nucleus interaction is yet another field where our researchers have made pioneering contributions. From the use of modest computer programs run using punch cards, we have graduated using supercomputers, massively parallel processing computers for calculations and simulations, and vast resources of bridge computing spread across the world to analyze the data taken at CERN, for example. We have tried to organize a program to cover all these aspects as a tribute to the vision of Dr. Ramanna. We are grateful to all the speakers for bringing out the vibrant and wondrous charm of nuclear physics, which Professor Ramamurthy is comparing to the beauty of Cleopatra, telling age cannot wither her, nor custom stale her infinite variety, which he borrows happily, where he happily borrows the words of the Bard of Ravan. Thank you, ladies and gentlemen, for a day of rejoicing and celebrating the glory of nuclear physics and the efforts of all those who made it possible. We lean back in satisfaction that the field is in competent hands and has a wonderful future. Thank you for taking the trouble to come and meet as a tribute to one of the greatest sons of Mother India, who opened the doors to security forever for our country and to ever-widening scope of research and development in all aspects of nuclear physics and technology.
We thank Department of Atomic Energy, Dr. Ajit Mohanty, Dr. Grover for supporting the event, Professor Shailesh Nayak, Mr. Srivastava, and NYAS for extending all support, and Dr. Rudrodip Majumdar for braving the troubles of organizing it. We are grateful to the speakers, the chairpersons, and our participants for a very satisfying meeting. I would like to invite the main actor who made this event possible, Dr. Rudrodip Majumdar, to kindly offer a vote of thanks before we break for tea and a musical performance for excellence. Thank you.
Thank you, Professor Srivastava, for your kind and generous words. So before moving straight into the thanking part, I just want to mention one line that today's event appeared to me as a warm and fairly large family get-together interspersed with a series of enlightening discussions. Such a successful hybridization is indeed unique and does not happen often. So at the outset, I wish to extend our sincere gratitude to Dr. Ajit Kumar Mohanty. Despite his high-profile responsibilities and packed schedule, he has found time to come down to NYAS. We deeply value this relationship and personal touch from you, sir, and I am sure that this relationship will continue. Our director, Dr. Shailesh Nayak, you are the patron of all the activities at NYAS, but I wish to mention your name because of the continuous encouragement and support you keep on providing. It does a world of good to our collective self-belief. Professor V.S. Ramurthy does not require any introduction to the NYAS family or DAE or Nuclear Physics Committee. Only from my personal experience, I want to mention that he is like a big banyan tree for us. We at NYAS, everyone rest in his shadow and play around his branches, and we hope to continue accessing such privileges in the days ahead. He was the guiding force for this event, and I hope we did some justice to his expectations. We are very grateful to Professor R.B. Grover for facilitating this event and his active participation. I don't want to make it very formal since he told me not to do so. He is also a senior member of our NYAS Academic Council. Professor Srivastava, of course, he is known as an eminent theoretical physicist. I am not going to that part. What amazes me is his continued tenacity like a 27-year-old, his frankness, warmth, and his general curiosity about life and science. We are hugely grateful to all the eminent people who kindly served as chairpersons, speakers, and participants today. This event has become really bright mainly because of you. The rich lectures and the discussions will stay with us for quite some time. I am particularly happy to see a substantial number of students and young scholars today. After listening to some of the top nuclear physicists in the country, I am sure the spark of aspiration has been kindled in some of your minds to pursue higher studies in theoretical and experimental nuclear physics. The event could not have been possible without the tireless support from the NYAS administration, logistics department, hospitality staffs, photography and videography staffs. We are grateful to all of you. You continuously keep on working behind the scenes so that we remain relaxed during the programs. I am very thankful to my students Saurabh, Bamshij and Deepak, who happily took up responsibilities when I approached them in the 11th hour. I loved your team spirit. Finally, I am grateful to the NYAS community as a whole for showing this sincere respect to our founding director, the great Dr. Ramanna. Our technical session ends here. However, the day is not yet over. Now we'll break for this tea, as Professor Srivastava said. We'll come back in about 20 minutes. My colleague Dr. Ramya Bala will introduce you to three very accomplished musical artists. I'm sure you will have an immersive musical experience this evening. I sign off here. Thanks once again, ladies and gentlemen, for your wholehearted participation in celebrating Raja Ramanna.
कलकत्ता से पूजा के बाद अरे पूजा के बाद हाँ पूजा तो कलकत्ता में होती है समटाइम्स कम पूजा आई एम मोर